Okay, I got bad news for you. My name is not Jenny Dietz. She's sick today. She was going to be the MC, so now you're stuck with me, the guy with the face and a voice made for writing blogs. My name is Jim Pfister. I'm a contractor for SNIA, and you'll see me a little later today talking about a different program. I want to welcome you to the Persistent Memory Summit. I think this is going to be an awesome day. We've had a great organizing group led by Jenny Dietz, who's been working on this agenda for a good 3 or 4 months. We got some very exciting submissions, some good keynote speakers, or a great keynote speaker, some very good content through the day talking not only about the hardware around persistent memory, but the software environment for persistent memory and real life people doing development for persistent memory. So I think it's going to be a great and exciting day. Everybody pumped up? Yes. Come on, I know the coffee wasn't out there in the lobby, but get moving. So our first speaker is going to give us a good State of the Union. Everybody knows Jim Pappas. He's pretty easy to spot. He's pretty easy to hear. Jim is a SNIA board member. Jim is a longtime Intel employee who one of the smartest men at Intel once said, "Jim, you are the perfect guy for the perfect job for what you do," and I think we would all agree with that. I will also say Jim is very persuasive if he knows you like beer. Jim Pappas, come on up.
Thank you, Jim. And welcome again to our, is it 7th? We started in 2013, the first PM Summit. It'll be 7th. And this is, those of you who are on LinkedIn, you probably saw this is my favorite event of the year. I pointed that. There's something about this that really turns me on, getting a lot of smart people from across the industry and sitting in their chairs for like the whole day on a single topic. You're doing something right when that happens. So thank you for coming. So that's me, and today I'm going to talk about giving an overview of what's going on with persistent memory, where we've been, where we've gotten to, and you could guess from those of you who've seen me, I'll talk about this. I'll probably talk a lot about outer space, so because I just happen to like it, and I never talk directly about what we're talking about. I always talk in metaphors. It's just the way I talk. What can I say? So a little bit about SNIA at first. This is, right now we have, this is pre-Persistent Memory Summit. We have people from the symposium in the room. I'm going to give an introduction on PM. Then we have our keynote speaker who'll be coming in, Andy Beckelsheim, this year. I think everybody knows Andy, and we're very, very pleased to have him here this year, although he hasn't shown up yet. So. Any bets whether he shows up with his Birkenstocks and socks on? I mean, I think that's probably a given. I've never seen him anywhere or anything else. But about SNIA, we have about 185 companies involved, a couple of thousand people who are actively participate and volunteer their time. It's a volunteer organization. And we have a reach of about 50,000. So our mailing list and our people we influence is in that range. So it's a very, very substantial organization. So and I've had an absolute blast being on the board of SNIA since we brought in persistent memory into this in 2012, mid-2012, June 2012, in fact. I had the honor to present that to the SNIA board, and it was accepted. And I had also asked, that this is really important to my company. Can we come in and get a board seat again? And that was also granted. And it's been a very, very fun ride. Andy Rudolph's over here. I see him nodding. Andy is the chief architect, really, for persistent memory, and it's been a lot of fun. I will say, and I'll talk about this in a second, we really were not expecting persistent memory to take this long. It's hard. You know, projects are based on your previous experience. And so, for instance, my company, we built CPUs, and we you know, there's a formula for how to do it. And you know, things don't always work exactly the same each time, but you know, you've done it before, so you know what kind of has to happen. When you're doing something new like persistent memory, it was very unknown from one step to the other, which is why I like to compare it to our space program. You'll see me doing this later. Because it was the same thing. You know, it's never been done before, and when it hasn't been done before, you really don't know what to expect. So, back to SNIA. We've spent 20 plus years doing development standards, and Ken Gibson, I saw Ken walk in a while ago. There he is. Back when we were trying to decide, you know, my company was working a lot on persistent memory, and I had the action item to figure out how do we standardize this. We were talking to many, many companies in the industry, and everyone says this is really cool stuff, but there needs to be an industry standard. And I think Ken and I made the presentation to our executives, and we recommended SNIA as the place to do it. It was approved. And that's kind of what started this whole thing off. So I'd like to acknowledge Ken's contribution to that. So so here's my portion of the talk. I'd first like to thank our sponsors. Without our sponsors, we could not do this event. And it's free. It's been free all the time, and it's not cheap to run, but it is. We feel strongly about this. It's important. So, and we could not do it without our sponsors. The SNIA Solid State Storage Initiative, soon to have a new name, by the way. Inside of SNIA, there's another new program called Computational Storage that's moving into the Solid State Storage Initiative, and there's a new name coming. To be announced any day now. I think they decided the name yesterday, but I don't think it's quite public yet. I think it still needs to go to the board tomorrow. Those of you would have received a little card when you registered today. That gives, there's a new book on persistent memory that is just coming out. And he actually has a copy of it. And if you, with that QR code, you can get a free copy of the book. So if you did not get a card today, just stop by the registration desk and get one so that you can get the free book. That was, Intel had asked to distribute that at the conference instead of having a table, which was kind of came with the sponsorship. We decided we wanted to give out a booth instead. Come on in, Dave. And so MemVerge has got a table out here, Smart Modular and Smart IOPS. So thank you very much. So I'm going to go back and do a little bit of history here, and pick the last few years. And you know, Doug Voigt made this slide several years ago, and it's a log slide. It shows where we have, you know, the media latency between various types of media, from memory or persistent memory, and then into various SSDs, and then finally, you know, hard drives. And it's on a log scale, so it doesn't really generate it. So if we were to unlog this, unlog scale it, and this is a smaller conference room than some, but if let's say that this was 18 inches on the screen, how high would the other things be if it wasn't a log scale? So SSDs, you know, NVMe a little bit faster than SATA, but if you kind of average them, it's about the height of the Empire State Building. And then after, I'm not going to ask you to raise your hand if you still use a hard drive. You know, I don't want to embarrass you. And this is done by the Solid State Storage Initiative, after all. Okay, I see that Tom Friend, who previously was working on hard drives, is giving me grimaces here. But It's back up. So the hard drive is, and going to outer space here. About 2/3 of hard drives would be above the Kármán line, and Kármán line is 100 kilometers, and that's where NASA considers the end of our atmosphere and the beginning of outer space. So about 2/3 of it, so we're up in spacecraft territory up there. So we kind of did this to poke fun a little bit at what these latencies really are and what 6 orders of magnitude feels like, and looking at at the time most people were still using hard drives, and we were talking about 6 orders of magnitude of latency removal, and architecture is probably going to change significantly. Then the next year I did something totally off the scale, and I wasn't really sure. I wanted to use a space theme, and I just woke up one morning thinking about, you remember hydrazine and nitrogen tetroxide? I mean, who's going to forget when we talked about that? I'm looking at Nathan. Nathan, I'm sure, remembers that one. And it was used as a metaphor. I told you I always talk in metaphors. But these two components, when you touch them together, only one possible thing can happen. They're hypergolic. They start burning. You don't have to give a spark. You don't have to do anything. If you just open 2 valves, and that's what goes on in like the command and service module and the LEM that lands. They use nitrogen. They use hydrazine and nitrogen tetroxide, and they don't have to do anything. We've always gotten the astronauts back because you open 2 valves, the stuff mixes together, and there's only one thing that could possibly happen. It just burns like hell.
And they say rocket science is really the smartest.
There you go. Right. So, and of course, that was a metaphor for if storage and memory come together. Realize at the time we have not done any of these new technologies, to be able to scale them and put them into manufacturing. But if in fact they come together, something will happen, and that is there'll be an architecture disruption. It's got to happen. The benefits are so outrageously changing. 6 orders of magnitude. No other possible thing could happen. And then after the next year, I didn't do too much about space then, but when Stephen Bates, and unfortunately Stephen's not going to be here today. Stephen's family is sick, and so he's up in Canada nursing his sick wife and kids. I think he just recently recovered himself. So he won't be coming, but in the middle of his talk, and I don't think oops. Oh, there we go. In the middle of his talk, he was talking, I don't remember the exact sequence, it was probably something like, how you do this stuff, and you do an S-fence operation, then you try SCE to aux, and then you do a PM flush. And he said it, and kind of nobody kind of caught on, but he looked at me when he said it. And I'm not going to go through the story on trying SCE to aux, but those of you who don't know what I'm talking about, Google it sometime. It's just a great, great story about this very young engineer, straight out of college, 22 years old. He's sitting there in mission control at the thing, and it was a couple years later when this was Apollo 12 actually, when he saved the lives of the crew more than likely, and certainly saved the NASA program. It's just a methodically great engineer, the engineer of engineers. The steely-eyed missile man became his thing. And I won't say more about this, but it's when we're off debugging something and we can't figure out what it is, I oftentimes say, well, just try SCE to aux. And it's up to you. If you don't like to Google, and just catch me in a break, and I'll tell you the story. So, buy me beer. So here we are, 2020, and what am I going to do? Of course, I'm going to talk about space. It's not really a question mark. So, thinking over the last few days, where are we in this program? And as I said, we started this in June of 2012. That's 7.5 years ago. So 7.5 years after we started this thing, Apollo 7. That was the first manned Apollo mission, was Apollo 7. It was supposed to be Apollo 1. It was supposed to be the first, but we lost that crew on the ground in the fire. And things changed, and there was a delay. I told you persistent memory is taking longer than we thought it would take because everything is new. Well, the same thing happened. So they were behind schedule, but that was 7.5 years. And if you go from June of 2012, we're 7.5 years into it. So we are there. So, and there's this one event that really, pretty much everything has to be done before you could go on. And that is clearing the tower. When you, and that's where I think we are with persistent memory right now. If you, clearing the tower, this is probably the most dangerous phase of the flight. Spacecraft is sitting there right up against the tower. Any of dozens of system failures, a bad burn, guidance software being off by minuscule amounts, anything. You have, the astronauts are sitting on 450 tons of liquid rocket fuel with enough energy in it. I don't know, it's relative to atomic bomb, I think it's like half of atomic bomb or something like that of energy. I don't know the exact numbers. But, everything could go wrong, and clearing the tower is a critical step. One more thing too, when the commander, says we have cleared the tower, he says, the clock is running, and then the second thing he says is we've cleared the tower. That's when the Kennedy Space Center says, Houston, they've cleared the tower, it's over to you. And from that point on, Houston runs it. And the thing I liked about this, and I hope I don't upset anybody because I got this wrong, but the first system shipping with persistent memory was, in my recollection, was an HPE system with NVDIMMs. I can't remember which vendor, but it was the first OEM, and of course they're a Houston company. So I just want to do a shout out to our friends at HPE. I think they were actually HP at the time, but it took a lot of firsts to get us here. So we cleared the tower. And so I have some proof points of why do I think that we're at this point. And going back to NASA, going back to Apollo, and never having done it, they had 7 things that they needed to get done. And it was things like, we need to build the machine to get us there. We need to build a suit that will protect people in space and on the moon. And we need to be able to do an EVA. We need to leave the spacecraft, do a spacewalk in space, and get back in. Can we do that? Can we get out? Can we get back in? Will it all work? We need to do long duration flight. We need to do rendezvous. We need to take 2 spacecraft. We need to rendezvous. We need to find each other, get there, get in the right configuration, then we have to dock. There were 7 different steps that they needed to do. Long duration space flight was another. Can you actually go up there and spend a few weeks? That's what it'll take to go and come back. Can you actually do that? Will the human body live through that? So they had to prove all of these things one after another. And I arbitrarily picked 7 big things that we needed to do in order to make persistent memory happen. So we needed the standards. And as I said, we did this in SNIA. And very, very appreciative to SNIA on this. We have to get media. We have multiple medias right now, and several more arriving. Dave Eckelstein will be talking about this later in his talk. At this point, most or all OEMs and ODMs are now shipping, having some SKUs with persistent memory in them. Major, major accomplishment, both with NVDIMMs and other native persistent memory technologies. Probably one of the things that we did, and because of, and I'm looking to Andy over here, because of the programming model that we delivered, both Windows and Linux have almost exactly the same APIs. And the chances of this doing without having that programming model and that level of clarity was about 0. And big, big step. And we have, in fact, the OS companies outperformed the hardware companies delivering the products behind that. We had OS support before we had really stable, available hardware. A remarkable, remarkable achievement. We now have hypervisors. We have actually two, VMware is giving 2 talks today. And if those of you remember when we had Scotty Miller from DreamWorks on stage a couple years ago, and people asked him, how can we deliver this to you? He said, through the cloud. And he said, that's how I need it. And we have 2 cloud vendors at least now. I know that both Google Cloud Services and Azure have both publicly announced availability of persistent memory instances. Sometimes they're specialized, like for instance, like to make SAP HANA as an example initially, but that's how these things start. And it's out there. The technology is starting to have things. And then finally, applications. And we have several, not enough. And I think the biggest reason is because we have, I have to hurry. Because in order to get the entire industry doing it, fear drives it. And when you see applications coming out and you see the benefit, and we know that the inherent benefit is there with the orders of magnitude of improvement that persistent memory brings, companies will start fearing that, oh my God, this is really happening. Where's my program? How do I get involved and stuff? And we'll see an acceleration. Under development, working on more applications. We have, SNIA has taken the ball and we've been driving it from the base up. We running hackathons. Jim Pfister, who is the new Jenny Dietz for today, and he is running that. And we're taking responsibility to kind of create, our goal is to create this ecosystem. And then new hardware interfaces. Stephen Bates, his talk is not going to be given by Stephen, but we'll have Milind Mittal coming in here later on. He's Mr. C6. He was the key architect for C6. He'll be talking about CXL today. And new media, also Dave. So these are all things that we still have ahead of us, but we are very, very far along at this point. Yeah, it's really real. This is on Jim's hackathon program. Amazing. We hired Jim to do this thing in December of last year, late December, like December 28th or something like that. I think I gave him the call. And he actually had the first hackathon a year ago, essentially today, at the day of this event. And he's since trained, it's over 325 or there people have come through the hackathon training. He's got an award program, a competition going on for, this is running on NVDIMS. And I don't know, you're going to have a couple of surprises today? One demo out there. One demo out there. So, yep, I know. Okay. And then, as I said, CXL is coming. CXL will be a new attach point for persistent memory. And it's because we really, right now, persistent memory sits on the same bus as DDR. And it's really a lousy place to do it, to be honest. For one reason, it's intuitive that the more persistent memory you have in, the more DRAM you also need. And of course, but we're trading them off. You don't really want to have to trade them off. As one grows, you want the other to grow as well. So the persistent memory will be moved off of that bus. It'll be moved onto its own dedicated interface, one that's better. And you have a talk on this later on that Milind will be giving. And there's our agenda for the morning and afternoon. And with that, that's the end of my talk. And, oh, one more slide. Did you throw one in there for me? Oh, okay, yes. So enjoy the summit. And it is going to be live streamed today. You could ask questions via Twitter. And we'd love you to hashtag this one as well. So with that, I'd like to invite our keynote speaker, Andy Beckelsheim. He does not need introduction. I think everybody knows Andy in the computer industry. He is going to take a second to set up his computer. And it's a really high honor. Andy, how many times have I asked you to come in and do this keynote? I think at least 4 or 5 times. And it was always, well, maybe next year.
Good morning. I wanted to talk about disaggregated, sort of decentralized distributed storage from a very network-centric view. I'm obviously working in the networking space lately, so this talk is mostly about the networking element of this, and then I'll get back to the storage element a little later. And what's happening in the network, as you know, the world has moved to the cloud. There's billions of these and billions of tablets being served by millions and millions of servers in the cloud. You've seen the pictures. These are some pictures from the Google data centers. The size of football fields. They give employee bicycles, to get from one side to the other. That was on the consumer side. On the business side, lots of people moving to the cloud. It's estimated that by 25, roughly half of the enterprise workloads will be in the cloud. It's growing at about 20% a year, according to both Gartner and IDC. And obviously the cloud business itself, the search, social, and so on, is also growing at about 20% a year, driving tremendous hardware investment. The hardware side of this has dipped a little bit because, quite frankly, the hardware got cheaper. In particular, flash and memory got a lot cheaper in the last year or two. So people are getting more equipment for the money. But there's no question that by now over half the new servers are going in cloud environments, no longer on enterprise on-premise. And obviously the data center network, the business I'm in, follows that. So the majority of data center networking is now in cloud data centers. And one thing about these cloud data centers is that there's a lot of bandwidth within the data center, meaning the intra-data center traffic has grown the fastest. On the picture on the upper left, which is from Facebook, the little green slice on the bottom is the traffic that comes out of the data center. The red portion is what's going on inside. And this is being driven, of all things, largely by flash and distributed storage. So, and of course, new applications like AI, machine learning, video streaming, and so on. So the age-old question in the cloud was, you got 100,000s of servers, millions of virtual machines. How do you interconnect these things? And at a speed of tens of gigabits per second per server, which adds up to multiple petabits of aggregate no-logging bandwidth at microsecond speed. And the whole point of this is to make this cloud sort of transparent to the application so that the application writers don't have to worry about data placement. In other words, the application should be able to run anywhere with any amount of data, scale up and down as needed. In the old days, more than 10 years ago, before there was big enough network switches, people had these things called pods, not to be confused with iPods, but they were like clusters of maybe 64 racks that were interconnected with a switch that could handle 64 racks. But what people found out is it just didn't scale beyond the pod. And the new picture that is universally adopted now is leaf-spine networks, including multiple tiers of these, where you have basically equal distance between any server and any other server, meaning you can get to any data at the same speed. In a larger data center, like this is a picture from Microsoft, There are typically 3, in some cases 4 tiers within the data center, and then they're connected through external gateways to yet other data centers in the same metro to build these, metro redundant kind of aggregated data centers. And the same picture at Facebook, they showed in a different way, but these 3 dimensions are essentially the 3 tiers of a leaf-spine network. These things are being upgraded, in speed. So there's a steady march from 10 gigabit 10 years ago to 40 gigabit 5 years ago, 100 gigabit 3 years ago, and now emerging 400 gigabit. Incredible amount of ports going into this, about 15 million 100 gig ports this year, primarily going into the cloud. 400 gig is just entering the market. The projected volume for the next 4 years is 20 million ports. And these, of course, are 4 times the speed of the 100 gig port each. So this is the same sort of port transition in graphics here. 40 gig is still around, but declining. 100 gig took over very quickly, partially because the 100 gig price point was parity with 40 gig. So there was no economic reason to buy a 40 gig port when 100 gig became available. The 400 gig, which is starting to ship now, is about twice the cost per port of 100 gig. So it is more, it's cheaper on a cost per bit basis, but the optics are still fairly expensive. So it will take a little longer to ramp, but nevertheless, because it's 4 times the speed of a 100 gig port, it's projected to cross over the 100 gig shipment bandwidth by the end of actually this is funny showing it, by the end of 21, not 2020 here. And again, the majority of these 400 gig ports are expected to go into cloud. So the whole thing about these Ethernet speed transitions has been both, there was a demand side, people wanted, of course, more bandwidth, but it also was driven by reducing the cost of these Ethernet ports. And what's happening there in the cloud, I'm not sure you remember this, the concept of learning curves where new technology comes out at a stratospheric price point, and then it takes years and years to get cheaper until people can actually deploy it. Well, that does not work in the cloud. In the cloud, nobody would buy a new technology that's more expensive than an existing technology. So for 400 gig to get any traction, it has to be cheaper, at least per bit, than the technology it will substitute, which is 100 gig. And of course, the cheaper it is, the faster the substitution happens. And if you don't get to volume, the old investment people making the silicon is not going to pay off. In the case of the 40 to 100 gig transition, the transition took about a year to the 50th percentile point, meaning in less than a year, the demand switched in the market from 40 to 100. The 400 gig ramp is a little slower. This is the latest forecast from Delora, which tracks this market. But it's still projected to go up very significantly starting later this year and the next many years. Now let me go down to the silicon a bit. You know all about Moore's Law. This has been going on, of course, for the last 40 or more years, actually 50 years almost. This has translated on the network silicon level, the network switches, to a tremendous improvement. Every other year, these switches doubled in speed, essentially the same cost, which is a remarkable achievement. Now, part of this was that the network silicon was lagging in terms of process technology compared to CPUs and GPUs by a long shot. All the chips that were shipping until the latest generation that just got launched were actually 28 nanometer technology, something Intel shipped in 2011. The new chips coming out at 16, this is something Intel shipped in 2015. And it's only the generation after the current one, which is coming out next calendar year, which is at 7 nanometer, which sort of matches current CPU processes. Now, the advantage of that was the improvements were much more rapid. So in other words, as the technology shrank from 28, 16, and going on to 7 and 5, the number of transistors per chip, the number of buffers, table sizes on radically improved. So the net of this is that the new chips coming out are always better than the previous chip because they have more of the stuff that people want in a network. And of course, most importantly, they deliver more cost performance. And this has resulted in this dramatic, sort of cost reduction and size reduction where the biggest switch that I was involved in 12 years ago called the Magnum switch, which was a double wide rack with 3,456 ports at 16 gigabits each, 55 terabit capacity, is, as of this year, 2 1U boxes. So it's a very dramatic shift. Now, the negative of this is that the design costs for the silicon have gone through the roof. This is some estimates for Intel CPUs type chips. Networking chips actually cheaper to design because a lot of cut and paste, like step and repeat. It's the same kind of structure repeated multiple times. Nevertheless, the tape-out cost in 7 nanometers, $10 million just for the mask set. Your CAD tool is going to run another at least $10 million a year. So by the time you have a team on this and get a chip out, you're looking at $50 million and counting, and it's probably going to be double of that in 5. And this only really works in volume, and the issue with that is you need, the industry isn't actually that large. So the combination of advanced IP, the demands driving to 7 and 5 nanometer transits to merchant silicon, which kind of has taken over the market. Most of the bandwidth shipping today is merchant silicon chips, primarily from Broadcom. There's also some other vendors. But the reason for that is that every year there was a chip following that Moore's law curve that doubled the speed or added more buffers or more routing and so on. And in terms of time to market, this just took over the market. Now there was this other element, which is the underlying SerDes speed, or the speed of the electrical lanes coming out of these chips. Until the current generation, everything was at 25 gigabits. So 100 gig Ethernet is actually 4 by 25. The new chips are at 50 gig SerDes, so 100 gig Ethernet is now 2 by 50, and a 400 gig Ethernet is 8 by 50. The next version of chips coming out next year will actually go to 100 gig SerDes, where 100 gig Ethernet is just 1 lane, and a 400 gig Ethernet is 4 lanes, and you could actually build an 800 gig Ethernet in 8 lanes. Now, this has been key, of course, to get more throughput per chip because you're limited by I/O. It's also creating interesting dislocations in the market. So in terms of the projection on bandwidth, the 100 gig SerDes, which will show up shipping in any volume next calendar year, is actually now projected to be larger in terms of bandwidth by 22 than the entire market is this year. So the expectation is this will get adopted very, very rapidly. And the reason for that, of course, is it's cheaper. You get, with half the lanes per port, you get the same bandwidth. You can double the density per chip. You can double the throughput per chip. You can double the density per system, and so on. So we're in the midst of this transition, which it is a little hard to go. It's hard to go faster than 100 gigabit. People looking at 200 gig or 224 gig SerDes, but the physical reach on PC boards gets very, very short. So 100 gig will be around for a long time, and the issue with that is that you want to match the optics that connect to these electrical lanes in terms of the speed. The latest generation of optics is called 100 gig lambda optics, which is a direct match. Everything else requires gearboxes. So to explain that, the current optics, which are 4 by 25 matching the 25 gig speed, are still the highest in volume. In fact, the entire market is essentially these 100 gig CLM4, 100 gig PSM4 optics. But going forward, 100 gig single laser optics, which is 100 gig DR, will be cheaper, and of course 400 gig DR4, FR4, LR4, all based on 100 gig lambda as well. So the good optics on this chart are the green ones. There's not too many 50 gig optics out there, so the current model of prediction is that there will be a massive transition from 25 gig lambda optics shown in green to the 100 gig optics shown in orange. And this sort of matches the form factors you're familiar with. There are, of course, ideas to take even an SFP module and run that at 100 gigabit. So you're not limited. SFP doesn't have to stay at 25 gig. It could go at 50 gig or eventually 100 gig. And the QSFP, which is 4 lanes, could go to 400 gig with 4 lanes of 100 gig. And the OSFP, which is an 8-lane module, will go to 800 gigs. So again, the majority of optics standards today are all based on 25 gig NRZ. The only one in the 100 gig era that's 100 gig lambda is 100 gig DR. In the 400 gig space, it's DR4, FR4, LR4, and in the 800 gig space, which hasn't been quite announced yet, but it's coming shortly, it's things like SR8, DR8, dual FR4, and FR8. There is talk about working on 800 gig Ethernet. In fact, some industry consortium is about to kick off to make that happen. It's actually very easy to make 800 gig Ethernet happen, which is you take the 400 gig spec and you change one number, which is the speed per lane. So this is one of the easiest standards to come to fruition. We hope to see this in silicon in a few years, but obviously there has to be a multi-vendor standard around it. It is harder to go faster. Part of that is that at 800 gig, the minimum packet size is 666 picosecond, which is 1.5 gigahertz. The internal clock rate on these chips tends to be 1.5 gigahertz. So with one pipeline, you can handle 800 gig. But if you wanted to go to 1600 gigabit Ethernet, you needed actually 2 parallel pipes, which means you don't get scalability at the silicon level in terms of cost. And the radix becomes too small as well. So the bottom line of all this SerDes and optical stuff is, 100 gig will be around for a long time. And anything else requires, gearboxes, either forward gearboxes or inverse gearboxes, which add significant cost and power. Now, switching over to the CPU and the PCI and the NIC side, PCI seems a little slow compared to what we just talked about. Almost all of PCI is still 3.0. The first CPUs with 4.0, of course, are announced and in fact shipping. But it came so late that a lot of people think that PCI 5.0 is around the corner. This is much needed both to drive faster I/O, to connect to more flash, and of course to have faster network interfaces. Dedicated GPU and specialized AI chips have even more need for I/O. So people there are looking at many times the throughput per chip than a conventional CPU. So they need even more I/O. And the sum of this is that we expect rapid adoption of 100 gig NICs for both conventional servers and for these AI GPU servers this year and next year. And just to showcase how where PCI has been, PCI 3.0 was actually launched officially in 2010, although I think the first systems shipped in 2011. That was 10 years ago, 8 gigabits per lane, 4.0 double stat, and 5.0 of course double stat again. But the key point here is with a conventional 8x adapter, today in PCI Gen 3 LAN, you were limited to essentially a dual 25 gig NIC, which is the industry standard for large cloud. With the 4.0, you can actually do a dual 50 gig or single channel 100 gig NIC. And with the 5.0, in 8 lanes, you can do a dual 100 gig. Or you could do 16 by PCI Gen 4 to do a dual 100 gig as well. So dual 100 gig is totally practical, or I should say economically justified going forward, because the underlying silicon cost isn't really any different than a dual 50 gig NIC. You just run the state machines a little faster. And if you look at this from the sort of rack level, top of rack level efficiency, the previous sort of top of rack chip that's still the highest volume today called Tomahawk 1, which is a 3.2 terabit chip with 128 lanes of 25 gig. Typically there's a 3-to-1 oversubscription going on to the rack level, which means you take 800 gig lanes going up, and you have the equivalent of 2400 gig lanes or 96 25 gig lanes going down, or it could be 48 50 gig connections to 48 servers in the rack. In other words, even today, in the last generation of silicon, you can connect every one of 48 servers on the rack with 50 gig, and there wouldn't be any point to go any less because you're just wasting your money. You're straining the bandwidth. The new chip that's shipping now called Tomahawk 3 has 4 times the bandwidth. So you can actually do 8 by 400 gig going up, and the equivalent of either 190 to 50 gig or 9600 gig servers going down. So the ability to interconnect a large number of servers at very high speed at very low cost is a given. And people typically use copper cable for these downlinks I should mention, because it's the lowest cost. So we do expect people to upgrade from 25 gig and 50 gig today to 100 gig going forward. Now let me go back to the real topic that I wanted to talk about, which is how this matches to scalable distributed storage. So I mentioned earlier that the whole notion of disaggregating data placement from the application is absolutely key in the cloud, because you just don't know which thing scales and how much storage it needs and where all this data is. So the way to think about this is that the spine tier, the top tier of these networks, is essentially your total throughput of the whole data center, and this for a large data center can be in the petabit range. In fact, can be multiple petabits. And then all these servers underneath, which could be 10,000, 100,000 servers, connect through these spines to any other server in a few microseconds. I mean, the exact number sort of depends how many layers you have, but it's perfectly fine for flash. So the point is, with the right storage architecture, you can actually disaggregate the applications from the storage completely. And quite frankly, this was always the goal. So this was, in the cloud, this was the goal for the last 10 years, because it does result in much better application availability, scalability, reliability. And the real question was how to do this without compromise, meaning data was getting bigger all the time, and there was a number of protocols, and there are a number of protocols in production that are doing this. So this is now getting to the more controversial part of this talk. So the largest installed base of this is arguably RoCE or RDMA over Converged Ethernet. There have been two versions of RoCE, as you may know, the priority flow control, which relied on the network guaranteeing no packet drop to achieve good performance. The issue with packet drop is that a single packet drop requires you to redo an 8 megabyte transfer, and your performance goes pretty quickly to hell if you get any number of packet drops. Unfortunately, PFC doesn't really scale well into larger networks, so these applications that deploy PFC RoCE are limited to what we call cluster size, not entire data center size. They are in production. In fact, we provide the network for the vast majority of these, but it took a lot of fine-tuning to get this working. Now the proponent of RoCE, which is primarily Mellanox, has a new version which uses early congestion notification to avoid the need for priority flow control. This is not yet in wide production, so I would say the jury's still out how well this scale, but obviously it would be preferable not to require PFC. And I should mention both of these now work over layer 3 technology. A very early version of RoCE did only work on a layer 2 network. Now the new kid on the block is NVMe Express over TCP/IP, which became a standard, I believe, a year ago, advocated by a company that's actually delivering a product here. Advantage of TCP/IP, of course, is it works beautifully on any SAS network. There's a reliable transport layer that guarantees that the packets arrive in order on the other side, and things get retransmitted if they drop in between. So we do believe this will be very robust and will be very easy to deploy. There is, of course, the overhead of driving the TCP protocol, which is primarily burdened on the server or the SmartNIC that implements this protocol on both sides of the equation. And people are looking at hardware implementations or highly dedicated, state machine kind of things to optimize the performance there. And then there are some other people in production that couldn't wait or didn't need to wait for the official NVMe Express over TCP standard that simply did their own version of a block storage protocol, which works in volume today in actually very large scale, but it's not published or standardized from that perspective. Now, the experience so far on all of this is that it does scale. The clusters with RoCE go to the thousands of nodes, and it's also clear that storage servers can saturate 100 gig links today. So this is with current technology. This could easily go up a factor of 2 or 4 in the future. A conventional server in these pictures can saturate at least 50 gig interfaces. So these are all sort of publicly reported numbers. And if they added more ports, they can probably get to 100 gig there as well. So getting 100 gigabit in and out of a server, current generation, seems quite feasible. What has also been emerged is that you don't want to run this anywhere close to maximum network utilization because both the latency and the congestions go up and packets drop. So the general advice is to keep network utilization below 50%, and this is the well-known sort of trade-off between latency and throughput, except in a network it's even worse than this theoretical curve. This is a queuing model because, again, the overhead of packet retransmission is very, very significant. Now, this can all be simulated. So there's work by a gentleman called Ariel Hendel and I think it's Lady Pallavi Shurpali at Facebook, which have built a NS3, which is an open source simulator for an entire data center network with, I think it was many hundreds of nodes, maybe thousands of nodes, multi-stage network, a queuing model for the NVMe Express, the storage layer, and so on. And what came out of the simulation is that, number one, the simulation results reasonably closely matched reality, which is a good thing. So what this means is one can experiment in the simulation model with settings on the exact protocol, data center TCP versus regular TCP and so on. But the main surprise to me was that just by making the network interfaces go faster, so you can in software dial in the speed of these interfaces, everything improved. So they actually dialed these things up, which they didn't have the hardware for, to a 200 gig Ethernet connection per server and on every link on the network. Even though the servers couldn't even nearly saturate this, but the overall performance improved, and the argument was you're sort of moving the knee of the curve on this latency chart to the right, which means, of course, that the network does perform better. So the long and short of this is, disaggregated storage, either the Rocky style or the NVMe Express over TCP style, works today at scale in large cloud networks. It did take a lot of tuning to get there, but it works. I think there's general agreement that TCP/IP or variants, like data center TCP, are by far the most robust transport layer. Although it's back to the performance equation, implementing that in either dedicated smart NICs or state machines. And the promise of disaggregated storage that's robust and easy to use, meaning that anybody, mere mortals, could use this, is definitely here in the near future, meaning these same technologies will allow anyone to build an extremely arbitrarily scalable, distributed, disaggregated storage system on the network at whatever scale. And I was going a little fast here, but that was my slides. Thank you for my attention. If there's any questions I can answer, we have, I think, a couple of minutes. There's one, and you next.
Andy, many people have suggested that going to a two-tier network with central data centers and edge networks can alleviate some of these problems. And I think in the past you've been pretty skeptical of that. I'm wondering if you have changed your opinion.
Two layers, you mean like a leaf spine? Or?
Yeah.
Yeah, I mean, leaf spine, with the switches getting bigger, can support a tremendous number of servers, by the way. So, I mean, this picture is a simplified version, but with currently available equipment, you can, if I remember this correctly, you can go up to like 70,000 servers with just a leaf spine. So what is true is that the more layers you have, the more problems you tend to have. And one thing I forgot to mention on the simulation results is that one particular problem is downspeed conversion. So if the leaf spine runs at, say, 100 gigabit or going forward 400 gig, whereas the server connection is only 25 gig, and that top of rack switch doesn't have a lot of buffering, you tend to end up with a lot of packet drops at that very point, because that's where the traffic sort of comes to a screeching halt before it trickles down in the server. And I think one reason that a network where all the links go 100 gig or faster works better is you have few of these speed conversion issues. So what is true here is that one should over-provision the network, and I'm not saying this in a self-serving way here, but it just works better, and you will have much fewer problems. And there was a question here.
Yes, it was a little fast, but just want to make sure I understand a basic concept. I think you said is that the device structures are sort of limited to support maybe 100 gigabit switching, and if you want to get to higher speeds, you have to do aggregation, and then the extra performance is basically a matter of the architecture over appropriate over provisioning and things of that sort. Is that generally correct?
Yeah, meaning, the real question on the edge is how fast does the TCP, is it multi-threaded? Do you have a smart NIC? The RDMA, of course, goes faster than the TCP version. And do you have multiple NICs? I mean, people are doing all kinds of stuff to get the performance up. But what is being deployed today in high volume is a dual by 25 gig NIC. And people have gotten 25 to 50 gig out of these things. And typically, these servers, I should have mentioned earlier, have a whole bunch of M2 flash memory sticks, maybe 4, maybe 8. Each one of these M2 devices can do like 2 gigabytes each. So there's plenty of capacity in terms of I/O inside the box in terms of the direct PCI interface that you could output easily 100 gigabits if the network stack provides that. So this is sort of the current match is, fill up the box with flash sticks or flash devices and then connect it to the network. And then the storage and the cloud is distributed across all of these boxes, because obviously it's arbitrary large data. And the only place to put it is sort of all over, which also allows you the redundancy by the time you do the M+1 sort of replication. There's some more questions in the back, and there's one there. So yes, it's if the service would be faster, people would go faster, but it's limited by the throughput you can achieve on the server level.
Do you foresee some of these upcoming interfaces like CXL, Gen Z, impacting the networking architecture, and if so, how?
Yeah, that's a very good question. So there are, you always have to start with the application, right? So there are applications that will work much better, in a large CXL, ultimate DRAM, I don't know how many terabytes of memory environment, like some database thing, where you have very tightly coupled, interactions. What I was talking about is the conventional cloud, search social environment, and the conventional enterprise as a service going into the cloud, where you take existing applications and just move them from on-premise into the cloud without changing the application model. But there's a whole separate opportunity how to take advantage of all this great new stuff coming in with persistent memory in the same huge box, could be a rack full of memory. And that may completely change what you can do there, but it's not going to change what Google and Facebook is doing in the cloud right now.
Sats here from VMware. My question is twofold. One is, you mentioned about when you move from 100 gig to 200 gig NIC, you see the improvement in performance. Can you quantify how would you do that? Like what kind of performance improvement you see it? And second part is, as we move from 100 gig to 200 gig on the NICs, on the servers, do you see a need for the NUMA-aware networking inside the servers? Thank you.
NUMA-aware networking, you mean like coherent? In NUMA, what do you mean by NUMA-aware within the network? So.
Basically talking about,
The current trend is actually to fewer sockets for the simple reason that even going from one socket to two socket currently doesn't scale that well, as you may know. So people are filling up these CPUs with memory buses to get more memory bandwidth, and there just isn't enough, pins left over to drive another socket at the same speed, right? So I would say, 64 core chips, where it may be multiple sockets in one device, but not sort of externally to get more interconnectivity is the future. It just gets a little hard to cool at some point. But going back to the networking speed, it's basically an economic trade-off, right? So you do pay by bandwidth, so higher bandwidth costs money, but you also gain a certain amount of performance. So what everybody in the cloud has been trying to figure out is what's the optimal spend, between the storage and the servers, the compute, which is the much, much bigger portion of their spending, compared to the network, which is a much smaller slice. You don't want to spend too little on the network because you would bottleneck the servers, but you also don't want to spend too much where it doesn't really improve the performance of the server. So until now, that trade-off was at the 25, 50 gig level per server, and typically 3-to-1 oversubscribed at the TOR, because you don't have all the servers being active at the same time and going into the storage, right? So that's just the universally accepted sort of design point today. But as CPUs will double in cores, the throughput will double. As the flash goes faster, the I/O goes faster. So it tracks the underlying technology in terms of both CPU cores and flash in predictably upping that speed. And I think I'll have to leave it at that. Thank you very much.
All right, everybody give Andy a big hand. All right, if you're going to different meetings in the symposium, this is your time to get out. Luckily we have about 5 minutes. There's no coffee out there, so if you're staying for the PM Summit, just stay in here. But we do need a couple of minutes for the clicker to cool down, because that was a pretty fast slide progression. But while we're doing that, I will introduce the next speaker, who will be up here in a minute. So tell you what, I'll give it a minute while everybody clears out, and then I'll come back with Andy. Get ready to go again. So Andy, why don't you come on up? So I would next like to introduce Andy Rudolph. He's going to be talking about the persistent memory programming model. I've known Andy. Okay. I've known Andy for a little bit in past life, but really it's been a pleasure to work with him this last year on the hackathon program. We've invented lots of new terms. Conservation of Andy Rudolph, let's not use him too much, he needs to actually go do work, as well as who wants to be Andy Rudolph whenever I do a programming challenge. So Andy's going to be here to talk about the programming model. I will bring him up. Welcome, Andy Rudolph.
Okay, thanks very much. Well, that sounds a little loud. I think I'm okay. So I am Andy Rudolph. I'm from Intel. Is that mic like really booming? Yes. Thanks very much. It's good. Oh, yeah, okay. But actually here, I'm not really here as an Intel employee. Boy, that really sounds loud to me. You think I should move this? Maybe that's a little better. Is that less booming? Instead, I'm really here as one of the founding members of the SNIA Non-Volatile Memory Programming Technical Work Group, or TWIG. That red line doesn't mean that I've been let go from Intel yet, but I just wanted to kind of make it clear that I wear two hats, and really I'm here with the SNIA hat on, and not so much the Intel hat on, although I couldn't help but to wear one of these little miniature Intel DC Optane modules on my shirt, but other than that, yeah. So every year we do this. This is actually the 8th summit, because we had 7 so far, and this is number 8. And every year I come up here and I talk about what the TWIG is doing. And I thought for people who are here for the first time, I'll give a little bit of the backstory. If you've been here before, you'll recognize. But I went through all of my previous talks from the past 7 years, which, believe it or not, were still sitting on my laptop, though I need to organize my files a little better. And I pulled out what I thought was the key message each year, and you can see how it evolves. But first of all, just Jim touched on this, but the very rapid history here. In June of 2012, we started the TWIG. It was actually a small number of people from Intel and from HP got together and came to SNIA and said, we need to do a standard, a unified programming model. It was an immediate popular TWIG. Microsoft was there from day one. Red Hat was there from day one. VMware was there from day one. And a bunch of other companies. It's about 50 companies still are members of the TWIG. By December of 2013, we published the first spec, the 1.0 programming model spec. And then a couple years later in March, we published the 1.1. A couple years later, we published the 1.2 spec. So it's had a kind of a cadence going along there. So right in between there, in January of 2013, we had the first summit. We called it the NVM Summit back then. Now we call it the Persistent Memory Summit, and you'll see why. And so I started with that 2013 summit, and I ripped one of the slides out of my deck. And the details aren't that important, but the slide basically shows that we were talking about being able to use NVM as standard block devices, but also it says in the middle there, NVM regions exposed as files. That was sort of already what we had in our minds. And then on the right, we were going to propose a new non-volatile memory API, a new asynchronous API, which you can kind of see over on the right-hand side. I drew in that same year some flows. And you can see in the middle here, there is a flow that talks about memory mapping files. So that was, again, already in our mind. And then there were these new NVM underscore routines that I'm happy to say died off and never happened. So one less API in the world. Thank you very much. By 2014, we had published the first spec, and so I started explaining what was in the spec during this slot in the summit. And I started out by talking about what we called PM.volume, which was an in-kernel way of getting to persistent memory. And then on top of that, pm.file, which was the application way. Now, this is going to start to look pretty familiar if you've had any experience with our programming model, because you can see the application there going around the file system and just using the mappings that are set up in the MMU. That was really one of the key ideas of our programming model, and that's the picture from that spec at the time. By 2015, I had taken that picture and revised it into the one that I have been using now for 5 years, where I took the management path on the left and made sure that that's kind of a first-class citizen, because it turns out to be pretty important. You can see the legacy path in the middle, the block path, and then on the right, our new persistent memory aware file system path. 2015 was kind of a big year because we had really solidified some of these ideas. We were starting to get traction with the operating systems. And since I am an Intel employee, in that same talk in 2015, I started talking about the instructions that you use that we've added to the processor for persistent memory. At least we've added it to the Intel processor. And you can see there are a few instructions up there for flushing stores out of the CPU caches. And then there's this second level of an instruction there called pcommit, which I'm kind of happy to say that a group of us, both within Intel and also a lot of Intel customers, thought long and hard about whether we really wanted to introduce this two levels of flushing, and we were able to kill pcommit before it actually ever shipped. Thank you very much. And actually, my partner in crime in killing it is actually sitting here in the second row. It was one of the funnest things I think I've ever done at a company, is to remove an instruction from a processor. So that was quite the experience. And also in 2015, we started talking about how to make persistent memory programming easier. And with that, we started coming up with libraries. This is the first, I think, presentation I did about the persistent memory libraries, which is now called PMDK. You're going to hear more about PMDK later today in a talk from the PMDK architect, so I won't go into too much detail right now. In 2016, we started focusing on all the traction we were getting in the operating systems, and so I just ripped a few of these slides out of the presentations. Neil Christensen from Microsoft came and talked about how Windows supports the programming model. We had Jeff Moyer from Red Hat talking about how Linux supports the programming model. Tom Talpe from Microsoft came up and talked about remote persistent memory, which we really started getting serious about. How could you do RDMA to persistent memory? What changes do we need in RDMA, and so on. And Tom's really been continuing to drive that in the years since this. Just due to scheduling and logistics and who was ready to talk about it, you'll see the Windows and the Linux in that year, 2016, but not VMware. VMware, we did have them front and center in the next year, 2017, where Rajesh from VMware came and gave a great talk about it. And actually, the talk right after mine, you're going to hear Rich talk about VMware's support for persistent memory even more. So that's pretty good stuff. And then also in 2017, I did my thing where I came up and said, what is the twig working on? And at the time, we were working on things like details around flushing. What are all the different types of flushing that you can do, and refining the error model and a few other things. And the flushing got kind of complicated when we talked about all these different ways of flushing things. There's the standard API like msync or flush file buffers on Windows. But there are these things that we called optimized flush, and there's kind of an interesting little thing in the middle, hidden in the middle of this slide, which most people aren't aware of these days, but this was only 2017, right? This is just a few years ago. It wasn't safe. The Linux community did not consider it safe for us to flush things to persistence from user space. So we had added those instructions, and we were all proud of these instructions. Look, we have this very optimized way of flushing things to persistence. And the Linux community said, no, we need the control point of you calling into the file system. And so I have this slide here that says on optimized flush on Linux is unsafe. You can't use it. And back then, our libraries in PMDK, we turned it off and we switched it back to calling msync, and they slowed down like 7x on some benchmarks. And when we said we weren't gonna ship incorrect libraries, we're gonna keep them correct. We weren't gonna change this until there was a way of doing a safe flush. So stay tuned on that. On Windows it was safe, but not on Linux. That was a pretty interesting piece of our history. And then we also started talking about how to flush something on remote persistent memory, and that's the RDMA work with Tom Talpe that I mentioned earlier. Spec also mentions something called deep flush, which is a way of flushing to the smallest possible failure domain, and that's also has been available in shipping for some time, but also kind of a complexity that a lot of people don't understand. So I started giving more talks about that. In 2018, when I talked about what was going on in the twig, it was more peripheral related things, right? Like security, we had published a position paper on the persistent memory hardware security threat model. We were getting a lot more into the details of remote persistent memory and talking about other things like higher level semantics. And then last year, I went back to the slide because I realized we kept talking about these kind of gory little details, but it was important for everybody to realize that the persistent memory programming model was actually designed to be fairly simple. It is built off of the storage APIs, and that was kind of the highlight of my message last year. If you use the path in the middle there, you're just using persistent memory like an SSD. Nobody modified your file system, nobody modified your program, it just worked. It just seems like a really fast SSD. If you use the path on the right, you're just using persistent memory like an SSD with no page cache because it's got direct access. And it's not until you actually decide to use that optimized flush that I mentioned earlier that you're even using a new API. Until then, you're really just using APIs that have been around for decades. So that was a very strong message I wanted to give last year to remind everybody that the storage APIs are there and they work. So today, we're really just focused on the right-hand side of the diagram. The operating systems have named that DAX for direct access. And this will be the focus of most of the talks that you hear today, will be some way of using DAX or using this programming model. So it's a relatively straightforward programming model, we think. So where has that worked? In the past 8 years or so, where has that model actually worked out for us? Well, I would say things that build on the model have worked out pretty well, including our libraries like PMDK. We haven't had to, while building these libraries, we haven't had to go back and say, gosh, I wish this model were different. In fact, it's actually worked really well for building PMDK. PMDK is a suite of libraries. Like I say, you'll hear more about it later, and I'm not going to go into them, but they're up to about 10 libraries right now, and you pull in just what you need. But it is worth mentioning that back when I first started talking about PMDK, we had the idea in the lower left there of the volatile use of persistent memory, right? So it is persistent, but you don't happen to care that it's persistent. You're just using it because it's big. It's high capacity. The product that I have pinned to my shirt here is 3 terabytes per socket. And so it's pretty high capacity. And it's cheaper than DRAM, so maybe one of the use cases is just to store stuff there, but not worry about it being persistent. And that's turned out to be kind of wildly popular. It's one of our most popular ways of using persistent memory. And so on the left, you can see there are a couple of these libraries that one of them actually just designed over the past year that have made quite a bit of traction in the ecosystem. So this last year then, in my summary of this last year, it's been a very exciting year. Intel did actually launch their persistent memory product. You can tell, okay, now it kind of shows that I work for Intel because I wrote, Intel launches Optane DC persistent memory instead of Intel finally launches Optane DC persistent memory, which I believe you'll probably see on some other slides. And you can also tell I'm not in marketing because I forgot the little R with a circle around it. But basically, this was a pretty exciting thing for me, being an Intel employee and working on this project for a good 8 years. It's really been great to see it actually launched and shipping in the wild. But it's been an exciting year for me too, because a lot of the companies over the past few years, I came up here and I told you, I just saw this great demo of somebody showing that they could use persistent memory. You know, a lot of these big companies that I've been working with have now moved beyond the demo stage to the stage where they're shipping products that claim to fully support persistent memory in one way or another. There are quite a number of these right now. I'm not naming them here, but a lot of them will be, some of them anyway, will be giving talks today. So that's pretty interesting too, I think. And the number of use cases, different ways for people to figure out how to use it, and the number of ways they've decided to do software enabling have really exploded. It's actually pretty incredible. Again, you're going to hear about a lot of it today. It includes things like new people coming up with ways of using it, or even building startup companies around new ideas, ways of using persistent memory. So I think that's pretty exciting. When I started on this project about 8 years ago, I looked into academia, and I looked for papers on persistent memory programming, and there were 2 notable papers that were even not that new. They had been around for a few years, and they were done as, I think, as master's thesis papers. But now I've lost count. Every year we get so many of these academic publications. It's amazing. It has really exploded. If you go to the non-volatile memory workshop at UCSD, a lot of the talks there are now about persistent memory. We've got a new conference that we did last summer in San Diego called PIRL, P-I-R-L, which is persistent programming in real life. And it was a fantastic conference. It was one of the best I've been to. And so that was pretty exciting. But it was both people talking, not just from the academic sense, but also some of their real life experiences in implementing some of these things. So it's been a pretty exciting year, I'd say, for persistent memory in 2019. So that all sounded really good, motherhood, apple pie, but you know, the model wasn't perfect, even though I tried to keep it simple and straightforward. There are always places where you can criticize what happened, and I think that's important for us to do. So where did the model fall short? So first of all, if you think back around this file system that's at the center of our model, this persistent memory aware file system. On Linux, the 2 file systems that are persistent memory aware are ext4 and XFS. At least these are the 2 that are upstream in Linux. And on Windows, it's currently NTFS that supports DAX. There are others, but they're either private or experimental, not upstream. So I'm not listing them here right now. These are the ones that are available to the general public. And so, like I said, we had this little hiccup where the Linux guys said, whoa, not so fast. I don't think we can just give you that flushing capability from user space and make it safe. And we negotiated for over a year between the Linux community, different people in the Linux community, and came up with this solution called MapSync, which is now something that the model never mentioned something like this. And we did go ahead and roll that into the next spec. We said, well, you may have to request information to use the optimized flush. And so that actually did make it into the spec. But what about an uncorrectable? So this stuff is like memory. It sits on the memory bus. You can have an uncorrectable error, right? They're rare, thank goodness, but they do happen, and you have to be able to code for them. So if an uncorrectable error happens where I've shown it in the data that the application has mapped, it's up to the application to deal with it. The application can say, I can't use this data anymore, and go get it from a backup tape. Or the application can say, oh, I've got redundant information, and I'm going to go ahead and repair the uncorrectable. But what if the uncorrectable happens down in the metadata of the file system? Usually that kind of metadata is protected by things like software RAID. But we don't have software RAID because there's no block stack anymore, right? We're just accessing the media directly. So this to me was sort of a failing of the programming model. And I went to the Nova guys, these guys who did a research file system at UCSD, and I explained this problem to them, and I said, you know, we'd really like to see replicated metadata. And you know, these are like grad students, right? They didn't know this would be hard, so they just went ahead and implemented it. It's actually pretty cool, but it's Nova. It's not an upstream production quality file system currently, but it's you know, something to be watching. And I've also discovered other ways of sort of solving this problem, like by taking XFS, where you can separate the metadata onto a different device, and you can RAID that device. But it's kind of complicated to set up. So it's sort of a failing of the model. Similarly, the Linux guys also came up with this other thing that you see on the far right of this diagram called device DAX. Device DAX is not the SNIA programming model. It doesn't use a file system. It is very powerful. It's a kind of a raw access to persistent memory. People use it because it supports RDMA better than the file system DAX currently on Linux. But it is a little infuriating to use. It doesn't follow POSIX. If you open up device DAX, first of all, you have to be root. If you open it up, you can't find out what the size of your persistent memory is. Stat doesn't work. You have to use some special magic functions that we've put into PMDK to figure that out. If you write some changes to device DAX, msync doesn't work, right? You can't flush the changes using the normal way. So things like this are complicated. And we've tried to take away a lot of the complications. You can see PMDK is in this diagram, and it knows how to use device DACs, and it abstracts away those details. But the whole fact that the Linux guys even had to create this, I think, shows a failing of our model, that we didn't foresee the need here. So that's something, again, I'd like to see us go back and re-examine and decide if the programming model is missing something because of that. So ongoing work, given all that, what are we doing in the programming twig? Well, first of all, the NVM programming twig was originally created to do all things non-volatile memory. So we were talking about disk interfaces, SSD interfaces, and stuff like that. After that first spec, we've done nothing but talk about persistent memory. So maybe we should even be calling ourselves the persistent memory programming twig at some point. We do continue to meet. Instead of it being every week, it's more about every month now. We do continue to meet face-to-face about every quarter. The chair of the twig was sitting here a minute ago, but he moved somewhere else. Where did Alan go? Oh, okay. So he went to go get ready for the next twig meeting. And, but we still have a lot of heavy discussion, a lot of interest in the remote persistent memory. Actually, the changes to RDMA are really coming along nicely, and how those work and how those will be used are one of the things we're describing. There's still quite a big interest in resyncing with the stuff that happened in the ecosystem that I mentioned, where it didn't have anything reflected in the programming model. So we're talking about doing a 2.0 programming model spec. Actually, at the meeting yesterday, we got quite a bit done in just sort of reorganizing the spec and getting it ready for that 2.0 publication. So that's coming. In the meantime, inside of Intel, a bunch of us got together, driven by my coworker, Steve Scargill, and we took all the persistent memory programming things that we had been writing and talking about for the past few years and put together a book. The book is you can get to it, it's free. If you download it and read it online, it's free. Or if you want the printed copy, you can pay for the printing costs, which are fairly minimal. But the book itself, I think, has turned out really great. So I just wanted to make sure people were aware of that. There's a little thing you can take a picture of with your phone and follow the link. It just gets you to the PDF download or a place where you can order it. So that's not particularly done by the twig, but it's definitely a lot of the same information that the twig has been working on over the years, and then that we've been working on in persistent memory programming, kind of culminating in a book. So for the 8th time, there is your summary of what's been going on in the NVM programming twig. Any questions about the twig or anything I can answer in that area? Good.
All right, excellent.
Thank you.
Rich Brunner from VMware. He's the principal engineer and CTO of the server platforms for VMware. I will say I've known Rich that's okay, you're good, come on up. I've known Rich See, I let him get past the speaker. I've known Rich in a previous life. I used to present to him quite a bit, and he was actually very nice to me. He would ask me a couple of questions that I knew. Then he would ask me a few questions that I didn't know, but he would still humor me and keep asking questions. So he was always very good. And so, Rich, glad to have you. Glad to see you again. And welcome, Rich Brunner.
Okay, how's that for volume? Hopefully that's okay. Good, excellent. Okay. So, I'm here to talk about VMware's adventure in persistent memory, which we've had the privilege of being on since the end of 2011 with our best buddies, Intel and other companies. I'm going to restrict my remarks to x86 virtualization. So there are other technologies and other solutions, but I'll focus on x86. So we're going to talk a little bit about our experiences so far, and the question, are we ready for persistent memory finally for customers and developers. And then we'll talk about some future expectations. This picture up here, I guess you really can't see it, but I'm a Trekkie, and so this is the original NX01 Enterprise. And the rule here is that after the first 3 tries, the first 3 seasons, they finally got it right on the 4th try, and then they got canceled. But hopefully that's not where persistent memory is going to end up. And if anyone thinks that the first 3 seasons of Enterprise were good, you need to come talk to me, because I don't agree. Okay, so this should be known to everyone here. We're talking about direct mapped, byte addressable, non-volatile memory that can be accessed with load and store instructions. That's what we're talking about. And we're talking about persistent memory that has latency and bandwidth that's close to DRAM, or depending on your technology, a little further out, but hey, it works. And various other things that software and operating systems expect in order to be able to manage it. This is nothing new. We've talked about this for many years. And down here at the bottom are the DIMM-compatible persistent memory technologies, such as NVDIMM-N, Intel Optane DC persistent memory, and in the future there could be NVDIMM-P. And we'll talk a little bit about that. So Andy has already sort of covered the various ways that you can access persistent memory in the native OS environments. So this is more just a reference for you, but the key ones that are very interesting for us at VMware is, first of all, what we call vPMM disk, where basically in the guest, the virtual SCSI device is actually mapped without the guest knowledge to an actual persistent memory device. And that's all set up by the administrator, not by the actual VM itself. Then we have sort of, and you could consider, some people have called this storage over app direct, but this is basically where you're exposing, when you expose a virtual NVDIMM, a virtual persistent device, to an OS, the OS may be aware of it, but the application may still only need to be able to treat it as a memory mapped file, or a block device, and that's where this model comes in. But the exciting one is when you have direct access, and Andy discussed the various mechanisms in Windows and Linux for that. That's where you need new operating systems and new applications, and we finally have those, as you'll see in a moment. Okay, so we've been waiting for this for several years, and it finally happened. So I'm sure you've heard about Intel Optane DC persistent memory. It has fantastic capacity. Probably in the first month, more of these devices sold than in our customer base than any other persistent memory device. So that's pretty cool. It also has probably one of the worst names ever for people that want to stay on the right side of Intel. So I liked Crystal Ridge better. Anyway, so this is the big deal. This has really changed the game for us. And to be honest, it was started in 2012 when Intel realized they had a problem, and they worked through the industry, just like CXL, in bringing in parties who had a common theme, even though there may be competition at other levels. And so that really made the difference, and it's because of the NVM twig and the programming model that we have software that we can actually run on top of our hypervisor. So I sort of go through this list here to just say, are we ready? And this is not an exhaustive list, and if I've left your company out, I apologize, it was not intentional. There's only so much you can do over a weekend. No, just kidding. So first off, the JEDEC, the people that actually define the electrical, the protocol, and the low-level register interfaces for DIMMs, they now have the various standards that are relevant for this generation of NVDIMM and Intel Optane DC persistent memory. And in the future, they will actually get ahead of the game with their specs for persistent memory across DDR5 and the support of NVDIMP. So that is, that's great that we're now finally, the standards committees are a little ahead of the game instead of playing catch up, but that's the way new technology works. We have the SNIA NVM programming model that Andy talked about. We've also had the ACPI non-volatile storage technology group. They've really helped to standardize the firmware interface to persistent memory for operating systems. And a lot of what we did is dependent on that. And UEFI, which represents where the forward-thinking firmware effort is, and if you're not using UEFI, you should be on your servers. They also added a number of important extensions to support persistent memory. From a device point of view, we've now got 3 choices. We have the NVDIMM solutions from HPE and Dell, and there are still cases where customers say, that's all I need. I just need a little bit for tail of log optimization for Microsoft SQL Server 2016. That's great, that's all I need. There are others that are looking at this more whole cloth, and they can benefit from Intel Optane DC persistent memory. So we now finally have a lot of this in place. We have a number of x86 server vendors, and I'll come back to that in a moment. And really important, we now have, as Andy described and as others, native OS support. We have Windows support, we have Linux kernel support, and there are probably other operating systems that I should mention here. But we now, customers now have a choice of what they can deploy natively and in a virtual machine. And then finally, we have the important direct access models. Again, we've already talked about them, and those are really important because what we want to do as a hypervisor is we don't want to get in the way. We don't want to have to intercept these requests, turn around, and emulate them. We want it to be direct mapped into the VM. The VM does loads and stores just like DRAM, and it all works. So I think we're pretty good there. Hypervisors, well, we have VMware vSphere, which is why I'm up here, but we also have solutions for KVM, Hyper-V, and the Zen project. So hypervisors are supporting this also as a first-class citizen. And then lastly, this is probably the key thing. We are now finally seeing enterprise apps that can support it directly, such as SAP HANA, Microsoft SQL Server, a number of other databases. We even have providers such as Phoenix NAP working with a company called Panzera to take their Vision AI Elasticsearch tool, or I should say mechanism, and be able to use persistent memory to speed up the search. We're finally getting there, but I still think we need more applications. I think this is probably one of the biggest obstacles in getting our customers excited is we need more choice in applications that support persistent memory. And so I'm hoping that many of you here represent developers and application software companies, and I hope you are starting to see the advantage of using this technology. So let's talk about servers for a moment. Well, actually, in 2017, we didn't support persistent memory in our product. And so I can say that in 2017, we had 0 certified servers with the technology. Now in 2018, we were actually able to add support for NVDIMM-N, and this was based around the Intel Skylake, and that's another, the official name is another long name, Scalable Processors Facility, blah, blah, blah. Anyway, that launched in July of 2017, and we launched vSphere 6.7 in 2018, and that represents a lot of work by a number of our people, including Rajesh, who Andy mentioned earlier. It was a pretty big deal for us. So what happened is, in that time frame, we had over 26 servers from various OEMs certified to use persistent memory. That's not bad. But when Cascade Lake launched with Intel Optane DC persistent memory in April, that number more than doubled. And so we ended up with 60 vendors who are supporting, who have certified, or I should say 60 servers certified with VMware persistent memory. That number is going to grow. So it's obvious to us that love it or hate it, Intel Optane DC persistent memory has really been a change in the industry and driving interest in our OEMs. So I think that's pretty good. So just reviewing the model briefly is you have a native OS, say a legacy OS that knows how to use, that doesn't know anything about persistent memory, but knows how to use special drivers that can expose it. That's great. In a virtualized environment, we can make that work. And that we can do with a virtualized PMEM as a block device, as I talked about. And that requires no new driver in the guest. So that's great. And of course, we can support VMs running OSs that are much more aware. In fact, we could support VMs of different operating systems with different PMEM technologies, all using a portion of the persistent memory, the logical persistent volume that we're exposing to each of these. So that potentially allows a direct load store model with little OS overhead to the persistent memory in a VM that's running in that environment. It also allows us to bring benefits of vSphere virtualization, which we either have made available now or will be able to do later, such as multiple workloads using PMEM, being able to migrate between servers with different PMEM technologies, live VM migration across servers. We'll be able to do checkpointing, and there are a lot of other things, and there are URLs down there that you can read some of the articles on it. So I think we're there. Another part of using persistent memory is making certain that you can actually deploy applications to take advantage of it. So using, it's one thing to manually move VMs to a host that has persistent memory and has the data that you wish to operate on. It's another thing when you can actually automate it, and we can do that with vCenter and our distributed resource scheduling, so that we can automatically move those VMs and their data sets, persistent memory data sets, onto a particular host. We can also do the opposite, which is really good in the case of data protection and error remediation. You can shut down, you can move the host into a maintenance mode and shut down the VMs, and then you can actually move them off the host. And in the future, it's likely possible that you'll be able to live migrate them as well. So I think we are there. I think as an industry, we have made a lot of progress, and the reaction from customers has been overwhelming. So this is a little boy dipping his toe into the water. It's actually not been overwhelming, but we can do better. So there were great graphics of people dipping their toes, but they were all copyrighted, so I couldn't use them. Okay, so let's talk about data protection. In the near term, we're talking about a scenario where the VM has managed to boot. We in the hypervisor have managed to mount the logical volume, and there were no errors involved in that. The data looked clean. But what happens now if during the running of the VM that's using persistent memory, it runs into problems? So the first one that you can think of is, well, what if there is transient corruption? And so the VM consumes poisoned, corrupted data. What can you do? Well, in the short term right now, what we can do is we can shut down the VM. We have to do that because we don't want it to make forward progress. Assuming there is VMware HA, high availability, installed, we could potentially restart the VM on the same host where the data lives, but of course we would scrub the affected areas where the machine check occurred to see is it safe to start the VM. If it isn't, well then we're not going to start it. There are also a number of other error classes that are relevant that we have worked with ACPI to be able to define, because why today the mediation might be primitive, in the future it can be much more advanced. So for example, ACPI has defined various warning alerts such as maintenance is needed, maybe you're exceeding your endurance, or performance degradation because maybe the device is overheating. That allows us to alert the administrator to schedule maintenance to go take a look at the problem, but not shut down the server right away. Then there's a class of errors where they're a little bit more serious. And I've shortened, these aren't the actual names, I couldn't fit them in the box, but effectively there's write persistence loss that can occur effectively when you attempt to offline or shut down the server. And what that means is that effectively any writes that you've done since the time the server is booted, you are going to lose them when the server shuts down, even normally. So that's a pretty serious thing. Or all data loss means if you shut down the device or shut down the server, the next time you bring that device up or you restart the server, not only will you have lost data that you might have written before, you're not going to be able to potentially read it reliably also. That's a pretty big concern. And then lastly, there is, if a power loss happens now, you're not going to be able to read or write anything the next time you boot, the next time you bring the device online. Those are pretty serious. So today, what we can do, or I should say what we hopefully be able to do in the future, is we can automatically shut down the affected VM, and then we're going to wave our hands at the administrator because they're going to have to take some serious steps. The administrator is going to have to shut down all the VMs. We can auto shut down the affected VMs, but he's going to have to shut down all the VMs to put the machine in maintenance mode. This doesn't require a reboot. And then the administrator will have to make a choice about, do I start migration, moving the data, the persistent memory data set and the VM to someplace else, and you'll have to reboot. Another case is basically you're going to lose write persistency at a power loss. So all the writes that you've done since the time it booted will not be saved. So you'll lose them if a power loss comes by. Or basically write persistency lost now. So all the writes you did before the event are good. All the writes you're going to do afterwards are going to be lost if the system shuts down or loses power. And in that case, in the simplest case, we can just shut down the affected VM and we go through the same flow. What can we do better in the future is in the case where the VM crashes or the VM actually gets a consumed poison, it may be possible to actually reflect that machine check back to the VM and allow the guest operating system to try to deal with that. So rather than shutting it down because we don't think the guest knows how to deal with it, we think that in the future, the operating systems and the application stacks using persistent memory are going to be smart enough to actually deal with this more intelligently. So we don't have to shoot the VM in the head. The other case is mostly the same, but in the case of the write persistency case, this middle box here, we can certainly auto-suspend or shut down, and we could even do potentially a live migration, or at least a cold migration of that VM off the server much faster than an admin who has to jump into maintenance mode to do it. And so this could be a great saver as well. We also have cases where, as we discussed before, where yes, we should suspend or shut down the VM. We have a little bit more time before we have to move it because our data is good at the moment, but new data isn't going to work, which is why we had to shut it down or suspend. And again, you can live migrate it or cold migrate it, and that seems like a pretty good thing. Now, hopefully you're also, in the future, we would expect that there would be a checkpointing or replication solution in the background that will be able to back up PM every so often to some external resource. That's going to be pretty important, because if you don't have that, the last class of error has a very special remediation. And you want to try to avoid that as much as possible. Okay, so one of our experiences has been that server hardware and firmware for PM was a real firestorm between 2017 and 2019. The specs were trying to struggle against hardware schedules. Thanks to Intel, error detection and remediation sort of changed at the last minute. And there were just too many iterations with OEMs, server OEMs, to get this right. We did it, but it was a lot of pain. And the provisioning and encryption is still pretty non-standard. This shouldn't happen in 2020. One, the firmware interfaces are now more mature and stable. And I can say this because there was a public Intel slide. Intel Barlow Pass doesn't seem to screw it up much, so that's good. And OEMs now have experience deploying real solutions, so that's really good. Also, we've been a little bit more defensive. We now have a full PMEM certification kit for OEMs to really test out a number of the error scenarios I showed you on the previous page in order to help us test our code and to make certain that the OEM is doing the right thing. But I will say that these architected firmware interfaces are critical to OS and hypervisors, and we will only certify a PM solution in combination with a platform that supports it. Okay, so I have a choice here between persistence and, I'm going to go with, just assume that there will be more interesting solutions in the future for persistence. And I apologize, I'm not going to be able to hit this in the time I've got left. Well, I could try briefly. So one of the key problems that Andy mentioned was this optimized flush. So you've got the data sitting in the cache of the processor, and the optimized flush moves it from the cache into a special structure in the integrated memory controller called the write pending queue. So that's great. And the right way to do that today is with a cache flush operation. Now, what do you do, however, if you lose power in that case? So a number of smart server people and Intel have defined a mechanism called a synchronous DRAM refresh. And what happens is a platform can inject a signal into the processor, and if the platform provides enough energy reserve, the processor will dump its write pending queues out to DRAM, including to persistent memory. And so in the case of an NVDIMM device, it will end up in the DRAM of the NVDIMM device. And in the case of an Intel persistent memory device, it will effectively end up in the media. So that's a little bit of additional energy reserve, and maybe a period of time that's under a few milliseconds. And this is standard in all persistent memory servers that VMware supports. So it's a good thing. Now, you still have the problem of, for NVDIMM-N, how do you get it from the DRAM into the NAND device? And this is why you see this requires a supercap or another energy reserve in order to be able to do this. And today, you'll see integrated solutions where this actually, there are traces on the board that come up through the DIMM connector that supply this power to do this. In the future, it's possible in systems that have really large energy reserves that you could actually have the processor automatically flush the caches into the write pending queue and use ADR to kick it over to the device. Right now, that solution is BIOS, issuing special instructions. And this has been shown, for example, in the HPE Scalable Persistent Memory solution. So that's something you can do. Thank you very much. Okay. That's something you can do, but it's still a little bit exotic, and I think it's going to take some time. You can certainly imagine if you can write bias to do these kinds of operations, you can optimize it even further with hardware state machines and other kinds of embedded mechanisms, such that you may be able to cut down that time significantly in milliseconds, and the energy reserve might not be as large. That's going to be really good. I don't have time really to talk about persistent memory pooling, but as other speakers have mentioned, with CXL and Gen Z, you actually have the opportunity, because these are coherent I/O, and coherency is very important. You assume it without even realizing it. With the coherent I/O interconnects, you can actually take your persistent memory and place it on a remote device. Maybe, in some manner, maybe it's an I/O device that's either plugged into a slot on the server, or it's a device that lives in a centralized resource. Perhaps it's a CXL.mem device, and you could even have it behind a switch. Putting it behind a switch allows you basically to sort of do failover as well as load balancing. The failover is if one server dies, but you've managed to at least make its writes hit the shared device, then you can, with the assistance of a fabric manager or an orchestrator, fail it over to a different server, and you haven't lost much. Also, there's the opportunity to load balance. So if you have, say, 32 terabytes of persistent memory here, you can choose, I want to give 6 terabytes to this server and 10 terabytes to this, and I want to hold the rest in reserve. These are the kinds of games you can play with CXL or Gen Z, which will have native support or very near native support in the future. This is a future that we're pretty excited about. I'll just say that on capacity, it's going to grow. It would not be a surprise to see maybe 2 terabyte devices in the next 5 years. It wouldn't be a surprise to see that a 2-socket server could have 16 or 32 terabytes of persistent memory. And there are a lot of new technologies coming, but my message to hardware vendors is there needs to be one standard OS software interface, or we're going to screw it up. And that's good. It's good to know that Andy and others are already working on that next generation. So in summary, we are ready enough, but we will learn much in 2020. We need more applications. We need to change the customer and developer perception. And in the future, we expect a lot of collaborative work in the industry on data protection, server firmware and hardware, and persistence domain and power loss. And you can see hardware innovation for future topologies and technologies are really going to be a big game changer. With that, I'll end. I've used up all my time for questions, but thank you very much.
Yeah, catch Rich on the break for questions. Thank you very much, Rich. Good to see you again. So we are going to go into a break right now. There is some coffee and I believe a couple other things out there.
Coffee.
Please stop by the sponsor tables. And there is an NVDIM Programming Challenge demonstration that will be going on the break as well. And we'll be talking about more in the afternoon. So we'll see you back in about 20 minutes. Thanks. All right, as I would say in my best Ohio redneck, let's fire this thing back up. So I'm going to bring to the stage now Olusoji Denloye. At the Pearl Conference, and we'll mention that a couple of times, Pratap, who you'll hear from later, made an offhand comment. He said, what I really wish is, all the people that understand persistent memory would just take a language or take a runtime or something in open source and adapt it for persistent memory. Soji wasn't there, but as far as I can tell, he's doing it single-handedly. So please welcome Olusoji Denloye.
Good morning, everyone. My name is Olusoji Denloye. I work at Intel. I'm a software engineer there. We have worked with persistent memory for the last 2 or so years. We've developed libraries for Java, mostly, and we've done some performance work trying to integrate persistent memory into some open source frameworks like Cassandra, RocksDB, Memcached, that kind of thing. So today I'm going to be talking about some of the things that we've learned along the way, some of the use cases where persistent memory is actually applied in the real world. So this is a persistent memory conference. I'm sure everybody is familiar with persistent memory, so I'm not going to spend too long on this. I'm going to try and leave some time at the end for questions if there are any. So here are some of the properties of persistent memory. It's byte addressable. You have direct user access with the DAX file system. You don't need to, it doesn't involve the page cache or the kernel. It also lowers DRAM footprint. So if you are using persistent memory, then now you can use DRAM for other things or use less of it because it's more expensive. It also works with both file and memory, persistent memory APIs. And then also, with the Intel DC persistent memory modules, they come in 2 modes, as some of you might know. There's one is called the memory mode, where you use persistent memory as the main memory. So the DRAM just acts as a cache. And then the one we'll be talking about today is what we refer to as the app direct mode, where the OS is aware and a user can ask for persistent memory from a persistent memory namespace, that kind of thing. Andy showed this slide earlier. I don't know if there's a cursor here. Oh, good. What we'll be talking about today will be mostly in this space, where this is the standard way, when you have your memory map a file on a DAX file system, and then you can do load and storage directly. And then there's using just the DAX file system, where without doing without any code changes to your application, if you just point your application to a file system mounted in a DAX file system, and then all of a sudden you're using persistent memory. So I'll explain more about this. This one's called, I will refer to it in the course of this presentation as storage over app direct, and then this guy is the app direct node. So, some common use cases that we've seen. This seems a little loud. So some common use cases are, and this is not an exhaustive list, is caches, stores, and buffers. These are the areas where we've seen persistent memory being used in real-world frameworks. So caches are data structures that are used for fast lookups. Stores, what I mean by stores is where you eventually persist your data, like spinning drives, NVMe devices, things like that. And then buffers, buffers are essentially temporary storage. For example, like a log, you write quite a bit at some point, and then at a given point, you flush everything to, say, your store, your persistent media. So the advantage of using persistent memory in this case, before I go there, another thing that I would like to mention, and Andy mentioned this too, is you can use, there's a volatile use of persistent memory and then the persistent use of persistent memory. So volatile in the sense that you're just using the persistent memory for its capacity and its speed. But you don't really require any data integrity. So if you, just like DRAM, once you restart your machine, all of the data is gone. But then the classic persistent use of persistent memory is you expect the data to still be there when you come back. So just a quick point, persistent memory is always persistent. When I say persistent, volatile use of persistent memory, it's just whether or not you care about recovering the data on a restart. All right, so I'll jump right into the use cases. So I'll start with caches, and then I'll go into storage. So really quick, a cache is a fast and lightweight data structure. It's usually used for to improve upon your read latency. They typically live on DRAM for speed, and they're constrained by the size of DRAM. So caches tend to be relatively small. If you have a lot of DRAM, then you can have a larger cache. So the value of persistent memory here, if you move your cache from DRAM to persistent memory, you can now, because of larger capacities that persistent memory affords to you, you can now have that benefit of a larger cache. And a larger cache means larger, higher hit rates, which means better performance. Also, if you want a restartable cache, which is not very typical. So imagine you have a data center and you have a caching software that's been up for days or months, and you've cached terabytes worth of data. And then if you, for whatever reason that machine has to come back, go down and come back up, you could find yourself spending hours rebuilding the cache. Right? So with a persistent cache, the data is just there. There's nothing to rebuild. So this is another advantage of using persistent memory as caches, as we've seen. So the first use case is HBase. For those not familiar with HBase, HBase is the database for Hadoop. It uses the Hadoop distributed file system to store its files, but the diagram here shows the read-write path. So what I'm going to talk about today is the HBase bucket cache, which is an instance of this block cache right here. So this block cache, as I said earlier, the purpose of the block cache is to improve the read performance. As you can see, it's on the read path. So rather than going to disk all the time, if you cache frequently used blocks in the block cache, you can improve the performance. So in HBase, there was an effort, in order to use persistent memory in HBase, one of the things that they did was to provide this new map file-based allocator. So now with this kind of allocator, if you give it a map file, if this map file is on a DAX file system, then all of a sudden you can do loads and stores directly to persistent memory, like was shown in the slide earlier with the SNIA and VM model. And then another thing is, so once you've now provisioned the persistent memory, given this allocator, your data structure doesn't need to change. So whatever you are using on DRAM, you can use the same thing on persistent memory. So in this case, it was, in HBase, they use they use slabs of memory to protect against fragmentation. More on that later. So the takeaway here is this effort is upstreamed. There's a link right there, and there will be a slide with all of the links at the end of the presentation. So it's upstreamed, and once you can get this, excuse me, once you can allocate the persistent memory, then all you do is just use the same data structures as you were using on DRAM, and then you're good to go. And again, the benefit here is with persistent memory, with your cache and persistent memory, you can have larger caches and improve your hit rates. Next example is memcached. Memcached is an in-memory key value store. It's mostly used as a cache, and it's designed to be fast and simple. The diagram here shows, is a very simple diagram of how it looks internally. So your keys are stored in an in-memory hash table on DRAM. Well, everything is in memory. Your keys are stored in a hash table, and the value in the hash table is a pointer to a slab of memory where your actual value lives. So with Memcached, there is now an option for a restartable cache. So it's very similar to what I explained before. You have a custom map file allocator, which you can choose, which you can give if the file you provide is a memory map file on a DAX file system, then that's it. You're already using persistent memory that way. Then they also changed the layout of the data structure. It's now a hybrid. So it doesn't all live on persistent memory. The hash table remains in DRAM, while your values and the slab memory is now on persistent memory. So one thing to note here is, in order to use the restartable feature of this Memcached restartable cache, it's optional. But in order to do this, you have to have an orderly shutdown. And then what happens when there's an uncontrolled shutdown, you make sure you flush Memcached takes care of this for you. But what happens is that you flush the CPU caches. Because, again, persistent memory is cache coherent like DRAM. So you need to do this in order to make sure that when you bring the cache back up, all of your data is now persistent, has made it to persistent media. And then you rebuild the hash table on restart, and you're good to go. So this is also upstreamed. It's not something that I worked on, but it's upstreamed in the Memcached community. I've put a link there. If you're interested, there's more information on there. So this is one thing to note here before I move on. Another way to get a restartable cache, which we've also seen, without changing the data structure or without changing the map file allocator, what you could do is, leave your application as is, and then on an orderly shutdown, you could serialize using the storage over app direct mode that I talked about earlier, where all you have is a DAX file system mounted. All you could do is, on a shutdown, you could serialize all of your data in DRAM, your cache. You can serialize it onto persistent memory and then bring it back up on restart. That is it's an easier, it doesn't involve as much code change. Yeah. Okay, so this next example is with Spark. I'm not going to spend too long on it. This is an effort to enrich the Spark ecosystem. But just like the previous examples, we need a cache. We want to put it on persistent memory. And the route that they took here was to use this libvmem cache library. This is what I wanted to just point out here, all the options that are available to you. So libvmem cache is part of PMDK, which I believe will be talked about in a later presentation. It's open source. It's a volatile LRU cache, and it's embeddable. So you could just use it as part of your as part of your solution. In this case, the Spark OAP, and there you go. You have a cache that lives on persistent memory. Again, the benefit here is you have a bigger cache, and it improves your hit rates and improves your I/O. So now to the storage portion. I think I have about 10 minutes left. So now, why use storage? Storage, just as a quick recap, is where we typically persist data. It typically has a large capacity in the terabytes range, and it's usually an SSD or a spinning drive. Now, the reason to use the advantage of using persistent memory in this case is it's kind of obvious. Persistent memory is a lot faster than NVMe and SAS and the SATA drives. You also have finer grained access. That's byte access as opposed to block access. Also, depending on the way you design your solution, there could be no need for serialization or deserialization. If you have you could have data structures that live in memory, And once it's on persistent memory, it's persistent. There's no need to flush it anywhere else. There's no need to serialize it to some other format for it to live on disk. And in the same way, now you can have mutable data structures. Because of the performance, it's now a lot faster. So before, in existing frameworks, you would just append because of the speed, right? Now, excuse me, now you can actually update in place. And I'll explain more in the Cassandra example. So, Cassandra. Cassandra is a distributed NoSQL database. It's similar to HBase, like we talked about earlier. And here, what our goal here was to, how could we use persistent memory to replace the storage or augment the storage? So this diagram is the write path of existing Cassandra. So first of all, in order to do a write, we write to a commit log first, and then we store it in DRAM in the mem table. And then asynchronously, once the mem table hits a certain size, then it gets flushed to disk, onto what's called an SS table. So we replace that with our persistent memory storage engine. It's just a box right now. I'll explain what it is. But essentially, you just do synchronous writes to it. There's no need for write-ahead log or any of that. Similarly, with the read path. Now, I'm not going to explain everything that's on this, but just know that this is highly optimized to reduce disk I/O. Right? So we have caches, we have Bloom filters, and what have you, to improve the I/O on disk. And what we simply did, you simply just do a synchronous read request to the persistent memory storage engine. So now what is the storage engine? It uses open source components, PMDK, and a library that we developed called the low-level persistence library. It's a Java persistent memory library. Inside the box, you can see, and based on that, we built, we created a data structure called an adaptive radix tree. So the LLPL library essentially gives you what we call memory blocks, which is a Java wrapper around a block of contiguous memory that you can allocate using PMDK. So using those little blocks, we can build something as a complex data structure like an adaptive radix tree. And we then organize these radix trees into shards, and we built this engine. And we got really good performance too, 6 to 8x speed ups on reads and writes. Again, with Cassandra, if you didn't want to, this was quite a bit of code change. So if you didn't want to go through all of this, you could have gone the storage over app direct route, where you just point your Cassandra data drives to where it was an SSD or a spinning drive before. You could point it to your persistent memory namespace. And so instead of using drives, you're now using persistent memory. So you get about what we've seen up to from 1.5 to 2x improvement in performance. So, which is good, but not as good as you could get with re-architecting a good chunk of it. Another thing I want to mention is that this is a pluggable engine, so it's not all or nothing, right? We're not replacing all of disk to use persistent memory. There are some capacity issues there, but in Cassandra, there is a pluggable storage engine API. Not upstream yet, but this is what this effort was built on, and we hope to upstream it soon. Real quick, thank you. I wanted to mention this slide. Certain considerations for persistent memory use, persistent use of persistent memory. So if you're going to use this for the volatile use, this is not what I mean. I mean for the persistent use. The first thing is data integrity. So if you need data integrity on a controlled shutdown, you must flush the caches, just like we talked about in the restartable cache case. Now, further on, if you need data integrity in the face of an uncontrolled shutdown, or like a power loss or a crash, then you need you need transactions, essentially. And again, transactions will be covered, I believe, in the PMDK talk. Next thing is concurrency. Many lock-free algorithms use compare and set. And if you need data integrity, then it means you need a flush. But compare and set plus a flush is not atomic, so that's a problem. So it's something to consider. Actually, in this case, that's why one of the reasons why we use the sharded approach. So each R tree, each adaptive radix tree is single-threaded, and we just broke them up into shards, and that was how we were able to get concurrency that way, and it scales very well. Fragmentation is another thing to keep in mind. It's an existing problem that is just made worse because now you have persistent pools of memory, and that could live for months or even years. So the problem of fragmentation gets worse. And the problem can be eased by using things like the way you organize your memory, like using slab memory, PMDK, or reusing data structures, reusing allocations. And then I guess garbage collection is something that might be a solution to the problem in the future, but it's something that we're thinking of, and something that we're looking for better solutions on how to fix more in an efficient way. So just to summarize, persistent memory is available and it's being used, and it has value. It's been upstreamed in some open source projects, like I showed earlier. There are also multiple ways that you can use persistent memory to extract value for your application. You could go the no-code change route, which is what I call the storage over app direct, or you could do a modest data structure redesign and get even more performance. So it depends on the amount of resources that you're willing to put towards the problem. Also, there are libraries that are available to help you with your persistent memory needs. There's the PMDK suite of libraries. And then there are also Java libraries that we've developed, low-level persistence libraries. One of them, there's a link to it in the next slide. We just did a 1.0 release at the end of last year, so take a look. Also, if you don't want to use any of these libraries, you could also go the memory mapped file approach and do it yourself. Questions?
Two questions. Oh, I'm sorry. You next.
On your Memcached modification, how do you quantify in terms of scale or restart or latency with Memcached use case?
How do you quantify
the benefits of persistent memory when you move from memory to persistent memory?
When you move from DRAM to persistent memory, how do you quantify the benefits?
Yeah.
Well, excuse me. For one thing, the latency, we know that persistent memory is on the same order of magnitude as DRAM, but not quite as fast. So the individual latencies, the average latency will probably go down, but the idea is now that you can have it has bigger capacities, so you have a bigger cache and then bigger hit rates. That's where the performance comes from.
The main use case was to scale?
Yes.
Okay, thank you.
Could you please comment on power consequences going from, let's say, a DRAM to a persistent memory solution, or from a flash memory to a persistent memory solution?
I cannot comment on the power consumption. Maybe someone else in the room can. I don't know. It would also depend on which technology you're using, right? This table.
You'll talk during the break? Okay. Reach out to Andy during the break.
Right, any other questions? All right, thanks, Soji. Half an hour or so. And then a lot of these tools are being developed and are used in open source, and that's available for you as a starting place to be able to do future development. So I think there's a lot of opportunity here. So our next speaker is Charles Fan. He's the co-founder and CEO of MemVerge. He's also the newest SNIA and the organization formerly known as SSSI, say that fast, member. Charles, come on up. And we're going to hear what memory at storage scale and storage at memory speed. Charles, come on up. Thank you.
Thank you. Oops. All right. All right, good morning. My name is Charles. Memverge is proud to be the new member. We are also a sponsor. This is our first marketing expenditure of the company. We don't have a marketing person yet, but so we've been around for 2.5 years, and over the last couple of years, been working very closely with Intel as our whole company was started to develop software on persistent memory. And before this, I worked at VMware for quite a few years, quite a few VMware colleagues here. I was managing the storage team, and I learned quite a few things at VMware, and I think one of them is VMware does have Intel to thank for their success. You know, if you go back to 20 years, if you remember, Intel CPU start to taking a different direction. Instead of going faster and faster, you start to have more and more cores into the CPU. And it's a great technology. It's one of the reasons the cloud and data center is so powerful today. But at that time, one of the difficulties was the applications were not programmed to so many cores. The threading model and all that are not ready to take advantage of this new hardware. As a result, the server utilization was not that high. And some applications they try to rewrite, but it's not easy to convince every application to rewrite, to adapt to this new hardware. So this is where VMware came in. It created a sort of a middleware, a virtualization layer, an abstraction layer, that creating an API that's compatible to the hardware, yet you can have many of them sitting on the same servers. So you do not have to rewrite your application, yet you can take advantage of all the cores that's available in the new hardware. And as a result, the utilization go up, and that got VMware started. And of course, it developed many other things afterwards, but this became a powerful software layer and create a new software market that also helped the adoption of this great new hardware in the data center. And it's our belief we are in the same situation here, or similar situation here, where persistent memory is a revolutionary new technology that redefined what was known as memory and what was known as storage before. And it presents new APIs, and certainly there are applications that are rewriting to take advantage of this new hardware, such as Soji presented earlier on. But the reality is that not all workloads, not all applications are going to rewrite. The question is, how can we get all those workloads onto this new hardware and take full advantage of it? And that's a mission we have. So our mission at Memverge is try to create a software layer that's designed for persistent memory. Yet it presents API that's easy for application to consume, including existing application without rewrite, that they can start taking advantage of the bigger scale of the memory service the persistent memory provides, and the persistence of this memory speed storage that can take over the I/O of the applications transparently. And we can do so at the same time, software-defined, dynamically reconfigurable between those APIs. So that's the layer of software that we are developing. And I'm happy to introduce some initial, our initial version of the software, its design, and some of our initial use cases. So the space that we're targeting is the intersection between big data and fast data. We believe that's sort of lower hanging fruit where persistent memory will find its most compelling use cases. As we know, we are living in the age of data, and the word of big data has been around probably for more than 10 years now. And there are a number of good solutions on the market today to address big data. You can scale to many petabytes of storage. There are hardware solutions, there are software solutions. You don't need another solution for that. But there is a limitation to those solutions, and that is latency. A typical latency of a big data solution are in the order of milliseconds. And the fastest can go to maybe hundreds of microseconds in terms of latency, but no shorter. And that's partly limited by the underlying media that's available to power those big data solutions. So it's good to scale, but not so good with speed. Now, so what do we do with speed? So there are also a number of solutions that handle low latency situations. And those tends to be more DRAM centric. in the space of low latency trading or in AI or even in big data. There are more and more applications that's DRAM centric. They keep more and more of the processing all in memory. In those situations, you can't go to low latency. You can go to microseconds or even nanosecond level latency. But you have a scale problem because DRAM naturally is limited to the amount that's available to the applications, typically on the hundreds of gigabytes per server range. Now, what happens if you need both? And fortunately or unfortunately, there are more and more use cases where you need to deal with both petabytes of scale and nanosecond or microsecond of latency at the same time. And there's not a good solution to address those use cases. And there are more and more such use cases available. And we believe this is one reason persistent memory came at the right time. Because it does have the scale that's beyond the scale of DRAM. It does have the speed that's way faster, or latency that's way faster, 2 order of magnitude, or maybe 3 faster than the fastest SSD or NAND flash that's available today. So that provides a good foundation where we can build a solution that can address both big and fast data at the same time. And I'll probably go fast on this slide. I think the previous speakers know this much better than I do. The only thing I want to say is I do think it's a groundbreaking product. It's 20 years into working, and we believe it's just a beginning. Today, or this year, I think is year 1 of persistent memory. And it will have a long and happy life ahead of it. And we are happy to be a first mover, kind of creating the software on top of it. I think there will be more people like us. And I think this will be a vibrant ecosystem, and happy to welcome more friends to do things on top of this new amazing technology. And then diving into what we do at Memverge, the software we developed, we don't have an official name yet. We need to hire a marketing person to name the product. The technology is called distributed memory objects, which I'll go into more detail in the next slide. And our main purpose, if there's some marketing person, feel free to apply here. And let me know how you want to name it after the talk. In one sentence, what we try to deliver, at least in the first version, is try to deliver bigger memory and faster storage at the same time without requiring application changes. Now, you could do some of it certainly without us. As the previous speaker introduced, you can, if you just want to be compatible with memory, there's a memory mode that you can use. If you just want to be compatible with a block storage, there's a app direct storage mode that you can use. But if we want to use both at the same time and dynamically reconfigurable without changing applications, there's not an easy way of doing it. If you're just using app direct, the persistent memory programming model, it is a new API. You do need to program to it. And so the first module we did is what we call memory hypervisor. This layer essentially access persistent memory in the app direct mode. We actually use PMDK that Andy and team developed and to access and manage the persistent memory across a pool of servers. And yet to the applications, northbound, we present various storage and memory APIs that are compatible with the APIs today. And these are software APIs so that they are flexible, they are sort of composable, and dynamically reconfigurable. And they, so essentially we are a translation layer, we are an abstraction layer. We talk to the persistent memory in its native mode, and we present compatible API to the applications so that they don't have to rewrite. So that's what we meant by the memory hypervisor. The hypervisor in quotes because it's really different from VMware or KVM hypervisor. It's really do a protocol translation on the memory or data front. And above this hypervisor, and behind those APIs, we developed 2 interesting systems. The first one is a distributed file system that is optimized for persistent memory. There are many distributed file systems out there. Probably last time I counted, there may be 24 of them. Some of them open source, some of them proprietary. So the world doesn't need another one, except there's not a distributed file system available today that's optimized and designed for memory. And we believe this is the first of such kind that is designed from ground up for persistent memory and deliver storage services to the applications. And this is a sure nothing distributed file system running on servers. And behind the memory APIs, we also developed a tiered memory system. Essentially, it's a memory system that has 3 tiers. There's a DRAM tier, there's a persistent memory tier, and both of these are local. And then there's a third tier that is memory that's available on the other nodes in the cluster through some kind of network. Today, we use RDMA, most commonly RoCE, RDMA over Converged Ethernet. In the future, there could be over CXL or other memory fabric across the servers as well. So we developed a distributed clustered tier memory system behind that memory API. So the combination of those 3 components essentially does what I described. It takes full advantage of the properties of the persistent memory underneath across a cluster of servers, and they present them to be available to the application in both memory APIs and storage APIs, so that the application do not have to change, and they really have the best platform for their working set of data. And that has a latency on the order of hundreds of nanoseconds if it's local, single-digit microseconds across the cluster, and it can scale across the cluster to hundreds of terabytes of memory. So the next slide will give you a bit more details of what I described, as well as some of the initial use cases that we are addressing. Our software is in beta today, so we have not officially shipped our product yet. I guess we need to have a name to ship the product. But we do have a few customers. We have about a dozen beta customers who have been working with us in proof of concepts and running this in their environments. And so on this picture, at the bottom, you see the compute nodes. Those are servers. And we are software-only product, so it can be any servers from any of the server vendors. Inside the servers, there are persistent memory, but there could also be DRAM inside the same servers. There could be SSDs inside the same servers as well. They are interconnected by some low latency networking. As I described, we recommend RDMA networking. And our software is this blue box between the application and the servers. And the APIs we provide to the applications include a POSIX-like file system that essentially the application can just use as any VFS on Linux. So we are a user space software running on Linux. It can run on physical nodes. It can also run inside of virtual machines. And we actually have a demo that for us running on top of vSphere inside of vSphere VMs. And it can also be deployed on the cloud after the cloud have the persistent memory available in their infrastructure as well. And the APIs we provide, as I mentioned, on the storage side, we have a POSIX-like file system API. We have an HDFS API that for anything that's talking to HDFS today, they can just talk to us instead. And the reason we support this protocol first is because some of the use cases we targeted first in big data analytics, in machine learning, AI training, HDFS API is a popular API that they use. And we do have our SDK, so for those who do have control over their software, they can certainly link to our SDK and call our function calls directly as well on the storage side. And on the memory side, they can certainly use our SDK to allocate and deallocate memory that way. But we also have other ways to intercept the memory functions through LD preload. So we would intercept the various memory allocation calls into our system so that we handle the memory allocation and place them on the right media underneath in our tier memory system. So this allows us to work transparently with applications that they do not, if they wish, they do not need to change their applications and yet readily can use us both for their memory and for their storage I/O. The key application, I mentioned a few, they're machine learning, TensorFlow workload. We're working with some customers with TensorFlow. Their big data, analytics workload. We have quite a few Spark deployments among our PLCs. And we also have recently have a version of RocksDB that works well with persistent memory. And we also use that RocksDB as a storage engine for MySQL and MariaDB so that we have a clustered MySQL deployment with a customer that increase their credit card processing by at least 3 times in terms of transactions per second. So there are some use cases there as well. But what's most exciting for me in the last few months is we start working with quite a few financial customers on Wall Street, particularly for their trading infrastructure and for their market data infrastructure. There are quite a few use cases that can really enjoy, I think, these exciting new properties persistent memory and our software bring to those use cases. So I'll give some examples of these use cases. The first one is a big data analytics use case, and this is us working with a cloud service provider. This is a cloud data warehouse service built on top of Spark SQL that runs on top of a cluster of Spark nodes. In fact, I think last year at Persistent Memory, we gave a talk invited by Intel that went into, I think we co-presented with Tencent, if I remember correctly, on this use case. And this is exactly their use case. This is actually, we creating a DMO cluster, that's the Spark accelerator on the side. They have a Spark farm that can scale to a couple of thousand nodes. We basically move all their intermediate data from the Spark, including RDD data, including shuffle data, all onto our nodes that in turn not only did not slow down the performance of the Spark queries, but actually speed it up. Here are some examples. Terasort with RDD caching speed, they're 5x or 7x of performance speed up. And also through this process, we move those intermediate state away from the Spark cluster so that the Spark farm become more elastic. It's become more stateless and elastic, and that is desirable for this particular cloud service provider. So they liked us for the performance speed up as well as for the removal of the state from their core resources. So this is one example of us using DMO plus Optane DCPMM to deliver for a Spark use case. A second example is us working with a social networking company based in the US. And it is the infrastructure for AI training behind their recommendation engine. It's running TensorFlow with a model called Wide and Deep. And Wide and Deep is a popular model for recommendation engines. And one thing with recommendation engines, the model is not necessarily very deep. It's not like image recognition or say, oh, you have many layers. But it's very big. It's very, it actually takes many terabytes of memory space to just have the model itself. It has many, many parameters. It's a very sparse model. And the training data itself is huge as well. They have over 600 million users. So that's the edges. And you have many billions of edges, which are the connections between those users. And you need to feed all those data into this huge model over 1,000 times in order for the parameters to converge. And so that you can making the recommendation on the people you may know, or maybe the job you may want. So this is the core service for that social networking company, and the training typically takes a couple of weeks to complete, and it takes a cluster of servers because of the amount of memory it needs to have. So there are a couple problems. One is just the speed of convergence, and the other is that because there are more than one servers, the chance of failures is high. How do you recover from the failure become a problem, because if you lose a node, they need to restart the training from 2 weeks ago. So that's a lot of waste of resources and time. And by replacing the local drives, the HDFS they are using with a DMO system, that we are able to achieve up to 6 times improvement in the length of training. So what used to take a couple weeks now takes a little more than a couple days. And just the storage importing from various data sources into this system sped up a lot, just because the previous system wasn't that fast in getting the data in. And most excitingly, that we can perform checkpointing much more efficiently. One particular sweet spot, we believe, for persistent memory is efficient checkpointing, because checkpointing is where you copy the data from memory to a persistent store, and in order to save the memory state so that you can recover from it in case of failure or for other reasons. And now with memory itself being persistent, there are various ways we can optimize that process. And not to mention the speed itself is much faster. So we have a capability that can do very fast checkpointing that really made the failure recovery more graceful in this use case. So that's a second use case, AI training use case. The third is a group of use cases I just mentioned. These are with the financial customers. This is not yet with their mainstream infrastructure, their vSphere setup yet. This is with many of these financial institutions, they often have a corner where they have their low latency infrastructure to support trading and support fast, high performance market analytics, market data analytics. And that's sort of a niche, but it's a big niche. And there are a lot of value associated with that infrastructure, and that often is the early adopter of a new technology as well. And we've been working with quite a few customers, including hedge funds, quantitative firms, banks, investment banks, as well as the exchanges. In some of these use cases, we're working with some applications such as KX, which produce a time series in-memory database. And then we support KX, we support a few other databases, and we support in-house applications that they develop for this also. So generally, we found at least 3 areas the persistent memory and our software has a potential value to add. The first one is sort of in what they call the back testing. So what back testing means is for people with quantitative researchers or quants. They invent new models and they need to test the models. And the first way they test the model is using historic data. So they usually have a storage that takes a few hundred terabytes or 1 petabyte of market data, some NAS system or some distributed storage system. They use a KDB or some other solution or their own solution to be able to query a subset of those data that serve as the input into their model, and then they take the output of their model for prediction and check with the actual historic data to see how well they match. So that's a very common way for quants to validate their models. And now if you have a lot of quants, the storage become a big bottleneck in performing these backtesting jobs. And for our system, we can providing a much faster system. So the existing state of art is they keep certain data in DRAM, but not a lot, and most data in the storage system. Now with our system, we can creating a layer that's bigger, that can take more of the data and deliver it much faster to these quants, so improve the backtesting efficiency. And then there's a pub sub service. This is a more real time. This is very important for the exchanges as well as with some large banks. As the market trades are happening, those ticker data coming in, and they have a sequencer that's writing them down. And then at the same time, they have many other processes need to consume this event stream, which are these trades that come in at a high rate, and they want to deliver to these many processes with low latency and with good fairness. And And to do so, there is an existing system using some kind of multicast on SolarFlare, but at the same time, they need to persist it at the same time onto the storage. So we are delivering a new solution based on DMO that essentially using the combination of the obtained DCPMM and the RDMA Mellanox network, and having a new mechanism to allow this data to be shared across could be 100 different processes that are consuming this event stream. So that's another use case that we are very excited about, and we are validating that with some of these customers. And the third one is working with KDB, both in accelerating the KDB performance, but also potentially to help KDB in the crash recovery use cases as well. So we're working on a partnership there. So those are some of the financial use cases that have emerged recently and we are pretty excited about. So at the end, this is my last slide. So let me just give you my high-level view of where the future holds. I'm sure here many people share this view, and some people might know this to a higher granularity than we do. But let me just share with our view here. Our view is in the next 5 years, we believe it's going to become obvious to everyone, not only to the people in this room, but to everyone that persistent memory is here to stay. And it's going to be an important component of a data center. In fact, thanks to persistent memory, DRAM is not going away. It will continue to exist. But a combination of DRAM and persistent memory, we believe will create a new memory tier. Right now we call it MCI. We call it the memory converged infrastructure. You can give it any other names, but it's a new memory tier. As a result, the data center will become more memory-centric. And what do I mean by that? Is that this memory tier will be very different from today's memory tier. Number one, it's going to be much bigger. We believe it's going to go to hundreds of terabytes per server. Yeah, certainly Intel and others need to work hard on that. But we think it's going to go to hundreds of terabytes per server, and the cost will be going down. And imagine, as an application developer, you have 100 terabytes of memory available to you per server. That just opened up the new world for you, how the new application can be developed, how they can be optimized, how they can be deployed. So that's going to change the application world. And secondly, it will be persistent in itself, this memory tier. It's big, it's cheap, and it's persistent. So what that mean is if you have the right layer of software that to go with this memory tier, deliver the right data services directly on this memory, the primary performance tier storage as we know it today may no longer be needed, because all those functionalities we are relying on primary persistent memory, primary performance storage now will be performed and fulfilled from a memory tier themselves. And that's going to be a big shift to the industry as well. So this is very exciting. And we are here to deliver this software tier. And we will not be the only one. I think there will be others who join us. But I think there's a great future that's going to move tens of billions of dollars around in this industry. And we are glad to be a first mover and look forward to this journey together with all of you. Thank you.
In your summary, you just said that DRAM was not going away, and then you said the memory tier may no longer be needed. I don't know how to reconcile those two statements.
Sorry, maybe I had a typo, or so I think what I meant, and that's, so what I meant is the primary performance tier storage layer may no longer be needed, not the memory tier. So I think the memory tier will become bigger, and it's going to take over the data center. And the storage as we know it today, and by the way, if there are storage people in the room, it's not meant to be offensive. I think the function will still be needed. It's just the form factor, I think, will look a little different. So the data center today, I'm a storage person also, so the data center today is you have servers. Server have compute and memory inside, and then you have performance tier of storage. Those are now more and more all flash arrays or so on. And And then they have capacity storage either on-prem or in the cloud that give you, a lot of scale. So, and they are interconnected by various kind of networking. So that's sort of, from a certain perspective, how the data center looks like today. In the future, we believe this memory tier will become bigger, more powerful with the right data services, and answering to the data persistence needs or for active data directly from the servers. So the green part will be the sort of the new server racks, and there'll be potentially new memory fabric interconnecting them. And that layer might answer to all your data needs. So the performance tier storage, as we know it today, may no longer exist. So that's what I meant. Yes?
One more. Can you wait for me to come to you?
Yeah, I think I heard it. So the question is whether it's an appliance model, whether or else. So we are actually not an appliance model. So we are a software-only model. So our customers would, and we noticed a shift in customers' sentiment also, that they like to standardize on their server infrastructure from their favorite server vendors, or having a right bidding process between the server vendors, and our software work on all of them. And so it's sort of a VMware model where it's a software only running on all major leading server platforms, and or on the cloud as well. And we are licensed based on we haven't finalized the licensing model, but we are licensed. Our current thought is we are licensed on the amount of persistent memory that we manage, and it's transportable between cloud or on-prem.
I think we have one more.
Yeah.
There is a difference between endurance of a volatile memory like a DDR and a non-volatile or persistent memory here. So if you think of, if there are hundreds of millions of read writes to a DDR, the DIMMs will still work after 5 years or 10 years down the stream.
Right.
But if you do the same workload on a non-persistent, a persistent memory, you may probably brick the device within few years.
So the endurance of persistent memory is significantly less than DRAM.
Absolutely.
And so that's why it's just like Intel memory mode, which is really a two-tier DRAM with PMAM, where DRAM absorbs many of the write cycles. And similar with our tier memory design, where we do have a DRAM tier in our tier memory service, where that will absorb many of the write cycles from the applications, so that the persistent memory write cycles will be enough for that.
So if you have questions for Charles, please visit him in the Memverge booth over lunch and at the break.
Yes, we do have a booth, given that we spend the marketing dollars, and, and we have some demos, so look forward to talk to you.
So thank you, Charles.
So we have one more talk before lunch, and I think this is going to be a great talk. So this is a Pearl alum speaker and Intel employee, Piotr Balcer, and he's going to talk about PMDK and how it's evolved over time. Take it away.
Thanks. So I'm Piotr Balcer. I'm one of the developers behind PMDK, and today I'm going to be talking about how we changed PMDK as we learned more and more about persistent memory. So this talk is going to be hardcore programming, just so you know. But before we begin, I want to first briefly introduce what even is PMDK. So PMDK stands for Persistent Memory Development Kit, and it's a suite of libraries and tools designed to make persistent memory programming easier. And we really think of it as the standard library for persistent memory. So like you have your libc, where you have malloc and free and stuff like that. Persistent PMDK kind of tries to provide you with similar types of capabilities for your applications. So we have two different types of libraries. We have persistent libraries, and then we have volatile libraries. The volatile libraries are mostly for taking advantage of the high capacities of obtaining persistent memory. The few libraries that we have is libvm cache, which is what Soji mentioned in his presentation. It's an LRU cache. And then we have a couple of allocators that are derived from jmalloc. And those allocators allocate memory from PMEM instead of DRAM, which is not as easy as it sounds to change. So then there are the more interesting libraries, the persistent ones. And in here we have a couple of different things for different people. So at the bottom we have libpm and librpm. libpm is the very bare bones of what you really need for writing software for persistent memory. It has stuff like mapping your files, giving you information about whether or not you have actual persistent memory. It also ships with optimized memcopy and memset for persistent memory. And then we have librpm, which is kind of our example implementation of how to use RDMA in combination with PMEM, with persistent memory. Moving up, we have libpmobj, which is our flagship library. It implements memory allocation and transactions for persistent memory. Then we have libpmobj CPP, which is built on top of that, and it just provides you way nicer interface for those use cases, because it's in C++ instead of C. And then we have libpmkv, which is built again on top of libpmobj C++, that provides you even easier interface. So first I'm going to be talking about usability changes that we've made over the years. So right now I'm going to be focused on libpmobj mostly. So our first draft of the libpmobj API implementation was what you see. It's not very pretty, and it's really hardcore C that probably not many people will even understand at the first glance. So the reason why this looks like it does is because this was our first draft, and two, we really wanted to use C without any compiler modifications. So we didn't want to introduce any preprocessing steps into the compilation, so that we just use what C99 gave us. So the result is kind of difficult to use API. But nevertheless, we haven't given up, and we made some optimizations. So about 2 years later, we came up with an API that used tons of macros to make this a little bit simpler to use. So compared to the previous slide, right now we have typed pointers, because previously if you wanted to use persistent memory, you kind of gave up types in our previous API, and with this API we actually retained the type information. We also simplified the transaction flow. So this is what our API looks like right now, and all of the future libpmobj libraries look like this. So we think this is a good middle step between having very difficult to use but powerful library and something that's very limited but convenient to use. But ultimately, I think that this is what we could have come up with for C. I don't really see a way for making this a little bit simpler in C without any compiler changes. So instead of focusing on C, we really wanted to move a little bit forward, and then we spent a little bit of time thinking how the APIs could look like if we were to have a more expressive language than C. So we turned to C++, and then we made a couple of prototypes to see what we can achieve with the meta programming capabilities of that language. And the result is pretty nice, if I can say so myself. So instead of having the bulk of the changes concentrated on the code, we instead shifted the focus to the type system. So whereas previously, so for example here, we have macros that are used to the reference objects, pointers, which is clunky to use, and you pretty much have to modify every single line of your application if you had an existing application to use this. With PMDK C++, we made it simpler so that all of the changes are mostly concentrated in the type system. So you instrument your types with, instead of using shared pointers, you use persistent pointers and stuff like that. And then you just wrap things in a transaction, and that makes it automatically transactional. So this was our evolution, and what we think is kind of the ideal way of writing software for persistent memory from in PMDK right now, because it allows you to have all of the features of the PMDK without being constrained by C. So one of the things that we learned in this experience was we released way too early. So look at the dates on those slides. So this was literally 4 or 5 years ago. And the 1.0 release was created like 3 years prior to any hardware being available. So this led to us not being really that experienced with the actual persistent memory hardware. So we also could have used more time with the designing of the APIs. Other thing is that meta programming and types and using the type system instead of relying on the arcane C macros is really a great way to simplify coding. So some people might say that using C++ and templates and stuff like that is error prone, but I think that it really simplified what we wanted to accomplish. But nevertheless, we didn't think that PMDK C++ is for everyone, because it still required quite a lot of knowledge about writing C++ and persistent memory and transactions and allocations and data structures. So we made a step even further, and we created a simple key value store API that can be used by anyone and is just way simpler than any other our approaches. So we did this because people are familiar with key value store APIs. And before introducing the key value store API, we had very limited interest in PMDK C++, because those libraries are really, well, difficult to use. So providing an intermediate step that people can just take and experiment with really helps. So another thing that I feel we kind of rushed initially is the interface for memory allocation. So we just simply took the memory allocation interface that you have with DRAM, so malloc, and we created a persistent version of malloc. Kind of. In a transaction, it works like this. So like on this slide, we have a make shared. So this is what you will do in volatile memory to create a shared object. And on persistent memory, we created something called make persistent, which allows you to allocate persistent memory. So this made perfect sense to us because people are familiar with memory allocation interfaces that they used. But one unfortunate aspect of dynamic manual memory management is fragmentation. And with persistent memory, the length of life of the heap is way, way longer than for volatile applications because the heap can live on for years. And the heap outlives the application process. So we have to think a little bit more about fragmentation. And in hindsight, I think forcing the application to design the core data structures around trying to solve fragmentation will be a real benefit. So for example, you can work around fragmentation by using slab allocators. So creating an API that will instead force you to use slab allocators for your objects will be beneficial. We actually introduced a similar API to LibPMJ C++, but it's not a core API. You don't have to use it. And everything just still works with make persistent, just normal malloc. But just using the slab allocator will be just better. So one of our biggest goals with PMDK is correctness. And we want to make sure that everything we ship and we release is as correct as we can make it. But what I mean by that is that if you crash your application at any moment of time, then we want to make sure that that region of memory is recoverable and you can get back to your data, to your allocated objects, for example. So doing that, making sure that everything is correct, is really not simple. And we've spent a lot of time to develop tools like PMCheck and PMReorder that allow us to identify potential mistakes and bugs in code and then fix them before we ship anything and before we have any bugs in production. But so the problem with the approaches that we have is checking if a complicated data structure modification is correct, is fail-safe consistent, is very expensive because you have to effectively step through every single step of your application memory state and then check if that memory state is consistent. So instead, we effectively did isolate certain parts of our algorithms so that we just check smaller bits of algorithms, and then we bundle them together to make sure that everything together is correct also. So now I'm going to shift focus to performance and how we changed performance over time and why. So this is a chart showing you the difference of performance between the versions of LibPMJ. So we started really bad, I think, honestly. So we improved performance over 5 times over the course of a couple of years. So current version of LibPMJ is 1.7. So it's 5.5 times better now. And one of the things that we really started thinking about when designing the algorithms for the new versions of the PMDK is that persistent memory isn't really just memory, like we thought about before. It really has characteristics of both storage and memory. And we really should think about how this algorithm will perform even on traditional storage. So this is an example of how we changed our transactional subsystem to make it perform better on persistent memory when treated as storage. So whereas previously for transactions, we created allocations for every single snapshot, for example. Right now, we simply create a buffer where we create snapshots for transactions. So that larger buffer allows us to simplify the snapshotting logic instead of creating small allocations for every single one. So what I really want to highlight here is that the performance of non-persistent memory can be really tricky to get right. And we had to focus really hard on even individual cache misses that we encountered during development. Another point I really want to make sure that sticks is that persistent memory is really disrupting. And like I said, it has characteristics of both storage and memory. And this means that things like cache-oblivious data structures or data structures designed for persistent memory like LSM trees can be really beneficial when designed right for PMEM. Okay, so one other thing that we did in libpmem was creating our own implementation of memcopy. And we didn't do this for performance reasons, really, or maybe not for throughput reasons, but rather to make sure that our memcopy is deterministic in terms of what instruction does it use. Because certain types of instructions have different influence on the whole system. So, for example, one of the flags that you can pass to our implementation of memcopy is non-temporal. If you pass that non-temporal flag to memcopy, then you are guaranteed that the memcopy will use non-temporal instructions. And what this gives you is the possibility of avoiding cache flashing because the non-temporal instructions bypassed the CPU cache. So what we learned when we've been working on PMDK and its data structures is that correctly using non-temporal stores is very critical for performance. And avoiding cache flashing and unnecessary expenses when possible is the way to go. Okay, so once again about memory allocator. After transactions, our memory allocator is the most changed thing in PMDK. And the initial interface that we designed it with was kind of similar to malloc, where you provided it with a size and then it gave you allocated object. But that came with a problem that your allocation had to be immediate. So once the object was allocated, it had to be persistent, and it had to be stored somewhere so that it was reachable. So that caused a lot of performance. So we redesigned this a little bit so that the persistent doesn't have to be immediate. So we changed the interface into two parts, where you first reserve an object in volatile state, and then you publish that object in persistent state. So we first make changes in volatile state and then in persistent. This allowed us to do some very clever optimizations in various parts of PMDK. So the lesson here is that combining DRAM and PMEM in algorithms is very beneficial very often. Because in DRAM you can stage a lot of changes, buffer changes, and then on PMEM once you gathered the DRAM changes, you can just publish those changes into PMEM without much of a problem. One of the other things is that offloading data to PMEM is beneficial when you don't want to delay the main thread of your application, because when you store something to PMEM, you have to issue an SFENS, which stalls your CPU, so that's also not a very good idea. Like I mentioned before, also something worth reiterating is that storage-focused algorithms, data structures, are also something that should be considered when designing data structures for persistent memory. So this is something that we learned in PMDK, and we definitely take advantage of. Okay, that was my last slide. Thanks.
Questions?
Thank you. On the linked list example, the good version, the one that you like, my understanding is there's a lock associated with the operation there. It's my understanding that locks are released at the very end in some sense. So if a transaction has nested transactions and you're accumulating locks, they're all released at the end. Is that correct?
Yes.
How would you implement a highly concurrent linked list, for instance, governed by hand-over-hand locking?
Not using this API. So highly concurrent.
Do you have an API that would be appropriate for that use case?
No.
That's one of the most primordial concurrency paradigms, right? Hand-over-hand locking.
Well, yeah, but the difficulty with persistent memorial concurrency is the difference between visibility and durability, persistence. So making sure that something is durable or persistent, and once it's visible, is difficult, and you have to, for example, flash after you read something and stuff like that. And it's just making concurrent linked list, for example, will be just difficult, because we will have to expose a comparent swap and that type of instructions that also contain persists. And then we will have to have something that reads data, that is also making sure that it only reads data that is also persistent.
If it's a tricky problem, there are some grad students here who might take this on as a dissertation project, right? I mean, if you don't see light at the end of the tunnel, maybe one of them will.
So what we actually intend on doing, and what we are doing right now, is we ourselves are designing data structures that are concurrent. So we have, right now we have a concurrent unordered map. We have concurrent ordered map that we implement ourselves and that we verify is correct, because we believe that not many people will get it right. So I'm not sure if making an API that is specific for concurrency that is going to be extremely difficult to use is just worth doing. I know that there is a research paper from Microsoft, I don't know, I think so, that is multi-word persistent CAS, something like that. It's clever, but it's not as generic as I would want it to have to be a public API of PMJ.
All right, so if any grad students want to talk to Peter about an internship in Poland, you have some opportunities to do that as well. Again, you know where the business center is. Right now it is lunchtime. We are right on time. So head out for lunch. We will see you back in an hour, right? 1 hour. Everybody hustle up. I'll give you 30 seconds to sit down. We're good. I heard the bells. All right, well, we're going. So Jim Pappas mentioned earlier, Stephen Bates was sick last week, and then I think the rest of his family got sick. So he decided discretion was the better part of valor and chose not to travel. And then, of course, Jenny's been sick as well. So, I mean, in the very least, what we can say about this particular persistent memory summit is the chance of a random random but relevant F-bomb is dropped significantly with those two out. But in the process, we had to then figure out, what are we going to do? We wanted to make sure that we covered the topic, and this is NVMe, CXL, and persistent memory. So Stephen had written the presentation. We asked around, and luckily Milind Mittal and Scott Shadley both said, yeah, we're willing to do it. So my request to him briefly before lunch was take like 3-4 laps around the building, get your blood pressure up, and between the two of you, that should equal about Stephen's energy. So let's grade them on how they do. Welcome up Milind first, and then Scott in a little bit.
Yeah, hello, can you hear me? It's okay? Good, okay, good, yeah. So yeah, I mean, this thing came up just 2 days ago, but I think it's a comfortable topic, we can cover that. Hopefully do justice to what he meant to cover, how he meant to present it here. So here basically I think the one point is that the theme of this presentation is now about bringing 3 technologies together: persistent memory, and then CXL and NVMe. So he mentions that basically here we're saying is that persistent memory we've talked about in past has been discussed here, and now we want to talk about how this can be really realized in context of CXL, and particularly then applying computational storage to that memory paradigm, right? So you need one additional piece beyond CXL for that, and we'll talk about that. So what is CXL? So I'm pretty sure that almost everyone here has heard about this new interconnect that is being led by basically multiple companies: Intel, hyperscalers, silicon providers. Xilinx is also on the board of this consortium. And just a little bit of background for people that this desire to have additional capability added to the interconnect, as it interconnects from the host to accelerators or external devices, that's been there for now a number of years. Multiple efforts that we're trying to address that this new capability opportunity. And now the really good thing is that with CXL, that finally I think the whole ecosystem is coming together, where all the silicon vendors, system vendors, hyperscalers, everybody is basically behind the standard. And now we can truly look forward to moving forward with additional capability beyond PCIe. So what is CXL? CXL is really, it's very compatible. It just builds on top of PCIe. I think for large number of cases, PCIe really is the right framework when you're doing I/O coherent traffic between the accelerator and the host. But there are use cases that are developing where you want to bring heterogeneous architectures where the accelerator is more like closer to the processor. It can do sharing of resources with the processor. Also, the memory attached to the accelerator is now part of the system memory pool as opposed to being a private memory. So CXL really builds on top of PCIe. So here, it can connect into the PCIe connector. And the way to think about it is this, that at the discovery time as a link comes up, right? You can, if there's a PCIe card that you have put on that slot, you'll connect to the host as a PCIe. Or if you have put a CXL capable slot, connect card, then the link trains as a CXL link. The speed-wise, the speed is consistent with PCIe Gen 5. Is the framing format on the wire would change. It will be CXL format. It's called FLIT format for CXL. So this is how it basically builds on PCIe. So speed-wise, is completely working with the PCIe there, 32 gig, Gen 5 speeds, and basically with this now push for considering device attached memory to be part of system memory, which really calls for very low latency interconnect, right? And also now with accelerator performance requirements going up, where you also could really benefit from more bandwidth. So there's a really now aggressive push to move PCIe Gen 5 to even get to PCIe Gen 6 very quickly. So let's now look at the next level detail of basically the CXL other attributes. So it comes up as a CXL link, right, based on PCIe Gen 5. Then CXL has this memory, basically CXL has these additional capabilities beyond the PCIe. CXL has these three types of, which actually is shown in the next slide, is the three types of traffic that it can carry. Is a native PCIe traffic, which is called CXL.io. Then there is memory, where basically you are like a memory target for a point of coherence, which is in the host. So just like locally you have DIMM slots, at point of coherence beyond that you go to local memory controller. CXL allows that memory controller to also exist across the link. Right? It's just, that's a simple way to view it. So point of coherence is still with the host, and then you can come and basically this is part of the memory pool. So that's .mem. In this case, there is already work done in UEFI to expose this memory differently than reserved memory. It is exposed as conventional memory, but with a special marking, which is called a specific purpose memory, SPM. So it is basically giving this guidance that ultimately it is part of system memory. However, it is not necessarily suitable for OS to allocate its own data structures here, right? And there may be additional restrictions that may apply. But it's a paged, it can be a paged memory also, but it is also, you can have the shared page tables with the host and so on and so forth, right? It depends on how far on the OS layers we go to expose this, but it is really a memory that is part of essentially, you can say either driver managed within the OS or kernel managed itself. Okay. So this is .mem, and this memory can be hot plugged, right? Because it's connecting to a device, it is more suitable to be hot pluggable memory. Then, from the form factor point of view, the standard PCI form factors would work. Also, there is active work that is underway, that's happening, that today you have this even.s form factor or U2 form factors where they can also connect over essentially PCIe. So it would apply there as well. So then from management perspective, so because CXL also supports this PCIe traffic, and essentially PCI, it completely supports the PCI management framework. So all the configuration, discovery, so the device is discovered as a PCI device, then you determine that also this is CXL capable, and then you get additional capabilities visible to you at this point in time. But the management wise, it is otherwise essentially consistent with the PCIe. And then the other frameworks also are available where basically if you have some support for SM bus, that would just come naturally with this as well. And in the OS, from management perspective, again, this other ACPI framework, and also the other dimensions here like HMAT tables, which are really giving you this description of a different nodes and how far apart the memory nodes are from the compute nodes and so on and so forth. This will just show up as part of you can consider as a NUMA socket essentially in that framework. Now this is getting into those things that I had to mention already there, is that there are really three types of traffic that is carried over CXL, CXL.io, which is for discovery configuration, and also address translation service happens over this. And because your cache is here, you want to enable cache access to be done from virtual address space, but caches are physically addressed. Basically, as part of .cache of CXL, you have to support address translation service. So that is also part of basically you ride over CXL.io for ATS support. Interrupts, MSI, signaling you leverage from the IO framework. CXL.cache is really now, today for PCIe, the accelerators or any functions on the PCIe device, the coherency paradigm that they use is what's called IO coherency, which is basically they can do any access to the host memory. They will get the latest copy from wherever it is, whichever cache holds that latest copy, but the device cannot cache the data for itself. If it needs to reuse the data, it has to go to the host again, or it has to just make a local copy which is not coherent with the host, and then use a data sharing paradigm which can deal with existence of non-coherent data. So there are certain paradigms there where you explicitly move the data around. As you consume the data, you make a local copy, and then when you produce the data, you push it back to the host, right? A producer-consumer model where coherency can be managed at the point of transitions. But in case of CXL.cache, what you get is that now you can actually cache the accesses that you're doing to the host, and for future accesses, you do not have to go back to the host. And basically the coherency is maintained. If the host needs that line of data, you will get the snoops. So this is .cache. .memory is really, as talked about, it's like a memory controller attached across the device. Still controlled by the point of coherence in the host. There is one other detail quickly here is that the local memory is a little bit more than just the local memory as a memory controller. Now there's a level of detail. There is a support in CXL that allows you to go to this memory directly, because if I have an accelerator and memory on the same device, this is a type 2 device in the CXL. So in that case, it doesn't really make sense to go to the host, get the data from local memory, right? Go and make a hairpin turns like this. So there is a provision in CXL that at certain, inconsistent to the producer-consumer model, you can essentially have support where you can still maintain coherency, right? When you can directly go to the memory that is local to you, but this is not for fine-grained data sharing. It is more for producer-consumer model, coarse-grained data sharing, but the coherency is still maintained through hardware mechanisms. Okay, so this is some detail there that is available in the spec. So these are three basically types of capabilities that CXL is adding. Now what can, so again, in terms of .io is doing DMA, interrupts, we talked about SRAOV support is there, ATS, we talked about that already. And then of course you get NVMe interfaces as well, because that's a PCIe interface. .mem, we talked about that already here. And here, I mean, the memory could be a persistent memory, that's what's more interesting here, but could be just general purpose memory as well, so DDR memory as well. .cache is able to cache. How am I doing with time? I think I'm taking too, yes. Is okay?
12, 15 minutes, yeah.
Okay, so I have to pass on to, okay, so sounds great, okay. So representative use cases. Now what are the new use cases that you can do with CXL? So first look at the case when it's a .cache. So it's like flipped, you can think host on the bottom and the device on the top, host on the top, device on the bottom, or it's just the other way around here. So now let's think what you can do with this. That first of all, you can do, in a NIC today, right? NIC wants to really work on the headers, right? It wants to do the header processing, and then it wants to pass on the payload to the host. In this case, instead of now buffering the data locally in the NIC, where you need to have additional memory, right, a DDR attached, you can really pass on the data to the host as soon as you can, and if you need to do further processing, you can still keep the cached copy of what is important to you in your cache and operate on it without having to go. Basically passing the packet, or as soon as you can pass on the packet to the host, does not mean that you cannot work on it efficiently. You can still keep the portions that are interesting to you, they'll come to you, stay in the cache, and you can operate on it, right? So it allows you to optimize the memory that you need to connect to the NIC. And the second thing is that atomics now becomes a lot more efficient to implement, essentially, atomic operations. You don't have to just go all the time remote atomics to the host. You can do the atomics locally, right, in the memory. So that's the second benefit. And protocols wise, so in this case, a subset of the PCI that is a CXL that is supported for this case is CXL.io and CXL.cache. Now let's look at the memory case when I have a cache, but I also have some local memory. This is the case I talked about already earlier. In this case, Exadata could be a GPU, right? Or you could be doing some computation near memory. Here, if the paradigm is still producer-consumer paradigm, right? What you can do is you have an accelerator, you have memory, you can work on this memory, but this memory is not private anymore. But from performance perspective, you still get the goodness of it being private, as if it were private, because it's local to you. But at the same time, you don't have to do this burden of explicitly copying your produced results back to the host, right? So you're a producer of the data, you just produce it here. As long as the latency attributes are correct, right? Overall, it's a win, right? And that's where the push is to have a low latency interconnect, so that this works out really well. And then memory buffers, where basically you have simple just memory expansion, but no processing being done on the device. Then you get a combination of CXL.io with CXL.mem. So these are different types of configurations you get. Okay.
Persistent memory would likely be
in that category. Yes, that's a good point. Yes, absolutely. Starting will be really there for persistent memory. So more simple paradigm, and there's active work in that space from software enablement perspective that we are covering here already. So I'm going to now basically pass down to you. Yeah.
So when you have a guy that doesn't show up, who has no hair and likes to swear, what do? You bring a guy who does storage, has hair, and doesn't like to swear. It's the best way to get. It's the best way to give and take. So I am not an NVDIM guy, but I love NVDIM technology, so we can certainly talk to it. And when you look at it from this perspective, the idea behind CXL, what it's bringing to the market, and how in the next slide you'll see it's valid for me to be standing up here, is that the PCIe transport's a perfect solution for a lot of what we're doing. We're looking at how NVDIMs are being manipulated and used in different ways. The persistent memory space is growing. We're seeing a lot of opportunity to use things like CXL and these different protocols with the CXL.io and .mem. And when you talk about it from this perspective, we put a DMA engine in the memory buffer. We have that opportunity to do all this over PCIe with CXL. So what do we do now that we've had all these cool ideas? We keep thinking about storage, compute, and memory all in their independent functions and features. Let's have some fun and now throw the compute concept into it. So this is where the idea of computational storage comes into play. So computational storage is one of the working groups within SNIA. I happen to be the chair of that group, a la why I'm up on stage. And we see the value in bringing this concept of computational storage, which includes the idea of a processor using persistent memory, which is what Stephen Bates' company is actually working on today, and using CXL-based NVDIMs plus persistent memory and these acceleration capabilities that are provided through the computational storage working group efforts. So you have a controller that now has compute capability in it. In the case of Iditacom, it's an FPGA. In the case of NGD Systems, it's an ASIC, but we've added compute resources into the controller that is managing some form of persistent memory, non-volatile memory, or other resources, and it's utilizing the NVMe and CXL partnership to accomplish those tasks. And that's really what we're kind of after. So computation on persistent memory in a CXL device is a great way to do that, and that's all being worked together throughout the synergies of the standards body's work between CXL, SNIA, and NVMe. So it's this concept, as it was shown on the front page, is this idea of a trifecta. So some ideas here are talking about storage-centric computation. So there's examples that have been highlighted in the use of being able to do compression offload, analytics with AI and ML. These are all different use cases that can be done using NVMe, CXL, persistent memory, and storage products all in synergy together in systems, where we're starting to pull these pieces and instead of just keeping it as a singular order of I have compute, I have memory, and I have storage, and we're starting to look at them as three independent parts that can be intermingled in ways that we've never thought of before. So instead of an inline process of going through the compute to memory to storage and back, we can go to compute straight to storage, or we can go compute to memory and memory straight to storage, and those types of things. And that's where this concept of overlapping these abilities and doing things like true DMA and other integrations of these efforts. A good example is with peer-to-peer and the CMB. Those are features that have been brought up to us by NVMe that can also be leveraged with this technology. So bringing these together is a benefit to the industry. It helps us all understand that there are new and innovative ways to look at things and be able to drive forward using a common, thank you, sir, a common interface like NVMe, PCIe, CXL, bring it all together, but at the same time make sure that it's easy for all of you who are developers to deploy these solutions, because we don't want to make it too difficult. It's all about the KISS principle, keep it simple, stupid. And so how does that affect what we're doing here in this particular space? This is the call to action. But before we get too much into this slide, we have to have a moment of silence. This will be the last time you'll hear the definition of the solid state storage initiative, because you see there's this wonderful thing called an initiative. It's the marketing arm of getting the working group guys to get together. And it's reached its fruitful limits with things like CXL, computational storage, persistent memory, all being managed by the initiative. SSSI officially dies today. So, moment of silence. What we're going to call it? That's a good question. The phoenix has yet to rise from the ashes. We have some ideas. So if you have an idea on what you would call an initiative that supports persistent memory, storage, computational storage, and or CXL and other interfaces, Marty's sitting right up here. She'd gladly take your ideas on suggestions for the new name. Meanwhile,
drink at the reception.
Or buy our free drink at the reception. So there is work being done from a computational storage perspective. We've joined the initiative along with the persistent memory teams. We're working cohesively as an organization to bring this together. We have representatives from NVMe, from CXL, all of it putting the efforts to make sure that whatever you need to deploy these technologies is provided to you in such a way that it's easy to put into practice. So there's liaison agreements between all of these different organizations, and we welcome you to join whatever we are going to call ourselves, or the to be named. So we could put up a symbol of Prince and say, you know, formerly called Prince or something, but formerly known as, yes. So at the end of the day, CXL is very valuable to the market. It's the first open interface and protocol that's being driven by everybody that's of significance in the market from a compute perspective. Intel, AMD, ARM, all of those guys, IBM, have all gotten together and said, you know what, we agree, it's time for some change, some proactive, productive change, and we're going to make that happen. You have the different ways of integrating it, so we've thought through the different process patterns. It's not just a one-time thing. We're not going to do a version of it. How can we use this in the most meaningful way? So you get your CXL.io, you get your CXL.mem, and your .cache. At the end of the day, you've got the ability to put this trifecta together. I would call it the fourth pillar of that. So three-legged stools are great, four-legged stools are even better. So since I'm a storage guy, I'll say that we could add storage into this as well, because there's opportunity to create storage devices that talk meaningfully over this process and this capability just as much as the persistent memory and the other aspects of these protocols. So CXL is definitely here to stay. We're very excited about it, even from like I said, from a storage perspective. It's a perfect solution to help drive forward the persistent development of persistent memory solutions, whether it be through NVDIMM, computational storage, or other aspects of that. So hopefully this gave you a little bit of overview of what those interfaces and capabilities are. And again, we welcome you to join the efforts to help continue to drive these things forward and make them better for everybody. So.
Right. Anybody have any questions? We got time for one question, so I'm going to go back here, and you'll have to catch me after the piece.
I have two questions actually. So the quick one would be. Okay, so I'll just. So on the persistent memory, the solutions are actually adding that TBs of persistent memory right at the host. So what are the applications which will use a memory or CXL.memory by using a memory which is attached in the accelerator? What applications will spill over the terabytes of memories and try to use the memory inside an accelerator?
I think from my perspective, I don't have a good enough answer to solve that problem for you. We can certainly follow up and get you some answers. I think Jim is ready to hop in and give some feedback.
Let me jump in on this one. It's important, and maybe didn't come through really clear. You should expect that persistent memory will be moving off of the DDR bus. It's not the best place for persistent memory. Today, it's the only place that persistent memory could be put. And instead, and as I said this morning, not all of you were here, there's, it's a perfect example is the more persistent memory you have in the system, you would want more DRAM as well. But the way, if you're putting it on the DDR bus, as you put more persistent memory, DRAM goes down, and vice versa, you're trading them off. So by moving persistent memory off onto CXL on its own, you could have the limitations we have now, where we talked about 6 terabytes of memory on a dual processor system. We'll laugh at that someday in the future, because you'll be able to have it'll be like the 127 kilobytes of memory is what you get on a PC. This is changing. So don't think of what kind of applications are going to spill over beyond what's on the DDR bus. Persistent memory will really be out there. And there's been a lot of criticism on all of this, because the techniques being used aren't completely open. CXL is designed so that everything you need to do in order to implement persistent memory, all the flushes and all that type of information, is all designed into CXL in an industry standard format. So it's a big deal.
Yeah. So
did you just cough in my microphone, by the way?
There you go. So at the end of the day, to his point, it's not about filling DRAM slots anymore. It's about where can I attach this device using the PCIe protocol. We've got chassis now that hold 24 or more, 4,800 plus PCIe attached devices. Those can be storage, those can be CXL based persistent memory, they can be all of those solutions. So again, it's disaggregating all of that into a way that we can now compose it in ways we've never thought of before.
Yeah, and I got to say, one of my favorite things that I used to say from my industry experience was the easiest way to implement software on a new piece of hardware is put that hardware on a programmer's desk and say, oh yeah, your software doesn't work. Usually works within about a month. All right, we got to keep going. So go ahead and pick them up at the break. I want to bring up Dave Eggleston now, because if we want to talk about memory, I'm not entirely sure
Thank you,
who the heck else we'd have.
Thank you, Mr. Storage Guy. Back to our regularly scheduled programming about memory. Thank you. But let's give another round of applause to Scott and Milan. That has to be really hard, like debugging somebody else's code. That's tough to pitch in at the last minute. So I like my title a lot, because going back for years on the Persistent Memory Summit here, we used to argue or debate what the media would be, and then we've had some discussion about where to attach. Now I've just heard Jim Papa's kill off DDRT. Thank you very much. Thank you. And also, we've seen the conference really move to usage, and I think that shows the nice progression in the industry overall. So I like the title about that. I'm a hardware guy. I like things that are governed by the laws of physics. Software is magic to me. So I'm going to focus kind of on a real hardware perspective. So we're going to start off with, I love DRAM. Raise your hand if you love DRAM. Oh, I know it's all of you, because your companies are buying tons of it and you're using tons of it. We love DRAM, and I appreciate Charles and then also Piotr. We're talking about how persistent memory and DRAM work together in the system. But DRAM does show some signs of age, let's call it that. And a couple things is, if we look at the decades leading up to 2010, we saw an average decline of price year to year of about 37%. Rapid price decline. But what we've seen over the last decade, not including 2018 to 2019, thank you, Jim Handy, but we've seen a very much of a flattening out of that price decline. So we're seeing the scaling problems of the technology are coming to the forefront. Perhaps also interesting is the bandwidth. And I took some numbers from J. Thomas Pawlowski, who was an architect at Micron up until just recently. And the scaling there has been pretty dramatic. Actually, bandwidth has increased at 31% per year. Now that's incredible. How did it keep up? But how it kept up was adding more channels, adding more DIMMs to those channels, and I'm going to show you that that's running out of steam. You can't keep doing it. So we're going to run into a bandwidth problem on DRAM here eventually. So one of the things we're really looking at here is, can persistent memory do the DRAM job or part of the DRAM job? DRAM is not going away. The future of DRAM is DRAM, okay? Keep that in mind. So let's jump into the media. I like this slide a lot. I took it from IEDM, from a completely different talk, because it tries to summarize the physics between the various types of media that could be used. On the far left, we have flash, which uses a certain physical effect, and then all the way to the right, where they've tried to summarize that. Now, I mentioned that we used to debate on the right-hand side here which sort of technology would win. And I personally became very tired of those discussions. And I think we do have a winner in the near term in persistent memory. And I'm going to talk about that in a minute. But there is something new up here. And I don't know if you noticed that. There's ferroelectricity up here. But this is not your grandfather's FRAM. This is something a bunch of guys in Germany and Qimonda discovered a few years ago, that if you deposit what's called a high K dielectric in a certain way, it's actually pretty tricky to do, but it demonstrates a ferroelectric effect. I had some involvement with a company a few years ago that's published a paper at IEDM, and we've seen at IEDM the investigation of this go from about 3 papers to last IEDM there were over 30 papers on this effect. So this is something brand new. Now, don't get excited. There will not be this type of ferroelectric chip in the next 5 years. Okay, there's a long way to go. But it does show that physics and material science continues to move forward on memory, and there are new ideas, etc. Very interesting, this was in the plenary talk by Intel. It kind of shocked me about what's called a 1T1C ferroelectric Hafnia bit cell, and that's showing some pretty good results. It's got farther to go on endurance, but it offers tremendous promise in terms of giving a semi-volatile or somewhat persistent memory. So keep your eyes on that. So that's something that's brand new. Now, what do we like or not like about each of these technologies? Well, we all know that NAND flash is just too slow, but we love it because it's cheap. But if we go across here, the ferroelectric one that I just mentioned is very fast, and it could be very cheap, but is way too new. If we jump to MRAM, MRAM has been well studied and commercialized actually for quite a period of time. And the foundries have certainly adopted it, but as an E-flash replacement technology, but it's way too expensive. We really have not seen MRAM getting out as the niche area in terms of being a standalone persistent memory. RRAM honestly has been pretty disappointing. There has not been good advances in RRAM, either as an embedded memory or as a standalone memory. Companies are still trying, but we haven't seen those results. So then we come to phase change, and yes, 3D XPoint is rebranded phase change. Some of you might remember I did a talk with Jim Handy and Tom Coughlin back in 2012, and I did get the audience to chant that 3D XPoint is rebranded phase change. But it does seem to be just the right technology. Don't take my word for it. The rebranded Toshiba, which is now Kioxia, they talked at IEDM last December about how phase change, yeah, they kind of admitted it is the right technology right now for persistent memory. But how do we use it? So I'm going to get into that a little bit later in my talk. Now, who's doing what? I like being an independent consultant because I can talk about things like this. And this gives you a pretty good idea of where things are being done. Certainly over with 3D XPoint, Intel, and now Micron have their own technology. They got divorced here recently, so they'll be going on different paths in the future. SK Hynix has published a paper on phase change. So we expect that at some point they'll introduce it. And I guess I should remove the little dotted line, which means it's a rumored activity around Samsung, because at Supercomputing last November, I saw something where they claimed that in there was a Samsung phase change chip. So we do see the heavyweights in the memory industry here. RRAM, I think, as I mentioned, has been pretty disappointing and is pretty empty in terms of the big guys working on those technologies. What we see with MRAM, though, is it's well adopted in the foundries, but as mentioned, that really goes into that embedded memory technology. And finally, for that new ferroelectric high-K dielectric, Intel, we saw that had a paper there, and there's some rumored activity at Micron and SK Hynix as well. So look for that one in the future. So let's go on to attachment. The guys before me talked about this. They clearly have a love affair with CXL. There is more in the world than CXL, and we'll come to that in a minute, although it looks like a pretty good option. I took this slide from HPE presentation at Supercomputing, and it really talks about if we have this sort of memory, how do we attach it? And their point is, there's tons of options, especially even as you get below kind of this 500 nanosecond breakpoint. There's a lot of options of how to attach things. But most of the things up there are DIMMs. And what are some of the problems with DIMMs? Jim talked about it in one context. If I plug persistent memory in, I have to unplug DRAM, or I have to plug a more expensive DRAM module in. So it didn't always make economic sense, or hasn't always made economic sense, to plug persistent memory into your system on the DIMM slot. And if you look at this diagram, this is one from the JEDEC training class for DDR5. Wow, what are we doing here? That's 16 memory channels coming out of the processor with 16 different DIMMs, and now we're even putting 2 channels for each DIMM. So this is not sustainable, and that's one of the messages I want to get across, and that's why I talked about the bandwidth for DRAM has had a very nice consistent increase year to year, but it's going to at some point start leveling out. So if we think beyond the DIMM and we look at other ways that we can attach memory, and we can attach memory with a lot of bandwidth, that is opening up a side channel which is also coherent. And that could be CXL, or it could be IBM's OpenCAPI, or it could be Gen Z. So that's what we see going forward, is having this side channel is a great place to do that simple job of memory expansion or other things. And I'll talk about that in the future, in my talk here. Okay, so if I go back to the presentation I stole from on the HPE guy, I just talked about the direct attach. Direct attach to the processor could be over CXL or OpenCAPI or Gen Z. But there's some other opportunities here as well. And he points out, especially down here, opportunity number 2 is to have that pooled or composable memory. In other words, some place where we pool memory together that those individual nodes can grab memory from that. I thought the Andy Beckelsheim presentation this morning, although his clock rate must be running at about 4 gigahertz or faster, I found it hard to keep up. But he did make a great point that if the network is fast enough, then it doesn't really matter where data resides, and you can move it around. So we could have our data in this pooled location, and it doesn't have to be bound to the node. The other opportunity here is through a switch, and that could be a Gen Z switch, or could be another technology switch, and give us that high degree of connectivity. So let's keep those ideas in mind. So if we look at who's doing what, I think the prior presentation made this point, but the one problem with CXL is you can't build anything and hook it up today. And that's going to be another year, or maybe 2 years. We'll see how it all goes. So there are things that exist today. So Arthur's right here. Arthur, go ahead and raise your hand. Arthur from SMART, and there's other SMART representatives here. If you go out to their booth, you can see the very first serial connected memory device, which is OpenCAPI, and that is specifically done for IBM, and SMART builds that for IBM for their new open power systems. Gen Z, SMART also builds, as well as Samsung and SK Hynix have shown, building memory modules or modules that have some level of compute in them that talk over the Gen Z interface, and those interface now to HPE and Dell servers. So those opportunities are there, but we do see that momentum behind CXL, and what I expect, just like I think Jim Pappas, did you announce a new Intel product, CXL? Persistent memory? Okay, that's what I thought I heard, but maybe I was wrong about that. But we should fully expect that. We should fully expect the memory companies to do that, and we should expect them to do it not just with persistent memory, but also with DRAM. Because again, it's DRAM and persistent memory together that make the compute system work. I'm not going to talk about some of the other options here because I've kind of made my case for why you would not use the DIMM, but you would use that side channel instead. Okay, let's finally go on to usage. And again, I'm a hardware guy, business guy. Software doesn't always make sense to me, so I'm going to kind of take a different approach. I'm going to make the point that what is it about persistent memory? What are the applications we should look for that make good business sense? Now, my friend Jim Handy, he did a webinar last week where he said persistent memory without using the persistence is useless. And I wrote that down. I thought that was a little harsh, because I'm not sure it's useless, but I don't think it has a good value proposition. And Jim also, he'll sell you a very nice report that'll tell you that Intel, in pursuing 3D cross-point persistent memory and selling into just a more memory value proposition, is a great way to lose a lot of money quarter after quarter. So that is not a good value proposition. But there is a good value proposition, and we're starting to see it emerge. I think we started to see it here in 2019. Things that are persistent and coherent, things that value persistence and coherence. That takes full advantage. Intel goes to a lot of trouble to engineer persistence into persistent memory. Please use it. So where are places where you'd use it? And this is a slide Arthur presented from, which actually came from VMware in the past. And they talk about, well, let's collapse the tier. Let's collapse the highest tier of DRAM and NVMe SSDs and put both our hot and warm data into that one tier. So that's a good usage of persistent memory and collapsing that tier, because we value the persistence in that case. And it also can be coherent with the memory subsystem of the processor. So good example. So let's go a little bit further. Intel and OG talked about it this morning. He gave you the Cassandra example. And one thing he didn't tell you was how much does that accelerate the processing, how much advantage that give you. And so what Intel shows is that with Optane persistent memory and using app direct mode versus just using an SSD for Cassandra, they get a 9x performance gain. Okay, so that's pretty fantastic. Now we're starting to see a real benefit in performance. Now finally, the one thing I have not personally seen until last week though, is somebody make an argument, an economic argument, a business argument, why would I use Intel Optane persistent memory? And that was, this is a busy chart, and I'm going to give a shout out. Jing's all the way in the back, so Jing, go ahead and raise your hand back there. Jing's from Formulus Black, and they gave a presentation with Lenovo and with Intel last week where they gave an economic argument. And that argument was for a particular workload. They came down to how much money per transaction does it cost, even considering the added cost of persistent memory in the system. Now that's a business argument. That's an economic argument. And for me personally, that's the first time I've seen that. And that's exciting to me. So we're starting to see these applications. What are some things to look for in the future, though? I've talked about one already, and I want to do it in this context. This came from a supercomputing conference last November. All the major supercomputers are heterogeneic. Now, I'm not even quite sure what that word means. It's a great SAT word, but I like pooled, or composable. There's so many words to describe this, but if we pool our resources, and the point is that those supercomputers pool the processors, they pool the storage, everything is pooled. Memory is not pooled. Memory is still bound by nodes. So let's start looking at pooling that memory. And we've seen that. We saw that in the earlier slide, and that's why I pointed it out. So even HPE is looking at what are the benefits of if we pool this memory. Now, how do you connect that? Let's just keep in mind that CXL is great for inside the box. Gen Z is great for outside the box. And Gen Z is an actual fabric that connects things together. So what I see going forward is this could be a Gen Z memory appliance, pooled memory appliance that integrates very well into the data center. So finally, I stole this slide from my friend Stephen Bates. Can we spread a rumor that Stephen Bates is patient 0 in Canada for the coronavirus? I think I'd like to do that. Let's just pick on him and see if that's the reason he's not here today. But anyways, he has talked about, and then Scott Shadley talked about this combination of compute plus memory, and also Milan talked about it as well. This is a very interesting application. Now you have those compute resources next to memory. Why don't we use it for computational memory? Should this be a new SNIA initiative or under the SSSI? And Charles Fan from Menverge, his marketing guy, needs to get on this and give us a name. But I think this is an opportunity for SNIA going forward. Okay, so finally to wrap up, 4 things I think. I love DRAM, and it's got some problems. So watch as both the technology scaling and the price scaling gets worse. I think that's an issue on the horizon here. 3D crosspoint and phase change is still the top media for the job, but I think watch this ferroelectric high K. That has some opportunities going forward. The DIMMs, we heard it from Jim earlier, but DIMMs are not a great place to add persistent memory. There's really some drawbacks. So opening up this channel with CXL, I do believe will become the primary attach for persistent memory, and then also some DRAM as well. And that gives you a big bandwidth increase, by the way. And then finally, we have to have applications to drive the business that value both the persistence and the coherence. So pooled memory appliances and computational memory are 2 things on the horizon that could do that. Okay, and then finally, this is my commercial and how to get in touch with me. Thank you.
Thank you, Dave. I think we have time for 2 questions. Who has a question? He's not that perfect. Who has a question? You must be.
I'll mic drop. No.
Oh,
Go ahead, sir. I think you had a question from the last session, too, so might have to call in some help for this one.
Good presentation, thanks.
Thank you.
Good to get more of an objective view there. So on the, like you're saying, smart modular, and we're seeing some other buses. So OpenCAPI at the moment already is in production. The OMI DIMMs are available. So people that are really excited by CXL could certainly benefit from experimenting with real hardware today. They don't have to wait a year or 2. Any comments on that side of things?
I completely agree with that point. And C6 I didn't mention, but C6 also exists in prototype form in some popular server processors. Yeah, it's a great way to build hardware today and learn from that, whether it's C6 or OpenCAPI or Gen Z. And I think some of the companies are starting to do that, because I think that puts you in a good position. The 3 exciting things about CXL are Intel and open standard and Intel. And it's because of the market reach, and give Intel a lot of credit for opening that up. I think Jim alluded to it, that there had been some criticism of Intel not opening up on the DDRT on the DIMM bus, but to open up with CXL, I think is going to really enable more opportunities for this space. Okay, thank you.
All right, excellent. Another hand for Dave.
There was one more.
We'll get you. We're going to keep moving. So, okay. So we'll go to the next. So Dave, I thought, asked a very good question there, which is, well, how are people going to use persistent memory? We've seen a little bit of early enabling or base layer level enabling here in the morning. The next three topics are really, this is how we as companies are using persistent memory. So the first person I want to bring up is Pratap Subramanian, and he's a VMware fellow. He is also a Pearl Conference speaker alum, and we'll talk more about that later. But he's going to come up and say how his team has been actually looking at persistent memory and what uses they found out of it. So please welcome Pratap.
Hi, sorry. So I'm Pratap Subramaniam, I'm from VMware. You guys are probably wondering what VMware has to do with persistent memory. We are a software company. We think of ourselves mostly as an operating systems company, where we build a layer of software that acts like an operating system for the infrastructure. Okay, so persistent memory for the first time provided a path where applications directly from CPL3 or at user space would want to manipulate the device. And so this is a very good opportunity for us to figure out how to get applications on board on this device. So this has been a journey for a number of years, and I just want to kind of take this as an opportunity to kind of share with you what we have done, what we have learned, and what we think is ahead for persistent memory. So VMware's view of persistent memory actually falls into three large buckets. In the first bucket, we just look at it as yet more RAM, slower RAM, just a higher density RAM. Okay? And now somebody said that that's useless. I actually don't think it's useless. It's a beautiful way to get your applications on top of memory that's prolific. Like, think about this, a large number of problems in computer science today are caused because you cannot fit the problem onto the hardware device. So what you do is you shard the problem. You split it into multiple pieces. And then you have this beautiful problem of keeping them all consistent. Okay? An entire space of distributed systems has been caused simply because we cannot have good scale up in your hardware devices. Now, if this is a way in which we can actually fit our problems into a single device much more easier, then why not? Right? So I actually believe a large number of people, customers, will actually consider adopting, say, the Optane persistent memory DIMM or any of the other commercial products that come about, and just attempt to use it as RAM initially, because it doesn't require any particular operating system change or any other software change. So it's a beautiful on-ramp into accepting the technology. And over time, I actually believe that application developers and architects will actually look at this and say, hey, if I can have a terabyte of RAM, then the previous decade of solving distributed systems issues and maintaining consistency and coherency and eventual consistency and all of that complicated stuff goes out the window. My application becomes simpler. So they will actually attempt to evolve their applications in that direction. This, of course, has very little for us to do at VMware. We just realized that this is a possibility. So when we have a conversation with our customer, we'll say, you know what, just why don't you try the DIMM, in memory mode and see how it floats. The second large way in which I think persistent memory will get adopted is just as fast SSDs. Okay? So there, once again, the customer will not exploit the byte addressable property of these DIMMs, but they will use it in the blocked mode. So in their software stack, they look at it and say, well, I'm not going to change the applications, but I'm willing to change the operating system. And that's where I'm going to stop this time. I'm going to buy this new device. I'm going to treat it as a very fast block device. And then I'm going to run the appropriate driver in the operating system to make use of that. But I'm not going to really expose the byte addressability of it. That's the next level of adoption, I think. And the third and the most adventurous sort of path is where you say, look, I'm going to get myself a new operating system, and I'm also going to upgrade my application to directly, from the application, manipulate the persistent memory device using direct loads and stores, since the device allows you to do that. Okay? But it requires you to modify your application. So it is not something that a large number of customers will jump into right away. Right? It's going to be many years of just playing with the device, getting familiar with it, getting confidence and trust and all of that stuff before they get there. Right? And inside VMware, we focused on one thing that we do really well for every new device that comes about, which is to virtualize it. Okay, so we couldn't really predict which way the world would go. So we said we will virtualize this device and we'll give you first-class 100% support for persistent memory in an ESX virtual machine. Okay? So you could take any persistent memory program today that's either working in block mode or in byte addressable mode, and you can run it inside a virtual machine, and as long as there's persistent memory in the hardware, it will actually virtualize it for you, and your program should work. So that was first things first for us. We just wanted to virtualize the persistent memory. And today, this is available. It's actually available in our product. Okay. And after that, we focused a large amount of our energy on onboarding applications in the byte addressable mode. Okay, we wanted to take the long pole. We wanted to convince people that that was the right thing to do and so on. So we spent a large amount of energy on that one. And as we started talking to various people about that journey, about why would they want to use byte addressability, why not, and so on, three questions kept coming up constantly. One is that, if you look at block mode, something that has been optimized for 3 decades, operating systems, devices, and translation layers on top of devices and so on have all sort of cooperatively figured out how to hide the latency of that I/O very nicely. Doing better than that is actually quite difficult. It's a path that has been optimized for 30 years almost, right? Suddenly coming and saying that you're going to do better than that is actually not an easy thing to do well. And so there was a lot of skepticism. When we would go talk to customers, they would say, well, really, is it really better? Well, let's think about this. I would go and flush data to a device in big 4K chunks, but I wouldn't do it all the time. I would do it maybe once every minute or so. And my performance seems perfectly fine. Now you're telling me that you're going to flush your cache lines every time they get modified. Can you give me a sense for the memory bandwidth explosion that's going to happen as a result of this? So there was a lot of questions about whether there's even performance to be gained in this model. So it's like you brought this device 100x closer, but now you're getting more chatty. Right? And so it wasn't really a clean trade-off. It was not very obvious to us that by bringing this device 100 times closer, we've actually made things better. Okay? And then when you do some things infrequently in block mode, that piece of code can be segregated in your software. When you're writing a key value store or when you're writing some in-memory database, most of your code is about the in-memory database, and every so often you might go off and try to flush what's in memory to the disk. The people who write that piece of code are not the core engineers in your team, okay? And they're off writing in one file out of 50 files in your source code, right? The path that actually writes to the disk. So it's out of sight, out of mind. When you're looking at your code base, you're looking at it as an in-memory database code. It's not, all this I/O path is not hitting you in your head. But with persistent memory, every time you update a hash link or a linked list or something like that, you have to flush it out. So that piece of code is now front and center. So if you actually look at an in-memory database in this new world order, there will be plenty of persistent memory updates constantly all over the place, unless it's somehow hidden cleanly for you, right? Now there are many libraries that exist to hide some of these things, but they're still kind of nascent in their powers, right? And then comes crash consistency, which is another evil thing. Like if you have a linked list update that you need to make, and you need to update 2 pointers in a transactional manner, and power goes off in the middle, you need to make sure that either both the pointers have been saved or neither have been saved, right? The problem is when you go to a piece of source code, 50, 60,000 lines of code that someone else has written, and you now upgrade it to become persistent memory aware, if you miss one of those updates, figuring it out is a pretty difficult problem. Because now you've got to crash the system several thousand times in various random fashions and figure out where what went wrong, why didn't you catch that one store of a pointer, and so on. So there's actual practical engineering issues with taking large volumes of application software and try to make them use persistent memory, right? So what we did was, since there was a lot of doubt about whether all these things would work out in its favor, we started one at a time. We said, look, is the performance really there, right? I mean, I couldn't stand here and convince you that, sure, the performance is there. You brought this device closer, but the chattiness is okay. Don't worry about it. Even if you got 3 times more chatty, you'll still be fine. I'm not able to give you that feel. There's no gut in me that actually tells you that, right? So we actually ran an experiment. What we did was we took a full-fledged key value store, which is written in C, and it's open source. So we actually took that key value store and we modified it by hand to introduce transactions and to introduce logging of all persistent memory variables. And we put the entire key value store in memory. Okay, and we turned it into a byte addressable piece of software. It was about 50,000 lines of C code. And it took us about 7-8 months to do this. And we wrote our own transaction library. So basically we modified the C code. It would make calls to this transaction library that we had developed. And all of this took us about 6 months to do, right? And thankfully the performance was there. Okay, out of the gates, we got performance improvements. So the lower graph there you see is that same key value store running with absolutely no modifications straight out of the master branch, and but it saves to SSDs. Okay, and the top curve is with our modifications in it. Okay, where now it's pretending to be a byte addressable key value store, talking to persistent memory DIMM underneath, and modifying this DIMM from user space. Okay, so this is the kind of journey we expect our customers to go through, or an application developer to go through, in order to actually consume persistent memory from user space. Right? So I was very happy the performance was there. We could actually do the analysis on this thing and figure out that yes, the chattiness had gone up, but it hasn't gone up to such an extent that it overwhelms the benefits gained by actually the lower latency. Okay. But the whole experience was basically hard. Okay. Like I said, it's very difficult to debug a problem where you missed a store instruction and you didn't put it into a transaction boundary. Okay. It's just an incredibly difficult problem to debug. So identifying transactions is a key thing, right? And second thing is, persistent memory, volatile memory is okay once in a while to leak. If you didn't free some chunk of volatile memory, it's like not the end of the world. But with persistent memory, it's actually bad to leave behind persistent memory on your heap. And then logging, we actually introduced it manually. So we would actually say, when you say x equals 5, we will actually log the old value of x. And then we'll change it to a new value and all of that stuff. All of that insertion was just very, very brutal. We just didn't see ourselves standing in front of our customers and saying, oh yeah, you have 100,000 lines of C code. I think this is the direction you should go. It's just not something we could do it honestly, right? So what did we do, right? We sat down and figured out what is it that's needed to have a successful conversation with our customers. And it just became abundantly clear that we just needed to build the ability to manipulate persistent memory in a simple way right into the language. Okay? I mean, just like C allows you to do, put stack variables and heap variables, have integer, character, and unsigned, and all of that good stuff, maybe it should have persistent data types. Okay? Maybe it should let you manage persistent memory directly from the program. So that's where we started. Okay? And then we had many conversations, and we started playing with Golang, because Golang is an open source piece of software. Everything is open source in Golang. It's a very vibrant community. And we started modifying the Golang library. It became very clear to us that introducing a new persistent data type was the wrong thing to do. For instance, if you have a library that you have written and you have managed over the last 20 years that, say, takes 2 trees and blends it into a single balanced tree, it's taking 2 pointers as input. Now, you don't want to suddenly say, oh, well, that code doesn't work anymore because I have introduced a new pointer type called persistent pointer. And the old code doesn't know what to do with this persistent pointer, so it will just not even compile, right? That sort of stuff is just wrong. And the second thing is we noticed a few people going in the direction of taking a persistent pointer and turning it into a fat pointer. Okay? It's not really a virtual address anymore. It's more than a virtual address. It has some metadata associated with it. And that, to us, was also not a wise idea. We wanted to go for an approach with this tremendous amount of code reuse, and a pointer is just a pointer, right? We wanted the compiler to generate the logs for us. So the one thing I was willing to do as a programmer was to say, here is my transaction start, here is my transaction end. Everything in the middle, any accesses to persistent memory, the compiler should generate the logs for me. Okay, I shouldn't have to do it. Okay. So we went with all these sorts of goals, and we wanted to say long-running applications, short-running applications. If the persistent memory needs to be expanded over time, the language runtime should take care of it for us. If we have to give up persistent memory because we're not using it, the language runtime should take care of it for us. And if the language is a garbage collecting language, it should just garbage collect persistent memory also. So there was a lot of, we thought through this carefully, and Golang basically fit the bill. Because it does have a very, very nice, powerful garbage collector already. And so we went ahead and started modifying Golang. We added all of the support for transactions, all the support for logging, all the support for heap management of persistent memory, and the garbage collection of that memory, and so on. And it was a reasonably enjoyable experience modifying the Golang compiler. And then in order to actually convince ourselves that we have built something that's useful, we actually ended up writing our own version of Redis key value store, but this time in Golang. Okay? And this new version of the key value store that we wrote did practically the same things as a C version of the Redis key value store that's out there in the wild. But we can compare it with our compiler this time. Okay? And all of these changes that I'm talking to you about, they're all open source. Okay? So you could take this Golang compiler today that I've just described to you and use it for your Golang project, fork it, add value to it, whatever you want. And it's a full functional Golang compiler. Okay? And when I say full functional Go compiler, I'm actually talking to various projects inside VMware where they're actually starting new projects in Golang. and telling them, hey, maybe they should start using this compiler. Okay, so it's ready for business, right? So with this compiler, I'm going to show you the same data that I showed you before. The top line, out of the gates, that's what we got with our Go compiler. Okay, so this new version of Redis written in Go is a lot easier to understand. When you look at this Go code, it actually looks like an in-memory database code. It's not, none of the persistent memory things hit you in your face. So you could do your job well at this using some compiler tool like this. So where I'm going with all of this is that the device seems to have the performance. In my opinion, once you start using byte addressability in your application, what you'll suddenly start seeing is that there was a piece of code in your software that would do the periodic flushes to the SSD and so on. That whole chunk of code disappears. Okay, there's no need for that chunk of code anymore, and that saves you many thousands of lines of code in your software. And then instead, you're now saving and flushing on practically every load and store, but then you are not actually doing it. The compiler is generating the code for it. So there is practically no code that you have to manage to do this state management, in a sense. Okay, so it's a win-win-win all around the board. Okay, so highly encourage a compiler language support for this thing. Now we tried Golang because Golang was open source. Presumably there'll be other people who look at C and Java and Python and all of that stuff, and I know there's efforts going on in that direction already. We will work with the Golang community to make sure that what we have done gets upstreamed as quickly as possible. We've already started talking to them, and there is some level of enthusiasm about it. But before that, I think we will have other VMware projects starting to use it and give us some feedback. So that's pretty much it. I wanted to share with you sort of a software journey, right? Any questions?
So I have the first one. I don't quite remember the answer, but I want to ask it anyway. And the last time I saw you do this similar presentation as this, you mentioned the size of the team that actually you put on this. So how many people did you actually have on this?
Yeah, well, so the one thing that is, this persistent memory journey has been going on for a while. So my team actually had a complete 100% turnover before the first device showed up. Right? So the first C Redis code was written by 2 people. Neither of them knew the C Redis code base. So they made mistakes when they instrumented this code base, and they suffered through the debugging of it. But it wasn't easy to debug it. Okay. And then, so they wrote the first transaction library, the logging library, and so on, those 2 people. Now I have 2 new people. Both of these guys have taken on the charge of rewriting the compiler from scratch. Neither of these guys are compiler guys. So they learned what SSA face was, and they introduced a new SSA face in the compiler and all of that stuff. So it's been fun. We rewrote the transaction library a second time around because we realized that we were not doing many things right. Now it's actually fairly optimal with the way in which it logs and keeps decides when to use move-nt and when to use CL flush and does the coalescing and a whole bunch of things. Yeah.
I think we got time for one more.
Yes, this morning we heard in the PMEM presentation that typing was a good idea for programming persistent memory, and you seem to think that that's not a good idea, but you want the compiler to generate all the logging code. So how in the Golang extensions does the compiler know that it's referencing persistent memory without examining every reference at runtime?
Okay, so let me give you a few steps about how that happens. At the beginning of the program, we have a package called PMEM that we ask the Golang program to import. And then there's an API in that package where you can say, initialize me a certain amount of persistent memory. I kind of think I need 100 gigabytes of persistent memory, but I don't know for sure. That's the kind of statement you would make. So it will give you a certain amount of persistent memory from the system. And then you can add to it some named objects. And the beginning and end of that persistent memory region is a virtual address region into which no other object is going to show up. So if your pointer is between the beginning and end of that persistent memory region, then the compiler by default assumes it's persistent memory pointer. Okay. So, right. So this doesn't come without cost, but the cost is all compiled away. So the comparisons of these pointer comparisons and so on and so forth actually goes through the compiler optimization phases. And you might find yourself optimizing many of those checks away because it's a check on constant boundaries. Right? No, it doesn't assume a static pointer. I mean, you just have to do a bounce check on the persistent memory. No, you don't. I'm not saying that the check can be eliminated away. The check can be commoned away. If you have multiple such checks, you'll find that there's a lot of opportunity for you to coalesce the checks and then coalesce the code underneath it. You should see the kind of compiler optimization code that we generate for this thing. We spent some time thinking about the inefficiencies there.
And you can, because the links are all there and it's all open source. So it's, I want to get to the next one. Let's thank Pratap. That incredibly thoughtful presentation. Thank you. She has a really interesting implementation that has been gone on here, and so I want to turn it over to you to wow the audience for all the cool stuff going on in Exadata. Thank you.
Awesome, thank you. Thanks, Jim. Hi, my name is Jia. I work at Oracle, and I lead the Exadata development team there. And I know for the prior 2 years at the Persistent Memory Summit, we had our colleagues came over and then gave presentations, but I was just busy, heads down, working on the PMEM. So this year I get to come today because we actually had released the product, and I'm really enthusiastic. Oh, thank you, Andy. Yes, been working really hard with Andy for the last 4 or 5 years with Intel. So personally, I'm really proud of what we have accomplished, and I'm super excited to be given this opportunity to talk to all of you here about what we did with Exadata. So with that said, let's go ahead and get started. I don't know how many of you here have heard of the term Exadata. If you haven't heard of the term, raise your hand. Oh, wow, okay. There are very few hands, so maybe you didn't want to. So I am actually really surprised because I thought, this is more like, we have hardware consultants and, all the, CXL discussions and whatnot. It's like, maybe not too many people know about software. So I actually put together some slides to give you guys a quick overview of what is an Exadata. So Exadata is an integrated, fully engineered system where it runs the database workloads. And then what we believe is that it is actually the best platform to run your Oracle database. So to accomplish that goal, we put together 3 things here. Number 1, we get the best database hardware that's out there. So which means that we actually coincide with the Intel, the tick-tock schedule. So whenever Intel comes out with a new CPU, we release a new generation of Exadata, along with lots of other goodies I'm going to show you in the next slide. And then more importantly, since I'm a software person, I believe what we really is able to sort of bring to our customers is the smart system software that we have built on top of this amazing platform. And last but not the least, it's a shipping product. We are, like Larry Ellison is, Oracle CEO. As probably everybody knows here, he has called Exadata as the most successful product that Oracle has ever done. So we are like $1 billion business. We just celebrated our 10-year anniversary, so we have a long history. And then we have the whole, automated management for our customers as well. Okay, so this is what an Exadata actually looks like. So I have like a full rack of Exadata there. So in the middle with those blue boxes are our database servers. So these are the Intel 2-socket database servers where the actual database, the Oracle database software runs on. And then in between those, the blue sandwiches in the middle, the patty, we have our internal fabric. So right now, what we have just recently released is these 100 gigabit RDMA over converged Ethernet, so Rocky network for internal fabric. And then at the upper and lower, the orange boxes are the storage servers that we have. So most notably on the storage side is that I'm here, is we put persistent memory in our storage server. So for every single one of our storage server, we put 1.5 terabytes of persistent memory in there. And I'm gonna tell you how we use it and why it's really cool. Okay, and this is another variant of our product. So this is an 8-socket server. So for the customers who prefer to deal with less database nodes, they can choose this larger SMP processor model, but everything, the storage, the network, the software are exactly the same. And we talk about scalability. So it's not just like a small bunch of servers form a cluster. Exadata is scalable. So you can start small with the 8th rack all the way to multiple racks. It's very elastically. You can grow that elastically that way. Okay, so enough about Exadata. Hopefully, haven't bored everybody by this point. So I like to wake everybody up because I know I'm standing between you and the next coffee break. So let's just, wake up and answer a question. For all of us here, I think a huge audience also go attend the other summit, which is the Flash Memory Summit, right? So what happened in the last decade? What we have seen from Exadata point of view is that we really went through a flash revolution. So let's take a look at what are all the shipping models of Exadata. So as I mentioned, we've celebrated our 10-year anniversary a couple years ago. So we started out in 2008. And that's not too interesting. The first generation of Exadata where we actually started shipping with flash is in 2009. And if anybody remembers, everybody talks about CXL in the future, NVMe. Back in 2009, there was no NVMe. So even if we had flash, we had to live behind a very slow interface, the SCSI interface. But that did give us an opportunity to provide a very powerful OLTP story for our customers. So for those of you who may not be very familiar with databases are mostly like 2 types of workloads. One is called online transaction processing, OLTP. The other is analytics, like data warehousing, lots of scans. And then what the most distinguishing factors between these type of 2 workloads are the I/O patterns. So for an OLTP application, you see a lot of random IOs. It's like you go to your bank. You say, I'm going to transfer some amount of money from account A to account B. So when that translates into the database, what you get is, you walk down a B tree index, move down, through some tree, do a bunch of random IOs, and finally get to your account. So that's why flash is very important for us because of the characteristics that flash brings us. I know people talk about flash being slow, but compared to disk, guess what? Flash is actually really fast. So it's a really nice storage solution for us where we actually build on top of it. We have flash cache, we have flash log to accelerate like a lot of those OLTP use cases. And then let's kind of quickly move down the years, fast forward to, I think that's 2014, end of 2014. So that is when we started shipping the first NVMe product. And as you can see, the Moore's Law kind of, sort of worked out really well for us in that sense because NVMe was a brand new interface back then. And it was like almost twice as fast as SCSI. So that really allowed us to unleash the power of flash. And then in return, we had like much higher scan rates for analytics workload, and we have much higher, like doubling the read IOPS, the random IOs. So we really like flash. But then what we have noticed in the recent years is that flash seems to be plateauing. Like our random read IOPS is high, these are in the millions. So for a full rack, you're getting, 6 million read IOPS. Okay, that's really good. But we haven't really seen much improvement in the last few years until what happened with September last year is when we actually released a product that I was previously referring to that I was working really hard on. That was the product with persistent memory. And then with that product, we're able to actually look the jump from like a 7 million IOPS to a 16 million. Also, we're able to get to a 19 microsecond latency. And note that it's not a local PMEM access. It's actually over the wire to another computer. So how did we do that? What was the secret sauce in the latest product that we just released? Okay, now it's the time for another question. Do you guys recognize this dynamic dual? Anybody have any guess? What are the two icons I put on the slide? Raise your hand, don't be shy, just shout out. PMEM, all right, the left one, I agree, it's PMEM. What about the right-hand side?
100 gig Ethernet.
100 gig Ethernet, very good. Although it's 100 gig Ethernet, but with, exactly, there we go. You won the prize. So first, let's talk about persistent memory. In this case, the persistent memory, everybody knows it really well, right? This is the Intel Optane Data Center Persistent Memory Module. We use that in our product in the storage servers. The capacity, the performance, and price is, nicely sandwiched between DRAM and flash. And then we have found, as we have, worked on the product, that the reads are really good. It's at memory speed. Writes are really nice because they're actually persistent. We run through, loops tests of power failures and cycles and whatnot, and then convince ourselves that, look, Intel actually really did deliver on what they have promised. They are really persistent. As long as you know how to make them persistent. Because we went through a journey of learning. It's like I'm sort of echoing the prior presentations to make sure that when you write or store to a persistent memory and making sure that write is actually persistent, made into the ADR safe domain, I don't say it will require a PhD, but it requires some study and work to make sure you get that right. So we don't want our customers to have to deal with all of that. We just want them to have better database performance out of box with persistent memory. So our software kind of takes care of all of that detail inside. All right, so that's number one, PMEM. The second piece, RDMA. So just a quick sort of refresher on what is RDMA, remote direct memory access. So how does that work? You need two computers. And one computer would be the initiator, the other computer would be the target. And then both initiator and the target will map their memory region onto a RDMA-enabled NIC card directly. Once that's done, you create a connection between those two endpoints, and you're able to do remote direct memory access without even involving the CPU or the OS of the target. So that's a technology, and we actually have been using it for a very long time. In fact, we started using RDMA when Exadata was first released. So we had our network fabric back then was InfiniBand because there was no RDMA on Ethernet. And so that was a very obvious choice for us. And we had used InfiniBand with RDMA for primarily low latency and high throughput, to harness the power of RDMA. But now, when we look at the persistent memory, what we have realized is that a lot of the databases, our customers are looking to cloud. What they really want is the ability to kind of run their workloads on their on-prem, as well as seamlessly move their applications to the cloud. And if you walk into any cloud data center, do you see InfiniBand there? Not really, right? Because it's Ethernet. Ethernet is everywhere. So for us, if you can do the same performance, 100 gigabits, both IP or Ethernet, which one would you choose? It became a no-brainer, right? For us to be able to sort of get into the cloud space, it's much better if we kind of cut over to use RDMA on the converged Ethernet, and this is what we did. So as I have told you, RDMA is great. It gives you high throughput. It gives you low latency. But why do I put these two together? What are the special chemistry that they can create when they get used together? So to answer that question, let me give you a hypothetical scenario first, which is how would you use persistent memory in a traditional storage sort of environment? In this case, I'm talking about a storage that's connected via a network to your database, for example, because we really wanted to have a shared storage architecture to allow us to be able to scale, as I mentioned in the prior slides. So a hop over the network is unfortunately inevitable. So you cannot optimize that out, okay? So with that in mind, if you do just the most simple thing, you put persistent memory into a storage server, you continue using the same I/O protocol you use today for a database to access a block, what would you get? So instead of picking on our competitors, which I don't know if they're in this room, I'm going to pick on myself. So I'm going to talk about what a conventional read, meaning before PMEM showed up on Exadata, we had this amazing technology called Flash, right? So I'm going to pick on that. Let's see how a conventional read from Flash works for Oracle database on Exadata. So on this picture, let me see if I can use a pointer. Yay. So this is a database server there. So that's where the database software runs, and that's where, in my prior example, the banking application, where, we walk through an index tree and trying to fetch my account. So let's say the page that contains my account information is not in the buffer cache of my database. What do? Well, I got to go to storage and read it, right? So very simple. On the right-hand side, I have a storage server here. So that's where the data resides. First step, the database figures out what the heck is my page, right? Where is it? So when you talk to storage, you say, okay, this is a disk I want, this is an offset I want, this is the size of the I/O I want to perform. So what do we do inside the storage? The storage process wakes up, picks up a message, say, oh, somebody sent me a message, let me figure out how to perform the read. So first thing what we say is that to accelerate OLTP, reads are extremely important, right? Because when you look up something in an OLTP application, and if that particular block is a miss in your memory cache, in your buffer cache, you got to perform I/O. And that typically is a random I/O, random read. So random read is hugely important for OLTP. In this case, what we say is, look, we have flash. We have 25.6 terabytes of flash in each of our storage server. Let me put the hottest data on flash. In case the database has to come back to read the same hot block again, instead of having to endure this painful miss in the flash and go to disk to get the I/O, I'm going to go and serve it right from my flash cache. So it's very easy, right? Well, I say easy. It took us years to build, but we figure out where on flash cache this data is. Go ahead and perform a local flash read on the storage server. I got the block back in my local memory on the storage server. I ship it back to the database. Now my job is done. Easy peasy, right? Okay, so we all agree this is how it happens. Let's take a closer look and see if we can dissect that particular flash-based database I/O. So this is the same picture, except for I kind of put together some software stack that an I/O took, kind of the I/O path took. First, the database software has to figure out, okay, I'm going to go read the block. So it submits a request to its local, the kernel OS. That, endures a context switch. The kernel goes ahead and sends a request over the network to the storage server, which is the other computer. That message gets received. Another context switch later, my storage server software gets woken up, picks up the request, issues the local read at the flash. So I'm not going to disclose what flash we're using, but let's say I'm reading an 8K block. I'm pretty comfortable to say that it's going to take less than 100 microseconds, okay? And then let's say that were the case, the read gets reaped, gets sent back to the database, went through the same context switches, and then the read is done. So my question for you guys is, does anybody have any guess how long this I/O took? Certainly shorter than the amount of time for me to explain what happened on the I/O. Significantly shorter than that. Any guess? Very good, a couple hundred microseconds. So 200 microseconds. And then the additional 100 microseconds that you see, I spent 100 microseconds just on the raw flash device for the I/O itself. So you figure, okay, there's another 100 microseconds. Where did that go? Well, it went on all the context switches and going down the I/O stack and everything. So that's quite expensive. But if you look at the actual cost of flash I/O taking 100 microseconds, maybe the end-to-end latency for a database to finish I/O in 200 is not too bad, right? Okay, let's say I took the easier route, like I explained earlier. I'm going to just stick with the software that I've already built for the last 10 years and do the easiest thing I can. I take the flash cache code that I have already written, put it on persistent memory, make a persistent memory cache, and put my cream of the crop, the hottest data into that persistent memory cache, and let it go through the same I/O path that I just painstakingly walked through with all of you just now. What is your prediction? So to help you make the decision, we've measured to do a local 8K read to a persistent memory. It's like far below 1 microsecond. So since we're not into counting nanoseconds yet, we'll just say it's a 1 microsecond, okay? Anybody has any guess how long this PMEM I/O will take? Oh, there's a hand in the back. Very good. 100 microseconds. That's exactly right. Because all the cost with the context switches, going through the wire, traversing between the user land software and the kernel, it's costing us that, and it's not going to go away just because I replaced my flash cache with PMEM cache. And that was a huge problem for us because Andy would know this. I have a very demanding boss. When I proposed this to him, say, look, I got the software, let's put in PMEM, let's ship it. He goes, no, Ja, this is the utter and complete failure. So that's not acceptable. I know, exactly, that's my argument too. But he tells me, look, over 99% of the gain from persistent memory acceleration is completely erased. How would you be able to answer to your customers? I'm like, okay, if that were the case, I'm going to apply a radical approach. So hopefully folks still remember the second piece of the puzzle. Oh, exactly. RDMA. So what happened in this case is we actually said that, oh, this graphics look a little bit, okay, my original one looked a little better, but basically we say, look, all that fat has to go. I can't afford to send a message to the other server, have the other server wake up, go process the read, send the results back to me. That's way too slow. What we do is we actually just, from the database server, issue a direct RDMA read on the PMEM cache. And the result that we were able to achieve is the 19 microseconds I mentioned earlier. And compared to the 200, the one that I bashed about my yesterday's performance, we have a 10x improvement, which is really good. So let me tell you exactly how we did that. It's actually really hard. That's why I was like talking to Andy, it took us 4 years to get this done. Because I don't know, the slide doesn't look, but the part you can see actually says PMEM cache. So we took the flash cache code and we say, look, I have a really good hardened stack that works really well. I stick it on the persistent memory. And I made it also RDMA-able in the sense that if you're that compute server standing on the other end of the network, you have the ability to query a RDMA-able hash table to figure out exactly whether you have a hit or a miss, and if you have a hit, exactly where on the persistent memory your cache line is. So once we get that sorted out and going with lots of concurrency controls and very complex algorithm, what we're able to do is really simple. We say, look, first you go figure out it's a hit or a miss through an RDMA call. If it is a hit and you know where the address is, just go direct to the card that's running on the storage server and then fetch that block. How easy is that? And that's what we wind up getting this 19 microsecond latency. And it's 19 because, mind you, we have to do 2 trips, right? One to sort of figure out if it's a hit or a miss, the second one to actually fetch the data. So this is a feature that we're able to release at September last year. We call it the data accelerator. So what it really allows us to give our customer is to, if you look at their OLTP applications, a lot of their time is spent on I/O waits because of those reads. Used to take 200 microseconds, now it takes 19 microseconds. And with that, it's a speed of a 10x. So they really like that. The second part is the high IOPS, the 16 million. So that really is a disservice to PMEM because our PMEM can do better than that. So I have to say that this is network bound. Because remember, we said the database runs on one end, the storage runs on the other end of the network. That's how we can actually do a linear boundless scaling up of the storage. With that, we're network bound at 100 gigabits Ethernet. So that's why we get 16 million IOPS and 19 microsecond latency. And we really like that. So now I'd like to talk about the second piece of OLTP workloads. So we talked about the random IO is really important. Let's say I went in and said, oh, I'm going to transfer $100 from my account, account A to account B. And I say submit. That's a time when the database needs to generate a commit redo, like a commit record, and have it persistent media before the prompt can come back to me and say, look, your transaction is processed. So the log write time is extremely critical for OLTP applications because the application just sitting there waiting for that particular redo to be persisted. Let's take another look at the conventional log write. I'm going to bash against myself, bash our yesterday's implementation again. No persistent memory, we only got flash. What do? Very similar. We figure out where the redo is on the storage, goes ahead and send a request to the storage. Storage server wakes up, said, okay, I got a request. We have a really neat innovation there I'm going to just quickly talk about. Instead of just writing it to one place, we write to the two persistent media we have on the storage server. One is flash, the other is disk. And on our disk, we actually have a disk controller that has a non-volatile DRAM sort of cache sitting in front of it. So the writes to disk is actually really fast because it hits a non-volatile DRAM. So what happens is we write to both. Whichever one finishes first, then we act to the database saying, hey, your redo log write is complete. The reason for that is like flash and disk, both of them have their own, flash has its wear leveling, the DRAM has its own, cache, flush mechanism, that occasionally we see outlier writes. So if you issue to both of them simultaneously, you get to basically combine the two outlier pattern and eliminate, a double outlier. You would only get an outlier if you have a double outlier, which is extremely rare. So that's how we accelerate log writes without PMEM. And with that, the storage sends the log back to the database. So, okay, my third question, I guess, last question for the day. If I put in PMEM as a drop-in replacement, like what I did for the persistent memory cache earlier, depending on the redo log write size, I can't say it's always 1 microsecond because we know persistent memory write is a little bit slower than reads, but it also hits a cache that's inside the memory, inside the DIMM. So I would say just less than 10 microseconds in general. And I'm not going to ask another question, but okay, 100 microseconds, right? It's the same story. So that's why for log write to accelerate log writes, we cannot afford just to say, look, I'm going to put PMEM on a storage server and use exact same model that I did the I/O before. So what do we do with RDMA log writes? So we went back to the same philosophy. We say, look, we have to cut out the context switches. We have to cut out all that fat. The only thing left is direct to wire, right? Just go to RDMA. So what we did is we actually get a bunch of persistent memory space, and then we carve those into, we call them persistent memory log buffers. And those log buffers are pre-posted to the RDMA NIC on the storage server. So when the database needs to perform an I/O, it simply just does the RDMA send to those persistent memory log buffers. And as soon as the RDMA lands, followed by a flushing read to make sure that the prior write has made it to the ADR safe domain, we say, look, we're done. That's it. The log write is already done. And then with that, what we're able to do is having, do I have the number here? Oh, I don't. But we have 8x acceleration in our log write latency. And just to complete the story, you can't just have your redo pile up in PMEM, right? Because like I said, we only have 1.5 terabytes. Even in theory, you can go up to 6 terabytes. But that's not enough to hold all of your redo log writes, correct? We actually use a tiny amount of redo, a tiny amount of PMEM log buffer for this redo accelerator. We use less than 0.1% of the 1.5 terabytes of PMEM. The rest, 99.9%, we give it to persistent memory cache, so you can have as many blocks cached in there as possible. So the way we can afford to do that and still have a great performance is that we actually have the storage server perform the draining of the active redo from the persistent memory log in the background. So as soon as the log lands in the persistent memory buffer, the server actually gets a notification, gets a completion, because it posts the receive buffers down to the RDMA enabled NIC, and then the NIC will give you a completion saying, look, one of your receive has arrived. So the storage server will wake up to that and goes ahead and put the redo and send it back to its proper place. So by that, it vacates the redo from the persistent memory and is able to post that log buffer back into the persistent memory right away. And you will ask, okay, so who said that? Dave said that? You know, if you use persistent memory without persistence, it's useless or something. So we completely agree. Because redo logs has to be persistent, right? I just talked about that. So what happens if your storage server were to have a crash? And then powered off or whatever, your kernel panicked. What happened to all the redos that was previously written to the log buffer, but the storage server has not yet been able to kind of move it to the backing store? So to solve that problem, we simply perform a recovery. So something crashes, it'll kind of boots back. So when the server comes back, what we do is we say, look, I'm going to take a look at all the active redos inside my persistent memory log buffer. Remember, it's persistent, and we made sure it's persistent, so we can actually figure out what are the redos that haven't been flushed, and then we proactively move them back to its backing store. Until recovery is completed, nobody can actually come and do I/O to the storage server. Once that's done, the I/O path is open. You're welcome to look at, you're welcome to send your I/O request to me because I have, the latest and greatest results for you. So that's how we deal with a crash. And then we call this feature the persistent memory commit accelerator because it really helps us with the log writes acceleration, and we're able to get to 8x faster log writes. And what that translates into is like lower latency for the OLTP application and a higher throughput. So we're really happy about this as well. And then to sort of conclude my talk, we put together a slide that talked about, we call it the epic journey. Because for us, it's been truly a journey. Because we started from like in this case, in the V1 case, 2008, there's no flash, only disk. It's a pure analytics play. There's no OLTP on it. With, the next 10 years, we have a huge, like a revolution of flash that gave us huge performance gains and whatnot. And then, PMEM showed up on the horizon and took us to the next level. So we're really proud of what we have accomplished. And I'm really happy to share with you that the X8M has been shipping since September of last year. And we actually have live, real customers deploying the system and running with persistent memory with RDMA that I just talked about. So really thrilled with that. And we got a lot of help from Intel. So I'd like to thank them for, a great partnership. But at the same time, we feel like it's been a thrilling journey, just even for myself, because just going through, getting to learn about persistent memory, getting to incorporate it with RDMA, arguing with my boss, and all of that is like priceless. So I'm really glad that I can stand here and share the story with you guys, and hopefully you found it interesting and enjoyable. Okay, thank you.
Awesome, thank you very much. All right, so after listening to Ja a little bit, you probably don't need coffee, but just in case, we do have some break available for now. We'll be back in about 20 minutes. We're basically right on time, folks, so we're going to get you to the reception in the beer. All right, everyone, 2-minute warning.
I have another control and I have a older one. Not so bad, but I still wake up.
Better than work keeping that way call.
Not working anymore. I used to be on call, but I woke up a lot. That's why I.
Oh, but you have room. All right, everybody's filtering back in. We'll get started again. Like I said, great opportunity because we're at the place where you're getting to see how people are actually implementing persistent memory in very complex, very simple ways. And so we have a third perspective on that, and that's coming from Yayuek. Come on up. And you can see her at Thinking Fish with Twitter. And so I will let her take it away.
There you go. All right, awesome. So I'm going to talk about how Twitter is trying to start using something new, persistent memory, in our environment. I think the high-level message I want to send here is we are not as capable as, for example, Oracle to build an exciting new product using multiple new technologies, spending years of effort in giving you sort of huge gains. That's sort of not what we're trying to do here. As someone who runs a service or applications, one of those people who does things that is above you that probably doesn't make any sense most of the time, what I want to sort of have people take away from this is what is the shortest distance from what you have now with traditional hardware and a data center that someone else designed, right? A hardware team, or maybe you're in the cloud, to a place where you can have a taste of new hardware without breaking all the norms of operations that you understand, and without spending a lot of resources in advanced commitment, which we don't have, and still get a sense of whether this is worth it, how does it work out, would it be reliable enough in production, is it worth a follow-up investment? So it's a compared to basically Exadata, consider this a piece of cake, right? It's a very small problem. So I want to talk to you about Pelican. Pelican is something that you probably have never heard of, but fear not, it's actually very, very easy to understand. I imagine everybody has at least heard of Memcached and Redis. So Pelican basically can act as either Memcache or Redis or both. So what it is a open source modular cache. So the architecture, if I have to give you a high-level view, will sound very, very similar to Redis and Memcache. It's a key-value store that stores data in memory. We use it strictly as a cache, not as a database, so we never thought about consistency, and I prefer to keep it that way if possible. A little bit of background of how we run cache at Twitter. I think this is important because this explains the test setup that we later will present. Right, so we have, I think, interesting, maybe a little bit unique setup where we are, in terms of cache, we're in favor of single tenant configurations to achieve good resource isolation. What that means is we have a very large number of relatively small clusters, ranging from a few thousand QPS maybe all the way to maybe tens of millions of QPS per second. And we run tens of thousands of instances over a hardware cluster that has maybe many thousands of nodes. So because of this configuration, you can see that we have to have multiple jobs running on every single node. So we tend to run small and wimpy clusters. So each job actually only takes about a few cores and uses a few gigs of memory in most cases, and sometimes spikes up to a larger size, which I will explain later. So our SLO is, decent, but nothing crazy. We're a web company. Nobody is in a hurry to get anywhere. People are there to kill time. So, and also, and also, if you know anything about end-to-end performance, most of the people spend the time finding the cell tower that's nearest to the cell phone, right? So the latency happening in the data center actually is not a dominant part. So our SLO is at a decent 5 millisecond at the tail part, P999. As long as we have that, we're actually quite happy. So the project Pelican actually aims to support all the well-known and maybe not well-loved protocols out there, Memcached, Redis, Thrift, don't deal with that, and data structures that may or may not be relevant to you. So what is interesting about Pelican, I think, for this audience in particular, is that I think it makes a lot of the experimentation less painful if you are not a software developer who already knows some of the open source projects like the back of your hand. Right? So handling key value requests is actually a very standard process where you would read some data from the socket, parse it, and then process it, and write a response and send it off. Right? So in doing so, we also need to deal with some data structure that is putting some kind of data storage. So if we do this abstraction correctly, then you will have something that looks more or less like what is on the left side, where you would delegate the parsing and composing to one module. You would delegate the RPC stack to an entirely different sort of invisible component if you can do that. And also, you will layer the data structure on top of a well-defined data store module. Right? So this is what gives the project the capability to mimic multiple services like Memcached or Redis without having to basically duplicate all the code. So we'll see why this modularization is helpful in adopting PMAM. So okay, going into PMAM, well, Intel insists I have to have the full name, so there you go, a very unbalanced slide. Just very quickly, everybody here already has heard of this like 10 times, I believe. If you want to use persistent memory, there is the memory mode and there is the app direct mode. Right? So the memory mode has the benefit of giving you suddenly more memory without any code change. It is, of course, volatile. You don't get to persist, but if I'm operating cache, I actually don't care. And you can also use the app direct mode where the PMAM is no longer, the DRAM is no longer hidden from you as cache. You suddenly have direct access to both, and you can make wise decisions if you have them, and also persistent. So for us to try PMAM, we actually have a couple of considerations going into this. First is, more memory is always better. We have 400 or whatever number of clusters, and some of them are memory bound. Actually, a lot of them are memory bound. So for the clusters that are memory bound, having bigger, cheaper memory is a very sort of straightforward TCO play, right? You reduce the cost if you remove that or shift that bottleneck. The other thing, and by memory bound I mean limited by the size of the memory, right? We want to put more data into memory to serve them out of cache, and that's the limiting factor. And also the flip side of that is now if you have more memory that you can use, more requests actually will end up as hits at the caching tier. And what that means is you will reduce the amount of traffic that goes into sort of the deeper level of the stack, which tends to be more expensive and slower and have some other sort of undesirable features. So that affects both scalability and cost. So generally having a very, very warm cache is favorable, especially for workloads that we have at Twitter. Many of our data sets actually can be cached up to like 99.9%. So you almost never see the database. And the other side of things are sort of actually trying to consider the persistent aspect of the memory. because one of the operational problem we have is anything that's in memory, when you restart it, it goes away. So if we are so reliant on cache to being warm, then whenever we lose a warm cache, it becomes a problem, a capacity problem for the back end, and also becomes a sort of a performance or availability problem for the high-level requests, which tends to fan out to many, many backends. So having a warmer cache means if we can reduce the sort of the data loss when we do routine operations, which are binary upgrade or host maintenance, things that tend to complete relatively fast, but inevitably forces us to give up data that's already in memory, that actually would be an operational win. The other thing is having higher availability during maintenance, like for maintenance not to be such a event that makes the entire site more vulnerable because the cache rate goes down, it's good for the site reliability overall. So we also have a couple of constraints, right? I said we don't really have all the resources we can sort of at will to drop into an experiment like this. So what is important is for the changes we make to be small and manageable. We can sort of dial up and down the investment as we see fit. So that means we want the change to happen in the same code base that we already have. It should be not very invasive. It doesn't require you to rewrite everything. And also, it doesn't change how developers interact with it from the way they already know. And then finally, last but not least, operability is extremely important if you're a service owner. So being able to sort of enable PMM at the time of launch, you don't have to build any special binaries for it. You don't have to do complicated procedures to deploy it. This is all very important. And also having predictable performance is the one thing that will keep people from being woken up by pages in the middle of the night. And I was on call for 7 years. I care about this a great deal. So here is why the abstraction matters, right? So we saw that the cache can be abstract as a bunch of boxes, and actually the data store is only a very small part of the abstraction. And it proves to be, so it turns out that if we do the abstraction right with memory, this little component is all we need to care about to enable PMM. And in particular, what we did, actually what Intel did, I actually did not write any of the code that is on this slide. So thank you, Intel, for doing my work. What Intel did is they created a data pool abstraction on top of existing libc APIs, as well as PMDK APIs. So there are two paths, right? First, we can have a compatible mode. If you don't have PMM, you just fall back to DRAM. And on the other hand, you can have persistent memory where we take advantage of the PMDK library, and also we can use file-based file-backed memory that is still byte addressable. So essentially, data pool will present the same API to the upper level abstraction, such as, you don't need to understand what slab and cuckoo mean too much. If you forget about it, that's fine. But the concept is the interface is very small. So we have essentially two ways of using memory, right? So slab is what you probably are familiar with. You have a bunch of memory that get chunked into different sizes to use as key value store containers. And cuckoo is another one that looks like a giant array that gives you a little bit better memory efficiency. In both cases, the modification we need to do to enable PMM is actually quite limited. Let's see. So if you only have DRAM, of course, everything goes into DRAM. When we make the change to use PMM, for the cuckoo use case, because everything is in one giant array, we just shift that whole thing to PMM. And in the slab case, we keep the hash table in DRAM, and the vast majority of data goes to PMM. So this is basically the philosophy is let's try to put as much data onto PMM as possible, because that's where the space is, and see if the performance is good enough. So let me talk a little bit about the result. I think this is the one thing that's interesting about this project is the code change actually was very, very simple. mostly because we have it done by professionals, and partly because the abstraction works out well. So to enable data pool was about 300 lines of C code, so anybody can do that in a reasonable amount of time. But on the other hand, because we aim for this final product to go into production at some point, I don't know when that exactly will be, but that's the goal. So it's really important that we test it out thoroughly. So this is how we test it, to gain confidence. So first, we try to mimic core parameters that replicate what we see in Twitter's production, right? So we pack every host with many instances. We have object size distribution in a way that reflects what is the most typical, that covers most use cases at Twitter. We also have dataset sizes that is comparable to our production configuration. And one notable thing is we have a much larger number of connections per server compared to most of the Memcache Redis benchmark you will see, because this is what we have. And it turns out actually the network performance is quite important. And we also have a couple of different rewrite ratios just to see if the workload is sensitive to that. And the focus is we sort of define 3 stages of evaluation, right? So every stage, at the end of every stage, we try to see, should we go or should we not go? So the first stage is just use the memory mode and see if this makes sense at all, right? It's like a vanity, it's like a sanity check. And then we enable app direct mode and see for the operational gains that depends on app direct mode being enabled, do we get the benefit that we were expecting, and do we have any performance surprises when we switch from memory mode to app direct mode? And finally, we want to run, so until now, all these experiments have been run on Intel's lab environment, because that's where the hardware is. And the last stage is when we finally have equipment in our data center. We want to redo the tests, use slightly different hardware, but is exactly what we will get if we are running in production. Basically, lots of thorough testing to make sure all the numbers are solid. So stage 1 is actually very, very boring. So the only interesting part you can see, that's the dip, is when the packet size, when the object size exceeds 1 MTU, so you have a throughput drop. That's exactly what we'd expect. And in terms of latency, it's actually more or less flat. So the line chart is about latency, and the bar charts are about throughput. So we change the object size. We change the amount of data that resides in DRAM versus in PMEM by just keep dialing up the size of the total data set. So as you go to the lighter shade, actually more data will be residing in PMEM, and there is very little difference in throughput and latency. And note this is a sort of a loaded configuration by Intel with the best CPU and a 222 configuration, so lots of bandwidth to go around. And then we move to stage 2, right? So stage 2, we have app direct mode. And again, kind of boring. It's slightly more interesting than the previous chart because the latency numbers start to move a little bit. But the throughput numbers are actually still pretty stable if you look at it. But overall, what we found out is, and also in this chart, we dropped the largest payload, which is 2K. So we keep it all under 1 MTU to keep the experiment a little more manageable, right? So we see what we would expect, that latency goes up as the value size goes up, but not by that much. Also, if you look at absolute number, 200 microseconds is well within our defined SLA. So the other aspect of the app direct mode exercise, right, is do we get any benefit from having persistence in our memory? And so again, to sort of go back to why we were incentivized to do this, having data available quickly after maintenance is actually something that's valuable to us. So really, the shorter the window it is to reload the data from persistent media into a serving state, then the more valuable this is to our maintenance. And it turns out that rebuilding our data from rebuilding the slab hash table from data that's otherwise stored on persistent memory takes only a pretty reasonable amount of time, right? So to rebuild 100 gigabytes of data, it takes 4 minutes. If you do 18 instances concurrently and load all the data, it takes 5 minutes. So compared to what we otherwise have to do, which is we need to wait 20 minutes between starts, this is a sort of order of magnitude improvement on how long we need to wait. Because the 20 minute only applies to a data set that's much smaller, keep that in mind. So we believe there's a lot of other changes that needs to happen before we can turn on the beast of loading from persistent media into production. But I think the raw numbers are supportive of us having some benefit for cache by putting data on persistent memory. So finally, the last stage, we bring everything in-house, and just don't. The one principle about benchmarking is don't trust anybody else's benchmark. So you should never quote my benchmark numbers in your internal reports, say in supportive or rejection of a decision. Always do your own benchmark. Because in this case, the numbers are somewhat different. I think the primary, we have not confirmed 100%, but the primary reason we think this is the case is because different from the Intel lab, what we have is large quantities of middle-of-the-road Intel chips, and also a much less loaded configuration. We have the 2-1-1, so that means we are losing 2/3 of the channels compared to the lab configuration going to PMAN. Right, so in this case, then we're going to see more bandwidth contention if we use things in a way that stresses that. And this is shown in this test, right? So you can see that compared to, you can see that the P999 latency, where the SLA is drawn in the middle, we start to drift above this SLA in memory mode when most of the data is in PMAN. Again, I think this is because we don't have as much bandwidth. However, when we switch to testing AppDirect mode, everything falls back to normal, right, by expectation. So this is acceptable again. I think this is interesting because I was not expecting too much of the performance benefit between going to AppDirect mode. But what this tells me is actually with AppDirect mode, it's easier to control tail latency compared to memory mode just because data placement is explicit. So that's a good lesson to learn. All right, so overall I think this exercise shows that memory mode is a very good gateway drug if you want to get hooked. So remember, one thing about application developer and software engineers in general is we do not know what's going on with hardware at all. We don't pay attention. And we have no idea how to predict how much effort it takes to do anything that relates to new hardware. So I feel the most important in continuing this discussion that has, it's sort of like a mini panel in the form of 4 presentations in a row is I don't think PMAN without consistency is worthless. I think one of the adoption bottleneck is really software engineers are not paying attention and they have no time. So whatever can lower the barrier to get something out of their existing software, get them to think what is possible if they spend a little bit more time in terms of architecture redesign and just use their imagination. And once they learn the property of the hardware, actually, I think over time, all that insight will sort of permeate above all these layers of stack and sort of invite people to create something that's new and exciting, right? But the thing is, you need to get people started somewhere, and I think memory mode is a great place to start. And over that, if we can use the correct abstraction to gently guide them to persistent memory and make it easy to swap one thing for another, add more complexity of how to deal with all the new properties, and then I think we will see more benefit on top of what people think they were getting going into the space. So a little bit of tidbit is after we got equipment from Intel and running the benchmarks in our production, in our data center, I actually started canarying persistent memory in production. We only do it on one instance out of the hundreds of instances that's serving people's tweets. So if you tweet enough times, one of those tweets will be served out of persistent memory. Who? Well, I'm strictly forbidden to tell you which one it is. I don't know at all, but I know probabilistically, if you tweet enough, one of them is going to be served. And it's been running in canary mode since the beginning of since before the holidays. I haven't, see, this is the nice thing about it. I don't have to think about how long it's been running fine. So that's it.
That's the best endorsement of information technology that I've heard. I don't have to worry about it because it's running. So thank you very much. Thank you.
Thank you.
There we go. Let me lower this.
All right, the next person needs no introduction because it's me. My name's Jim. I'm a geek. Longer than I want to admit. So hopefully at some point, or somewhere in this room, there's one or two people, at least. Don't raise your hands, I don't want to know, because if nobody raises their hands, I'll cry. But hopefully there's somebody in here who's going, okay, I want in. I have seen that there's tools and development tools available. I've seen a lot of the technology that's there. I'm starting to see how people are putting this together. So how do I actually get in on this? How do I learn more about persistent memory? What are the things that I can do with it? And how do I put it, and how do I put this all into place? Well, we alluded to it earlier this morning. It was about a year ago, I should say 13 months ago, Jim Pappas called me up and said, hey Jim, and he said, hey Jim Pfister, I want to buy you your favorite beer. For reference, my favorite beer is the one somebody buys me. So that's a hint, just in case. And he asked me if I'd come in and help organize a lot of the tools and the things that are going on. You know, Andy's been putting together a seriously good set of tools. He's got a great team working for him. The book that's coming out is phenomenal. I would certainly encourage you to pass that far and wide for that. But we wanted to put it together, and we wanted to basically set some goals on what would we want to do with persistent memory. So as you're aware, there's already a consistent Windows and Linux architecture model. That's, you saw that in Andy's slides, that was years ago that we put it in. And there's a variety of open source tools and libraries. You've seen a lot of them today coming up. And there's a lot of others that you haven't seen where you can go out and you can actually just Google persistent memory on blah. There's a good chance that there'll actually be different pieces and parts that are out there. But obviously we needed to focus on something from SNIA, and so we decided that we wanted to stick with the persistent memory development kit. As you saw this morning, it's a really good way to be able to get direct programming. You don't have to do a lot of the heavy lifting. It's already been done for you. And we felt that that would be the best way to be able to get people moving on this as much as possible. So last year, we effectively promised over the day of the Persistent Memory Summit that we were going to start evangelizing this a lot more. So first, we had a Persistent Memory Hackathon the day before the summit. We wanted to try it out. Had 20, 25 people, I think. It was a little nascent, but it was entertaining because it was Andy Rudolph and Stephen Bates. So you know, that always makes it easy. It happened at lunch, lunch the day of the Persistent Memory Summit. I actually sat down with Arthur Sanio, and we said, well, you know, we don't want to just do generic, we want to do specific. And so we hatched the idea of an NVDIM programming challenge. We didn't announce it at the summit, but that was where the idea came up. We did briefly mention at the summit that we thought that there was room for another conference focused very specifically on experience around persistent memory development. So I think in the morning session, we kind of threw out, oh, there's a new conference we're thinking about, stay tuned.
And we were at the time calling that persistent programming in real life. One of the P's is silent. Your guess as to which one is good. So we wanted to build that conference, and there is a non-volatile memory workshop, and that's great. It's an academic conference. It talks about hardware and software technologies around persistent memory. We wanted one that was a lot more, here's what we did and here's why it hurt, and is to make it experiential. And a couple of the presentations that you saw today were first formed for that conference. But that was what we said we were going to do. Okay, let's hack, let's challenge, and let's talk. So that was what we committed to. And it turned out pretty well. This is backward-looking as well as forward-looking. If you actually look at it, you can see all the different events and different pieces that we did. Very West Coast focused around Persistent Memory Summit, Flash Memory Summit, where we did a hackathon, had a PM track, Storage Developer Conference America, where we did a hackathon. You can see the rest. NVMW and Perl, we're driving in San Diego because we're doing those in partnership with UC San Diego. So, you know, we're not bigots. We'll go anywhere up and down the coast. We might even do something in Oregon at some point or another if you like rain. We also did, we kind of did a Japan hackathon. I had a question on it, and I think an Intel person happened to be going through, so they did the hackathon for us, but we'll call it credit. We did do 4 China hackathons with a company called DoIT, and we generated a lot of interest, and I think maybe in another 10 minutes or so, you're going to see where some of that interest led in terms of interest in China for programming persistent memory. Already for 2020, we've been doing the Persistent Memory Summit, of course, and the hackathon here. We do have a commitment at NVMW to do another hackathon. We do have a commitment to do another Perl conference. I didn't put that on the slide, but we are going to talk more about, oh yeah, I did. But we are going to, no I didn't, never mind. We are going to talk more about that. And we want to do more international conferences. China was fun. We want to focus elsewhere. So the next one that you'll see, in fact, February 4th, I don't see Alex in the room, Storage Development Conference Europe, which is actually in Tel Aviv, Israel, will feature a hackathon the day before. If you would love to go to the lovely city of Tel Aviv, you have an opportunity to attend a hackathon. If you know people that would like to go, then certainly direct them there. You can pick up flyers from the SNIA booth, and that's already available on the website. You can register there. And we were obviously looking at some other options. There is an SDC India. We're thinking about it, trying to figure out logistically how we can do it. There are some other international opportunities that we have. We'll continue to go. And in a minute, I'll actually talk about maybe some other ways that we can expand the reach. So all of that happens on site, but plus we've had entries in the SNIA blog. Perl has started up its own blog, and there's a lot of cross-posting. I'll say from the Perl conference, there's about half of the talks at Perl are actually available on YouTube. So you can search Perl Conference 19 on YouTube, and you get access to the speech that Pratap gave. There was an Exadata speech. It was given by somebody other than Ja, and several other really interesting talks. So I would certainly encourage you to go out and look at that. It's a great way to be able to see more about how people have have implemented persistent memory and what they found easy and what they found hard. So we're going to continue to do that work. Now, of course, the general question is, well, you know, hackathons sound really complex. Oh, where is it? There it is. Hackathons sound really complex. I don't know how easy it would be to figure this out. I want to show you that the interface that Andy developed for the hackathon is so easy that even the dumbest manager in the world can do it, although I will need my glasses. The dumbest blind manager can do it. Where's my mouse? Can anyone see the mouse? Oh, there it is. That's why. Oh. Hang on. Well, never do demos with animals or children, so. Let me see. Hang on. One more try. Nope. Never mind, come see it later. I tried. Trust me, it's fairly easy. It's a really nice web interface, and what's the nicest thing about it is it actually works in very low bandwidth environments as well. We had some trouble with the initial space where we were basically shelling directly into the server, and everybody in there were just basically crashing the wireless bandwidth of your hotel, which is usually minuscule. So we actually moved to an environment where you do all the development in a browser page, and then it actually gets sent off to the server to compile and run. So it's a lot easier to develop, and you also don't have to know all the intricacies of VI or any other language that you'd normally find in the shell. So it's a nice way to go. If anybody else wants to see it, I'll show it on my laptop, or Andy's always happy to show it. Or more importantly, come to a hackathon. Let me talk about the NVDIM programming challenge a little bit. Again, we were ambitious in saying we wanted to do it. My favorite way to do things at work is somebody go, well, what do you think would happen if we did this? And I go, I don't know, let's find out. So that's what we did with the NVDIM programming challenge. We had to find compatible systems. We had to find some sponsors. We wanted to make sure that we had good opportunity to put it in, allow people to do some development, and then build some rules around, well, how do we review and develop the challenge? So it took us a little bit to get started. We had 3 great sponsors: Smart Modular, Gigatech, and Supermicro. All provided different forms of equipment that we could work with. Smart's been, by the way, indispensable in this. Thank you, Arthur, for all the help that you certainly gave us and your team. And we've had the program running for about 4 months. And so we've had multiple submissions come in front of a panel. We've looked at some we've asked to re-review. We have one challenge winner that we've already announced. That is Steve Heller from Chrysalis Software Corporation. I see him in the back. Raise your hand, Steve. Yay, Steve. He's got a really nice, he calls it the 3 misses persistent hash table. If you haven't seen it yet, go out right by registration. He's sitting out there, and he's happy to chat with you. And you can see his submission. But what's really nice is it takes advantage of several things. We actually set some pretty strong criteria, and we wanted this to be able to very specifically be able to use things that were advantages of NVDIM as opposed to just general persistent memory. But it was helpful if whatever work was done was available across all persistent memory. So can it run on NVDIM as well as Optane? And so Steve did that and several other things, and that's why he's got a great submission. I encourage you to go see it and talk to him. He's a very engaging person. Now, this and other challenge winners, we're still accepting submissions. If you're interested, you'll see the email or anywhere in my presentation, pmhackathon@snia.org. Just send an email there. We'll get you a login for the NVDIM system, and you can participate in the challenge. We're going to probably run it through the first quarter. We're going to continue accepting submissions, and we'll do some follow-up blog posts, as well as if we get a couple of winners, we'll probably do a webcast just showing this is what normal people are doing with persistent memory. It's not impossible to work with. There's great tools, there's great opportunities out there, and so this is a good way to be able to show off that it's very easy to develop and run on this. So I talked about what we did in 2019. What are we gonna do for 2020? We're gonna continue with the hackathons. I already talked to you about a couple. We're looking at additional NVDIM challenges, and we're also looking at potentially an Intel Optane programming challenge. There's a little bit that I'd like to see in place before that goes, so I think you're gonna see that closer to the end of the year. But you can come to the hackathons, or if you really want to see a hackathon and you think that you've got some gravity, you think that you can pull some people in, pmhackathon@snia.org, let us know. We'll set up a host your own hackathon. You provide a venue. You might have to provide some sodas or something like that for a little bit. But we'll figure out how to get a team out to sit with you for a couple hours, show you how to do basic persistent memory programming, and get your team or your friends or anything that you want set up and run on programming persistent memory. We also want to continue, I said, we want to hack, but we also want to talk. So we want to do continued focus on expanding the conversation around persistent memory. So again, SDCME is going to have some wonderful presentations around that. You'll also see some of the new computational storage discussions that we're doing here in the organization formerly known as SSSI continue into SDC. NVMW, Perl in July. We will continue to post additional conferences and plans on the blog. So, keep an eye out for that. But there's an opportunity to really get in on the conversation. Now, there are some more things that we in SSSI do, and what we want to do is also analyze. So we've hacked, we've talked, we want to think. And so we also want to focus on programming and analytics and what we can do to expand. Computational storage is in the organization now. They're building their spec. We're already involved in the conversations on how do we take a lot of the concepts that we're doing with persistent memory and bring that to computational storage. More importantly, you saw today in the CXL presentation, persistent memory on CXL as a potential computational storage device is a high likelihood in the next couple of years. And so really understanding how those two dovetail together. Obviously, we thought it was important enough that the two be together that we put them in a single initiative. So I think you should expect that you might see future joint conferences around this. Maybe not in 2020, but thinking about it in the future. And we also want to take a lot of the workload analysis that we've been doing around solid state drives, another part of SSSI, and expand that to the persistent memory into the computational storage conversation. So there's a lot that we're doing. There's a lot more that we want to do, and we really want to bring all the things that we have been doing here in, again, the organization formerly known as SSSI, into the next generation. So I'm actually going to hand it off now to our next presenters. Let me bring up your presentation. If you have a demo, Eden, I hope it goes better than mine did.
It's a pantomime.
Okay, where'd my mouse go?
Today we're going to talk about real-world workloads, AI, and storage optimization. I've given several presentations at the previous PM summits, benchmarking various types of persistent memory and comparing it to different types of storage using synthetic as well as real-world workloads. So today we're going to look at benchmarking and testing DCPMM, Optane Persistent Memory, NVDIMM. We're also going to compare that to XL Flash SSD, a TLC SSD, and a 3D Crosspoint Optane SSD. Those will be benchmarked against some synthetic corner case workloads as well as more real-world workloads in addition to the ones we've been showing. And in the second half, we're going to be looking at AI optimization using machine learning, and Yafei will talk about that. So this slide shows you a typical real-world workload. It's been shown before. I just wanted to refresh the people who have seen it or for you who haven't seen it. What it shows you is that real-world workloads are a capture of IO stream activity that occurs in the software stack when you do something. So it's not a synthetic workload. It's not a random 4K write type thing. You actually capture the IO streams and metrics that occur when you do something in the software stack from point A to point B. So most often you're interested in what IOs are going to storage, but it can also be IOs going on one end of the wire to the other, or from virtual to hardware, or anywhere else you want to look. When you look at this picture, time is on the x-axis, and the y-axis is IOs, as well as queue depth in terms of users. So you see the three things you want to notice here. One, you have a constantly changing combination of IO streams. So when you look at those vertical bars, you can see a left-hand bar that spikes up over a 2 a.m. SQL Server backup with random and sequential 64K read writes. You can see morning boot storm activity with primarily sequential half K writes and so on and so forth. You can also see the corresponding demand intensity or number of users in that orange line that goes across. So you can see that users vary depending on the time of day. You can have very few users in the early morning hours. It can spike during morning boot storm. It can go up and down during the course of the day. The third thing I want to draw your attention to is there are a number of IO streams. If you look at the cumulative IO workload box on the right, yes, the right side, it shows you that we've selected to show 9 of the most prominent IO streams, the ones that occur the most. But there are over 5,000 IO streams that occur over a 24-hour day. So not only are IO streams changing from moment to moment, there are many, many, many IO streams. So this obviously affects your performance, and looking at a real-world workload applied to storage gives you a very different look at how your storage is going to perform. The last thing on this slide is, depending on where you are in the stack, your workload is going to be different. So the workload works its way down from user space to application space to the kernel to storage and back. And at each layer of abstraction, the IOs change. They can be coalesced, fragmented, merged, and so on and so forth. So when you want to test your X to a real-world workload, you want to make sure that you're pulling the workload from the right spot in the stack. So if you're in user space, you don't care what goes into storage. If you're at storage, it doesn't matter to you how many IOs are going to cache. I only care about how many IOs ultimately get down to me down at the storage level. Okay, so what are real-world workload use cases? They're pretty much everything. Today, we're going to concentrate on AI-related workloads. So we're going to look at 5G edge storage, video edge storage. But we also have workloads from cloud storage servers, from web portals, and the like. Pretty much any use case involves or can benefit from real-world workloads. But simply put, in this case for AI, you're looking to gather raw data from the edge and transmit it in to process it and train with it. For cloud servers or data centers, you're looking to see the IO load to balance your IOs and see where the bottlenecks are and see how well their storage servers are being utilized. Okay, so this graphic shows you real-world workloads going out to a bunch of different architectures. The main point of this slide is just to show you that this is a disaggregated capture and test architecture. That means that you can capture the IOs anywhere in the wild, at the file system level, at the virtual level. You can do it on the virtual storage servers, physical storage servers, to direct attached storage, to any virtual storage or logical storage. Equally, once you have a capture and you curate it, you can take the workload and then apply the workload to test storage at any level that you see. It can be logical or virtual. So what does an IO workload, an IO capture workload look like, and what does it do? This slide kind of looks at the life cycle of an IO capture. So what's an IO capture versus an IO trace? So we're all familiar with IO traces. You have block trace and others, and it's a constant collection of continuous data, and it results in a humongous file size. So they're difficult to process, they're huge in size, they're difficult to transfer. An I/O capture or an I/O profile real-world workload captures the statistics about the I/O streams that occur from moment to moment. So it's a time-stepped capture, which means that you can set the resolution to 1 millisecond or 1 second or 1 minute, and you can average all of the I/Os over that period and make a table of statistics about those I/Os. So instead of capturing 400,000 random 4K writes and saving them to look at it, you can have a table that says, I saw 400,000 random 4K writes and they had these characteristics. So by making a binary table, you aren't taking any personal data, you're reducing the file size so I can easily port it to wherever I want to go, and then when you get it, you can rebuild your workload on a time basis, moment to moment, and recreate the workload that you had. So in item 2, you're seeing edge transmission of these workloads from your IoT devices or your edge servers. It can go to your AI data center. It can be a constant stream of data packets if you want, or it can be transferred as a whole file. You can use I/O captures to do continuous monitoring of the edge workloads. So if you're doing AI and you've done your training and inference, you can still be grabbing real-world workloads in real time to monitor if the edge traffic is still the same as the basis upon which you did your inference. So in other words, if I train it to do ABC, I want to make sure I'm still getting ABC and not 1, 2, 3. As far as what you get, you have a wealth of key performance indicators from I/O, bandwidth, response times, process IDs, pretty much whatever you want to capture. And again, those are captured as statistics and tables, and they're easily curated, so you can take your workload, you can filter it or parse it to get what is of interest to you, and then you can take that and create a replay training workload that can be applied for AI, or you can do it to test your storage servers for qualification or validation. Okay, so in the AI world, what we're interested in is getting the data. All AI is pretty much based on I can get enough data. So how do you get that data? So again, capturing data from the edge is very difficult because the files are too big to be useful to be used in real time. If you use the I/O capture workload, you can get these workloads streaming to you. They can be in very small tables. They can be rebuilt in the database, and they can be curated to whatever you want to look for. In the case of AI, you typically look at things for machine learning in this trifecta here called gather, training, and inference. So gather is merely the activity of collecting the workloads from the edge. So the I/O capture tool versus I/O trace is very effective for this. The inset box that you can't see clearly here, but when you download you can look at it, is a LSTM, or a long short-term memory recurrent neural network graph showing you the input and output. The middle part, which is the LSTM, Yafei will speak to, but you can capture the raw IOs going into it. You can then capture the data coming out after LSTM, and you can look at those workloads to assess their performance. In the training, you can take the workload that you curated, and then you can create replay tests and run a loop of training tests to your storage and use that in the course of developing your AI optimization algorithms. And then as far as the inference is confirmed, you can look at how well your performance is with that same raw workload, at the same time monitoring the edge traffic to confirm that I'm still looking at optimizing ABC traffic instead of 1, 2, 3. Okay, so we're going to look at a couple of real-world workloads, and when you look at this picture, you can see that when you glance at them, they look different, right? The I/O streams are bars or continuous hash or horizontal. You can look at I/O clustering. The point of this slide is to show you that workloads can show you different key performance indicators. You can look at the I/O stream consistency. You can look at I/O and response time spikes. You can look at IOPS and throughputs. You can look at quality of service, a variety of metrics. So when I look at these, you can see that on the left, I've got retail web portal, which is based on different kinds of activity and different kinds of IOs. On the middle, I can see boot a C drive with a lot of cache activity being dominated by 128-byte reads. And on the right, you can see a more consistent pattern of labeled data that shows up as a random 4K, 8K, 16K type workload that we expect to see in corner case testing. Okay, so we're going to look at some reference workloads, and you can look at this table offline to see more details about it, but I just wanted to show you a couple of things. One, we use a synthetic database as a baseline test, which is basically a simple synthetic application of random 8K read-write with 65% reads. The next 4 are real-world workloads. One's a retail web portal, one's a GPS nav portal, one is data center storage, and the last one is video-on-demand edge server. When you look at the red column, the first one, that's the overall read-write mix. So you can glance at these previous IO streams, and there are all these points and bars and lines that might look confusing, but at a very high level, you can see that some are 65% read, 96% write, 75% read, 60% read. Similarly, if you look at the min, median, and max queue depth range, you can see that the median queue depth can be 23, 8, 62, or 3, and the max queue depth can range from 42 to 306. And then finally, on the right-hand side, you can see what the main IO streams are. So for the second workload, it's 64K, half K, 8K, 4K. The next one is 4K, half K, 16K, 1K, and so on and so forth. Now again, these are the main IO streams that we selected. Of course, there's hundreds of IO streams, but these 4 or 5 or 10 might represent 80 or 90% of the workload, and those are the ones that we're interested in seeing. And finally, on the right-hand side, you can see the access, whether it's a random or sequential access, and some are more random and some are more sequential. So, getting to the test sample pool, we're going to look at Intel DCPMM, the persistent memory. We're going to look at an NVDMN. And then we're also going to look at a SLC flash drive. We're going to look at a 3D crosspoint SSD. And we're going to look at a TLC NVMe SSD. So the 3 SSDs are all NVMe SSDs. And the 2 DIMMs at the bottom are Optane, DCPMM, and NVDMN. Okay. As far as how we're going to test them, you've seen variations of this chart in all the previous presentations. So basically, we're going to apply the workloads through the file system to the SSDs for the SSDs, and through a PM-aware file system using the PM driver to the persistent memory. Okay. This is a summary of all the data you're going to see in the next 4 charts. But to put it simply, we've got persistent memory, there's data center PMM and NVDMNs being compared. And on the right-hand side, you've got NVMe SSDs. The XL flash is looked at just for a few corner case workloads, and the 3D crosspoint and the TLC NAND are compared against all the workloads. For the synthetic corner case, for the DCPMM and NVDIMM, we're just going to apply a 64-byte, 128-byte, 256-byte, or 512-byte random or sequential read-write workload. So the first line is going to be reads, and the second line is writes. So before you see the charts, DCPM has faster sequential reads and slower random writes. Conversely, the NVDIMM showed slower sequential reads and faster random writes. So we'll show a couple of plots that show that. As far as the corner case for the SSDs, looking at the I/O rate and the bandwidth, you can see that the XL SLC had the fastest random 4K read IOPS. The 3D crosspoint had the fastest random 4K write IOPS, and the TLC 3D NAND had the fastest sequential 128K bandwidth. You're going to see more detail in the charts, but the main thing about this chart at the top, it says performance depends on the workload. So we're comparing very different classes of storage with very different workloads. So in some cases, some test samples are better than others. In other cases, they're not. And it really depends on the workload. And some of the workloads that we use from the real world are more suited for NVMe SSDs. Others are more suited for persistent memory. So keep that in mind. Performance always depends on the workload. For the middle line and the bottom row, these are the real world workloads. So for the real world workloads, if we make a synthetic test out of it, it has these multiple I/O streams. You can use those multiple I/O streams and apply them for every step of the test and make a synthetic test. So for example, if we had a random 4K read-write workload, 50-50, we could do every step of the test 50-50 random 4K, and that would be a synthetic workload test. If in the real world the first half hour was all reads and the second was all writes, that would be a real world replay workload. So in both cases, at the end of the test, you have 50-50 4K read-write, but in the first case, every step was 50-50 4K read-write. In the second case, the first half was reads and the second half was writes. So in that case, the performance average may be the same, but if you have hundreds of different I/O streams, you can see that you'll have a difference between having the same percentage for each step of the test in a synthetic test versus varying between backup to morning boot storm and so forth as you go along. Excuse me. So the final takeaway is when you look at the ordinal ranking, there's only 2 drives. There's 2 drives for the persistent memory and the 2 drives for the NVMe SSD or the 3D crosspoint and the TLC NAND. So the red numbers are IOPS and the blue numbers are average response time. So just glancing at it, you can see that in some cases for some workloads, one drive is better than the other, vice versa for the other. For the response times, they tend to be more uniform, that regardless of the I/O streams, the response times generally rank the same. So if it has faster response times, it'll tend to be faster despite what the I/O streams are, but I can have different I/O rates depending on what the workload is. Okay. So we said for persistent memory, sequential read-write benchmarks, 64-byte, 128-byte, 256-byte, and 512-byte. These are on the left side, sequential reads. On the right side, sequential writes. So you can see the yellow bar is higher. Higher IOPS are better. That's DCPMM. The green bars are NVDMN. So from an IOPS point of view, the persistent memory is faster for sequential read-write. For response times, you can see the response times are substantially similar until you get to a larger block size like 512-byte, in which case the NVDIMM has lower response time than the DCPMM. Looking at random read-write, the same way, you can see for random reads, they're pretty close. Even though NVDIMM, the green bar, is better for 64 and then less for the other 3, they're a substantially similar range. But note that the average response times for random reads, the NVDIMM is lower than the DCPMM. On the right-hand side, we're looking at random writes. Here, clearly, the green bars are higher. So you're seeing superior or faster performance of NVDMNs against DCPMM for random writes. Again, for response times, you can see that the NVDIMM has better response times. So when you look at those bottom ordinal ranking boxes on the right-hand side, the very bottom line says 1111. Average response time for NVDMNs is faster for all block sizes. For IOPS, it's first. Very simple one. On the left-hand side, it's 1111 in response time, but 1222 in IOPS. So again, the response times are consistent, but the I/O rate can be up or down. And in this case, they're not significantly different. Okay, let's look at the SSDs. So for the SSDs, we're using the SNIA IOPS test and the SNIA throughput test. On the left-hand side, and you can see the IOPS. Red is writes, blue is reads. So for the TLC NVMe SSD, it has second place for the red. The middle XL flash is third place, and the right-hand side 3D crosspoint has the highest performance for random 4K writes. For random 4K reads, the middle blue bar is the highest, and that's the XL flash. The second is the TLC NVMe, and third is the 3D crosspoint. But when you look at the overall performance, the 3D crosspoint is very symmetric. The reads and writes are about the same, and they're pretty high. So it kind of depends on what your workload is, what you really need. For throughput, you can see that in this case, the NVMe SSD has pretty balanced reads and writes. Again, the SLC XL flash has faster reads than writes. And then the 3D crosspoint is fairly symmetric as well. So again, these are corner case tests with this particular workload. But again, hazard to tell you that the media is designed for different kinds of workloads and different kinds of demand intensity. But this is just a corner case test that gives you a relative ranking. For the read latency, we're just looking at an outstanding I/O of 1. What's the response time of a single I/O round trip? So we express that as thread count 1, queue depth 1, or T1, Q1. So you can see here that as expected, NVMe SSDs have about 100 milliseconds response time. This is read latency. So you can see for random reads, you have 99, and for sequential reads, you have 92. 3D crosspoint is known to be very fast, and it's around 10 to 13 microseconds. So in the case of the random reads on the left, it's 11.9, and on the right for sequential, it's 11.2. And the drive really of interest here is the SLC XL flash drive in the middle. And it shows 20 microseconds and 13.5 microseconds, which is really very good. So the published spec for XL flash is 25 microseconds for read latency. So in this particular case, it outperformed what was in the public domain. This is the synthetic view of those real-world workloads. So we took the top 9 I/O streams and applied that ratio of I/O streams for every step across. It was like, remember the random 4K read-write example? Every step is 50% reads, 50% writes. So in this case, for each of the workloads, we're applying a constant workload to it. So looking first at just the green and the green and yellow bars, this is your NVDMN green and your DCPMM yellow. So you can see first off that they are much, much higher IOPS and much, much lower response times than the corresponding SSDs, which is red and blue. So for the Optane, you can see that it has 1 million, 1,000,004, 600, 600, and 148 IOPS for those particular workloads. And the NVDIMM is faster for the synthetic random AK 6535, slower for the VDI storage and the retail web, but faster for the GPS nav, and faster for the video on demand edge server. So you can go back and look at the box and the description of the workloads, and it might be faster because it's more write intensive, or it might be faster because it has more reads. It just really depends on the workload. For the for the NVMe SSD and the Optane SSD, the Optane is the red, so he's faster for the synthetic. Then for the video on demand and the retail web, it's slower, but then he's faster for the GPS nav and slower for the edge server. In terms of response times, you can see that the NVDIMM is faster than the DCPM on these particular workloads. Now again, these workloads are captured. They're comprised of very large block sizes and transfers, and these are not particularly the type of workloads that you would see in a persistent memory architecture. But having said that, the IOs are what they are, but in terms of response time, you can see the NVDIMM has faster response times for all of those particular workloads. In the same case, the 3D XPoint has faster response times than the NVMe SSD. So that's an expected behavior. In the first case, it's probably workload dependent. And then this is the same look at those 4 workloads, but as a replay. So here we replay the sequence of the IO streams that we observed. So it can start out with SQL Server backup, then do morning boot storm, then do mixed IOs for working hours. So when you look at this for the VDI storage, again, Optane is faster than NVDIMM, but in the next 3 cases, NVDIMM is faster than the DCPM. For the SSDs, the red 3D XPoint is slower for the first 3 and faster for the last. But they're pretty close to the TLC NVMe SSD. So it's kind of interesting that the NVMe SSD has faster performance than a 3D XPoint SSD. But again, it's just for these particular workloads. When you look at it from a response time point of view, you see what you expect is that the 3D XPoint has faster response times than the NVMe SSD. Again, for the Optane and the NVDIMM shows slightly faster response times. So I'm sure you're very excited to see all these graphs and charts. You can look online to compare. But the main point of this is you should be careful when you benchmark any storage, because storage is designed for a particular workload. So you should know what your workload is and then use that workload to characterize your storage. I can find a workload that can make any drive look pretty good on any given day. So it's really all about the workload. So at this point, I'm going to hand it over to Yafei, and he's going to talk about performance tuning. Right, it's forward.
Okay. Thanks, Eden. Hello, everyone. My name is Yafei, and I'm from Move your mic up just slightly.
You have to turn it on the box.
It's on, right? I thought it's on. Right? Oh, okay.
It's like in China, the slide advances off.
Okay, thanks. So my name is Yafei, and I'm from Dapu Store. We place intelligence inside the NVM devices. Eden, you have eaten up my time, so I will go fast. But but you have the real meat. So I started to work with Eden a while ago, and we have made a good progress on the SSD performance tuning with the real workload. So in my part, I will talk about how we utilize the artificial intelligence and the machine learning with the real workload to optimize the XL Flash SSD. So what is XL Flash? XL Flash is SLC 3D NAND flash memory, focusing on the low latency. It's offered by the Kyocera, and formerly that is the Toshiba Memory Corporation. Compared with the TLC, it has much lower latency. The TR is only 5 microseconds, and it has a high endurance. And more important for us, it has the compatible packages, and it's easy for us to port to the existing SSD controller. And according, based on the latency performance, we can put in this order, right? So from the left to right, DRAM, Optin, XL Flash SSD, TLC SSD, HDD, and tape. And from right to left, higher cost, lower capacity, and lower latency. What's that? Okay. So here, we use the real workload to compare the XL Flash SSD and the TLC SSD. So you can see here, we use the same controller and the same firmware architecture. And most of the firmware code are the same. So you can see that in general, the XL Flash SSD is much better than the TLC SSD. As we all know that it's a big challenge for performing performance tuning on the NVMe devices, because it's an embedded system and you have to make the tools to do the troubleshooting. And also there are many dimensions you have to consider in the target, such as IOPS, queues, low latency, reliability, etc. And more important, it's hard to get the real workload from the user cases. SNIA has provided some very good benchmarks and I/O traces, which are very helpful. But we have to face the complex workloads from the commercial world. So normally there are always some workloads you cannot handle. And so that's why we started to think about how we perform the tuning. And is there a better way to do that? We thought it might be a good idea to put intelligence into the devices and make those devices smarter enough to predict IOs from the host side. So if the devices can do such job, the devices can have dynamic strategies and it can return better performance. So we have explored different methods, including neural networks and machine learnings. And finally, we found LSTM is a good technology to do this job. LSTM stands for the long short-term memory. It's one kind of the recurrent neural networks. And LSTM has been applied in various applications such as weather forecast, language modeling, etc. And it's good to handle the time series problem. Since the storage I/O prediction is also a time series problem, so we use LSTM to do the storage I/O prediction. But the major challenge of using LSTM is the computation complex. So in this case, you cannot just apply this technology to the existing controller. So you have to make a special hardware. So that's why we made the FPGA to do the work. So you see that from the LSTM, there are multiple layers, the input layer, the hidden layer, the output layers. And inside each layer, there are many cells. And inside one cell, you can see there are 4 gates: the input gate, cell gate, forget gate, and output gate. The 4 gates decide which states should stay and which should be forgotten. And in our proposed model, the input layer, we have 4 cells, which are the I/O, the I/O address, the length, the read-write ratio, and the read-write interval. And the output has 1 cell, which is I/O intensity. That is the output we want. And we implemented the FPGA-based SSD, and we got very good results. So the I/O we got is from the SNIA and also the real world. And so you can see that the red curve is real I/O intensity, and the blue one is a prediction result. So it matches very well. But again, it needs compute. And normally, the existing SSD or NVM devices do not have such compute capability. So in order to make this technology commercial, to make it popular, so you have to make an ASIC chip, including this LSTM IP. That's one way to go. The other way, we thought maybe we can do something lightweight on the software level. So we did such work, and we implement the firmware level, the reinforcement learning algorithm. So this chart shows a performance tuning framework. You can see that the green one is LSTM hardware, and the red one is the machine learning embedded C library. So they are separate. We need either of them to do the prediction job. As long as the device has a prediction capability, it can do a lot of things. It can do it has a smart cache policy, the smart GC policy, and also it can do the on-the-fly queues management, etc. So now we have 2 effective approaches, software solution and hardware solution. So what are the differences? So from the response time perspective, the hardware is a nanosecond level, and the software is a microsecond level. And from the predict window, you can see that hardware can do the millisecond, and the software only does the second level, which means granularity is different. And the predict performance, the hardware is better than the software. So since hardware, next step for us is to have a ASIC test chip, including this IP this year. And the software we have implemented, and we team up with Marvell and Keynote together. And for Marvell, we use their latest enterprise SSD controller, which is ZAO. And we got XL flash samples from Keynote. Here, you see that the left one is without machine learning optimization. The right one is with machine learning enabled. So you can see that the improvement is around like 20%. And again, the workload we use is from Eden. This is a real one and a mix of read and write I/O streams. Generally speaking, so we think we are on the right track to ask the device to predict the I/Os from the host. And but hardware, it needs compute, and the software, so far the improvement is not so much, but we are still working on that. This project is like a working in progress. And here I'd like to call more collaboration and partnership. So if you are interested, please talk to us. So maybe later we can together to do the more intelligence in the work here. This concludes my talk.
We're a little bit behind, but does anybody have any questions for Dapu Store? All right, we have, where? There we go. Why don't you get Tom and Jim mic'd up while we answer this question?
Yeah. Good. Okay. Thank you for your interesting presentation. So after the drive predicts the workload, what are the actions that the drive takes, based on the predicted results?
Okay, there are different ways to. So first, we need to get the I/O intensity, right? Once we get that, we know the I/O flows. We know whether it's like a 4K I/O or it's like a 512 bytes. And then we can design the cache. So basically, the cache can be divided to write and read, right? Pre-read or the write. So if you don't know that, then you have to fix the cache. But if you know this dynamically, then you can assign, cache to read or write. That's one way, to do this smart thing.
Great, excellent. Thank you. Give him one more hand.
Okay, thanks.
I think you win the prize for coming farthest.
Jim Pappas has created a tradition of doing a very rapid, very concise overview of the entire persistent memory and formerly NVMe summit in the past. And so Jim's a big
NVM summit.
I'm sorry, NVM summit.
Humans are
incapable. Yes.
NVM without adding the E.
They are. You've trained them.
Humans are incapable of saying real-world workloads, too, which Eden did, so I think he's from outer space.
Yes. But Jim is a big guy, so we feel like we have big shoes to fill. So with that in mind, we're going to try to explain some of the terms that are used and the description. So the first one is, in Jim's opening remarks, so we used hydrazine and nitrogen hydroxide to create a hypergolic reaction, which allowed us to cross the Kármán line, except then we found out that we had trouble with our system, and so we fixed that by a reminder of SCE to aux.
What Tom really means to say is that he said that we had the 8th year of the Persistent Memory Summit, and there was a good illustration of how latency latency for PM was a bad thing if you went through the SSD interface or the hard drive interface. He also talked about how Google Cloud and Azure have PM services now, and that CXL should take over the role that DRAM interfaces are using today for persistent memory. But he said that everything is driven by fear, all of the advances in that. Our next speaker was Andy Bechtelstein, who said that if you use Rocky for your TCP/IP interface with an NVMe over Fabric, it becomes disaggregated and the leaf spine becomes apart.
Now, what Jim meant is that 60 slides in 15 minutes, we think that Andy broke the land speed record, which is probably appropriate for a high-speed networking guy. He talked about 100G switching chips being kind of a limit for right now because of the difficulty in new technology. But he said that if you aggregate these together, you can get some really high speeds. He was even mentioning 800 gig Ethernet. The trick in the transitions to these technologies, though, is a cheaper per bit for the network transactions, and that optical lags wire networks. Who would have thought? So, Andy Rudolph, the persistent memory programming model. So I was C-flushing my NVDIMM when I made a P commit to do RDMA over a PMDK with my Perl.
What Tom meant to say was that Andy was talking about how in 10 minutes he was able to summarize 8 years of persistent memory summits. And even though at the beginning of all of this great labor, there were only 2 important persistent memory papers, there are so many now that he couldn't even count them. He did point out that even though we've made a lot of progress, there are certain places where there's snags, there are problems with security in the Linux implementation, and other than that, there's a lot more work that still needs to be done. So then our next speaker was Richard Bruner, who talked about persistent memory in the wild by explaining that DDR5 allowed the ACPI to do a UEFI over NVDIMM-Ns with an upmem disk overlay.
Now, what Jim is saying there is that he's been working on this since 2011. And the basic capabilities are available now to support persistent memories. And vSphere 6.7 works with persistent memories. And in fact, there's certification of persistent memory hardware. But he said it's very important that we focus on data protection. It's mediation for one class of failure, he said, and this is very important, is to pray. So, Soji Den Loe talked about persistent memory use cases, and if I murdered your name, I'm sorry. So I took my bucket cache, I filled it full of KVs, and then I went and checked my Bloom filter to see about the adaptive radix tree, but I found that it was covered with a Java wrapper.
Yes, and so what Tom's trying to say is that what Soji's talked about were 4 use cases: caches, stores, and buffers or memory, in which persistent memory worked out well, and that there were good practices that could be used for cache that would end up working this very well. He gave details on Cassandra stores and how they got streamlined with persistent memory, and I think it was his that had the 9 times improvement.
It did, yes.
Yeah, which was a really compelling case. He talked about the persistent use of persistent memory, and he persisted in talking about that. So,
we thought that was important.
Yeah. Now, the next speaker was Charles Fan, who spoke about memory at storage scale by telling us that the KDB pub/sub was used in the TerraSort to be a hypervisor.
And again, Jim, what he's really saying is he's doing for persistent memory what virtual memory did for multi-core processors. And MemVerge, he said, is a first mover in this market, so they think there's going to be other people following behind them that, and creating a new market here. And by 2025, persistent memory will be mainstream. And he wants to hire a marketing person to give his product a name. So again, a reminder of that. So Piotr Balcer, and again, if I killed your name, I'm sorry, talked about the evolution of the persistent memory development kit. There's some very interesting terms here. I took my LiveVMem KV and also my LiveVMem obj cap and my LiveVMem obj, but I did not take my LiveVMem BLK or my LiveVMem log because I wanted to save that for my live BMM cache. And just in case I was traveling in time, I wanted to do that with a non-temporal store.
What Tom means by that is that there were 7 valuable lessons that he gave for programmers. And I'm not going to recount every single one of them, but he went through a chronology of processes going from a very verbose 0.0.1 implementation in C to a C++ implementation, which he called libpmem oj obj++, which gave closure to transactions, but it ended up being, you know, much more brief and worked out a whole lot better. He did ask one basically existential question, though. He said, who knows what SETJMP open paren close paren is? I wrestled with that for the rest of the day. Stephen Bates wasn't here for that. Let's see, the name of the guy I'm trying to remember now. Yeah, Milind. He spoke. Oh yeah, it was down here. Milind and Scott Shadley, the two of them covered for him. Now Stephen would have used very colorful language had he been here, but I think that Milind did a very good job when he talked about CXL mem being used for SPM via UEFI in a framing format with ACPI for HMAT.
And what that means, of course, first of all, that Stephen Bates was channeled by Milind and Scott, and we felt they did with their Ouija board, they did a good job of that.
Yeah, it was like he was here.
It was. I almost felt the F word.
But cleaner, yeah.
Yes. Trifecta is NVMe. The trifecta he's talking about is NVMe, CLX, and persistent memory together.
CXL.
Oh, I did say that. CXL. Excuse me. He said there was widespread processor vendor support, and CXL dynamically multiplexes I/O, cache, and memory. And Scott Shadley, like Charles Fan, needs a name. Sorry. So Dave Eggleston was next, and he gave a great plug for Jim's reports there. He talked about media attachment and usage, and so part of this is the heterogeneous FRAM has to be used with properly with an open CAPI, but just in case there's some kind of capacitance issues, you need a high K dielectric that is also informed by the local scuttlebutt.
In case you didn't understand what Tom was just saying, what it means is that the future of DRAM is DRAM. He also wanted to say that we love and hate persistent memories. They're the best of things or the worst of things.
Yes.
But if the network is fast enough, which he reiterated what Andy Bechtolsheim said, is you don't have to worry about where the data resides. You can use pooled memory, and the pooled memory was mentioned before in the Intel talk. It was mentioned later on in other talks. Pooled memory appears to be where it's at.
We all want to dive into the pooled memory.
Yeah. So the next was Pratap Subramaniam, who was talking about persistent memory in Golang, which that was new to Tom and me. We didn't realize that the lang part stood for language. But he spoke very succinctly about mem tiers on 0-day using fat pointers to avoid chattiness and try to provide crash consistency.
And of course what Jim means is that he mentioned the difficulty of understanding crashes, as did Intel's Piotr Balcer. He put an entire key value store in persistent memory and found that gave him advantages. And his program built using Go language with a custom Go compiler, hence the Golang. And the persistent memory provided improved performance, he found. But without the compiler, it was overall a very unpleasant experience.
I thought he was saying Gollum some of the time there.
You think so? Gollum? Okay. Now, Jai Shi gave a very interesting talk on Exadata with persistent memory, an epic journal. And it was epic because the OLTP sailed along on the elastic PM log buffers, going forth through the channel of the networked ACK.
I hope Tom didn't lose you there, but what he was talking about is that every Exadata server, storage server, uses 1.5 terabytes of persistent memory. And they were using what she called the dynamic duo of persistent memory and RDMA to achieve 16 million IOPS in 19 microsecond latency. That's 320 times what the Exadata had 10 years earlier in its first instantiation. The persistent memory cache was read using RDMA, and that was the key enabler for this, because it got past an awful lot of the latency problems that you have going through normal storage or communications protocol. She talked twice about sandwiches. There was a sandwich between the top server and the bottom server in the rack where the communications, the RDMA things were, but also talked about how PMEM is sandwiched between DRAM and the NAND flash. And even though I had this really wonderful SNIA lunch outside, it made me hungry. So anyway, she had a good way of describing how things work that way. And we're glad that she was able to come and talk this year because her boss finally let her out of her cage because she has a released product.
Indeed.
Now the next speaker was Yao Wei, who is with Twitter and seemed to be talking about birds an awful lot.
A lot of birds.
With Pelican on the ADP. And the way that she described it was by saying that there was a cuckoo in the Pelican with a canary. And that ended up causing the QPS to have a slab and a zipless S array with a TWEM cache.
Now, what Jim means here is that a Twitter cache has small and wimpy clusters. Also, memory mode is boring, but direct app mode is less boring. She said, don't trust anybody else's network, so keep that in benchmarks. Keep that in mind. Memory mode is a good gateway drug, something we all should remember. And if you tweet enough, you will tweet on persistent memory. And 7 years on call made her focus on potential problems. Probably a good thing for everyone to try. So Jim Pfister talked about persistent memory hackathons. And he threw some pearls out to us, but there were 3 misses. I couldn't catch any of them. But I did do my NVMW, and so.
Yeah, and you know, Tom couldn't go on with too many buzzwords because Jim didn't use too many.
He didn't use enough.
But what Tom means to say is that even the dumbest blind manager in the world can do a PM hackathon.
Yes.
So we're looking for somebody who's got that on their resume. We need more hackathons in more places, and if you want to send an email to pmhackathon@snia.org, you can get on that list, send that resume that says that you're blind and dumb. And the organization, he spoke about the organization formerly known as SSSI.
Twice.
Yeah, and so I guess that's somebody else who needs a name, you know, I guess, well, you know, that's
another name, yes.
Before. Yeah, and so we need a namer here. But what was the most interesting thing about names was that we found out that in Perl, one of the P's is silent. So Eden Kin came on. Why did I get stuck with this one? Saying real world workloads. I said it, but I can't say that 3 times in a row. Anyway, so the way that he described it to us is that you use the LSTM to test out your DCP-MM or NVDIMM, or even an XFlash SSD under a dearth phenomenon, which is uses loss streams.
IO streams.
Oh, that's IO streams.
Yes,
okay.
Oh, and then
I can't read your handwriting.
Oh, I'm sorry.
It's typed.
Now, he showed us workload types and how to capture them, and he captured workloads in the wild and said that you can too. And again,
the wild ones taste better.
They do taste better. They're a little gamier. And again, can you say real-world workloads 3 times? So, our last speaker here was Yafei Yang, who talked also about real-world workloads. He took as LX Flash, but put it beneath a hidden layer. But his recurrent neural net found the QoS OTF management.
And what Tom means to say by that is that Yafei's talk showed good matches between I/O predictions that were done by his AI machine and what really happened in real life. And in performance, his performance tuning was done better in hardware than in software. And I don't know if you really noticed, but in that table that he showed, it was like 1,000 to 1 difference in the speed of the software development versus the hardware. And you know, you got 95% accuracy versus 80%, so I'm going to go buy one. And he's looking for collaboration and partnerships in this area.
So with that,
yeah, that's our summary of this. And I
give him a hand. That was great. All right, 2 more thank yous. So just briefly, and I know she's already left because she was deathly ill today, but Jenny Dietz was responsible for pulling this conference together. She led the team, made sure that everything was on time, worked her tail off on it. Even if she's not here, maybe she's watching the video or she'll watch it later. So let's all give her a big hand.
I was hoping to get more laughter.
And since she's not here, I'll say we're so impressed we're going to give it to her for the next 10 years, because if she doesn't see this, she might actually approve my expenses next month. Okay, thank you all for coming, for being patient, for soaking up the information, and for contributing to a wonderful PM Summit. We will see you next year. And more importantly, we'll see you out in the hallway for the reception. Thank you.